Well, it's a real, let me turn this on so I don't get in trouble. Oops. Is that okay? Technical person? All right, yeah. I think that's fine. Yeah. The button's green, so it looks good. Well, it's really a tremendous pleasure to be here at Cornell to give this rather modestly titled series of lectures on the future of a subject that has a long and glorious past, going back over 2,000 years to the ancient Greeks, who first started suspecting that there is a systematic way of understanding the enormous diversity of different phenomena we see in nature around us in terms of potentially simpler rules. The modern way we think about fundamental physics traces its origins back to Kepler, Galileo, and especially Newton, who gave us an additional very important insight that the essential simplicity and underlying unity of the laws of physical laws of nature are best expressed in the language of mathematics and in the language of simple mathematical laws. This makes talking about not just the future, but the current and the past state of the subject to a more general audience a little bit challenging without using this wonderful language. And therefore, in talking about it, one is normally tempted to use metaphors and similes and analogies to try to get the point across. And I will be doing some of that. But I will do my best to give you a straight story. Every now and then, there may be a little equation up there. It will rarely require knowing anything more than high school algebra. And if it bothers you, just ignore it. It doesn't matter anyway. But if it doesn't bother you, you might get a little something out of it. This part of physics, fundamental physics, is in an extremely interesting place right now. It's a very exciting period. And to explain why, we can start by remarking that the 20th century began with two very big revolutions in our understanding of the laws of nature, given by our understanding of relativity by Einstein, and even more remarkable and revolutionary discovery of quantum mechanics. That took basically from 1900 to 1930 to complete, and it completely overhauled our picture of physics. And indeed, most of today's lecture is going to be talking about what that overhaul looked like. You can very broadly summarize the rest of the history of 20th century fundamental physics as grappling with the repercussions of those two revolutions and trying to see how they make sense together. Okay? And it turned out that the remaining 70 years were really about just putting these two things together and understanding how they work together and understanding the extremely rich and remarkable consequences that putting them together had, and in a way that allows us to understand everything that we've actually observed about the physical world so far. So while the first 30 years were all about revolution, the last 70 were really fundamentally conservative. Okay? We were putting together the laws that we knew and loved together, relativity and quantum mechanics, and figuring out what all their consequences were. That's just the way it is in this part of physics. You never know ahead of time if what's needed is a revolution or just to be conservative, to keep going with the theories that you have. Okay? If we knew ahead of time whether, if the right answer was always to be revolutionary or always to be conservative, graduate school would be a much more boring place. If it was to be always revolutionary all the time, we'd hand our students berets and send them off to mountains in South America. If it was to be conservative all the time, we'd send them to Wall Street. Or maybe not. But you just never know ahead of time. And in fact, most of the 20th century the rest of the 20th century was essentially conservative. However, there are many reasons to suspect that the period we're in right now is actually going to require something revolutionary. And that's why it's exciting. On the theoretical side, there's clearly something very deeply wrong with these ideas that we have. And what's particularly exciting about this decade is that there's a whole slew of new experiments that are happening that will shed light on at least some of these theoretical puzzles. And we might have, if not the answers, certainly not the answers to all of them, some partial but important progress on subsets of them by 2020. So the way I've described it seems to have a big divide between conservative and radical thinking. But in fact, in practice, there isn't such a big divide. And the reason is the nature of revolutions in physics is not like the nature of revolutions in society, which are violent, bloody things that completely upend the previous order. That's never how it's worked in physics. In fact, what we find, and as we'll see today, is that revolutionary developments tend to involve a much deeper understanding of the things that came before. Not only do they not upend them, but they put them in their proper context, and they build on them to a much deeper understanding. This is why, in fact, regardless of whether your temperament is to be that of a conservative or a revolutionary, there is a basic philosophy that all of us in theoretical physics adhere to, which is what you can call a philosophy of radical conservatism. What that means, I think this is a phrase that was coined by John Wheeler a long time ago. And what it means, what a radical conservative does is take the laws that are known and push them to their absolute limits. You see if they make sense, push them to their absolute limits. They don't drop everything, abandon everything at the first sign of trouble. You just take what you have, you push until you actually run into an actual crisis or paradox. Once you find a crisis or paradox, you're incredibly happy. Because a crisis or paradox means that's where all the effort should be focused and something's got to give. Okay? But in practice, we are going to take this philosophy of radical conservatism very seriously in these lectures. And I'm going to first describe the theories that we have. So here's an outline for the 5 lectures. So today I will remind you of these revolutions that started the century, which involved enriching our ideas of space-time through relativity and quantum mechanics. Tomorrow I will tell you about our actual current picture of the universe. What's in it, what interactions there are, what sorts of particles there are, how they all fit together. And so that's a recapitulation of the 20th century in the first 2 lectures. And the 3rd and the 4th lecture, I will tell you about 2 very sharp theoretical paradoxes that really seem to push, to give a guide for what's going to come next. One of them has to do with the fact that for many separate arguments, all very strong individually, suggests that the very notion of space-time is not a fundamental one. Space-time is doomed. There is no such thing as space-time fundamentally in the actual underlying description of the laws of physics. That's very startling because what physics is supposed to be about is describing things as they happen in space and time. So if there's no space-time, it's not clear what physics is about. That's why this is a hard problem. Okay? And we'll actually, that's a serious comment, as we'll see. A second problem, and these may be related to each other, but a second problem is that in our current understanding of the laws of physics, it seems almost impossible to accommodate a very basic fact about our universe. Our universe is big. We're big. The universe is big. But the underlying laws that describe nature are microphysical. They operate at small scales. And as we'll see, this might not seem like such a crisis, but the ubiquitous phenomenon of violent quantum mechanical fluctuations in the vacuum that we'll talk at length about tomorrow and the next day seem to actually make it impossible for there to be a macroscopic universe. So trying to understand how nonetheless a macroscopic universe arises is going to be a really major challenge. We actually don't have a good understanding for that very, very basic question. Why is the universe big? Okay? We can accommodate it in our current theories, but the accommodation, as you'll see, is so absurd that it makes us think we're missing something very, very big as an answer to a very basic question. It's a wonderful thing about the status of our subject that the 2 driving questions in it are extremely simple to state and describe. You will really get an fully accurate and honest appraisal of what these problems are. It's harder to describe the solutions or the potential solutions, okay? But the actual problems are easy to state and understand, and we'll do it. And I'll end by discussing these wonderful experiments that are happening this decade, everywhere from the Large Hadron Collider to experiments that are designed to look for dark matter, to understanding the dark energy that seems to be driving the expansion of our universe today, there's a whole slew of experiments that will perhaps tell us something about some of these questions, and I'll describe that. But today, it's all about setting the stage. So tomorrow, we'll talk about the detailed things that are in the world, this particle, this interaction, and so on. Today, I'm talking about the basic rubric that we think governs all of physics. Okay? So we're not going to be talking in great detail about the actual content of the world. We're going to be talking about the very basic laws that govern it, relativity and quantum mechanics. And as a backdrop, I want to remind you what Newton's picture of the world was. And Newton's picture of the world, imagine here's time going vertically up, and here's space. Here's a particle just sitting at rest. Okay? Doop, 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 moving up in time at different snapshots in time. It's just sitting there at rest. Here's a particle that's moving at some fixed velocity to the right here. Okay? But here's something else that a particle might do. A particle might move in some curvy fashion. And what Newton told us is that when the particle moves in a curvy fashion, that's because it's being acted on by a force. And that force causes the velocity to change from one moment to the next. The change in the velocity from one moment to the next is the acceleration. And there's this famous equation, F equals ma, that tells you exactly how that velocity changes from one instant to the next. Okay? So in this Newtonian picture of the world, all you have to do is specify at any given moment, where are all the particles, how fast are they moving, and in what direction? Go. What are the forces? Go. And you will be able to predict everything that happens in the universe after that, simply by applying these laws of motion. Furthermore, the nature of the forces were that they're extraordinarily simple and beautiful. The force of gravity, for example, was described by the existence of a force on this particle 1 by the presence of particle 2 that was proportional to his famous constant g times the product of the masses divided by the distance between them squared. Okay, so there's extremely simple forces acting pairwise between particles, which together with specifying the initial positions and velocities would allow you to predict everything. Note also that this picture allowed a very interesting notion of an action at a distance. Didn't matter how far away that particle was, it would still exert a force on you. If the particle was 10,000 meters away and you moved it over there, then instantly over here, you would feel the force changed, right? It's now pointing in that direction rather than in that direction. So there's a notion of an action at a distance. This was this clockwork picture of the universe that really allowed you to predict everything. There was no part of the universe that wasn't accessible, no part that couldn't be understood and predicted, okay? All of that's going to change, of course. So let's first review how Einstein changed part of this. So Einstein's name is famously associated with the principle of relativity, but what's sometimes not appreciated is that actually relativity is not an idea that goes back to Einstein. In fact, even Newton's laws had a form of relativity that even predated Newton himself. It was Galileo who first realized that this notion of relativity existed. What's the idea behind relativity? The idea is that, let's say I drop a ball, and I just drop it straight down. Then I know that after 1 second, it'll have fallen 5 meters. After 2 seconds, it'll fall 20 meters. 3 seconds, 45 meters, and so on. The distance that it falls is proportional to the square of the time as it falls. And that's something that I can just observe about what happens when I drop a ball here. Now I can ask a different question. What happens if I take the ball and I throw it? Okay? I throw it that way with some velocity. I guess I chose it to be 7 meters a second here. Okay? Now that's a different question, right? It's not just dropping it. It's a different question. I'm throwing it. Okay? But the idea of Galilean relativity is you can figure out what happens if you throw it in the following simple way. Imagine you threw it that way in 7 meters a second, but imagine that you were someone else who was running along at 7 meters a second. Okay? That someone else who was running along at 7 meters a second wouldn't see that the ball was moving. That person would just see the ball sitting there. The idea is that what that person sees is exactly what you saw when you just dropped the ball. That person moving along also sees the ball fall, and fall 5 meters after 1 second, 20 meters after 2 seconds, 45 meters after 3 seconds, and so on. Okay? In other words, the nature of the laws and what the motion looks like the nature of the laws is completely independent of the frame of reference if you're moving at constant velocities relative to each other. Okay? And you see, it's actually a powerful principle because it allows you to predict something. It allows you to predict what the shape is going to be if you threw the ball. It's very simple. You just imagine that first you were running along with it, so we know what would happen then, it's just falling. And then now you just go back and say, if I was running along with it, it would fall straight. If I'm not running along with it, that just means that every second it's moving forward in this direction by 7 meters. Another 7 meters. Okay? So the shape here is a parabola. So it's quite powerful. Knowing that when you drop it straight, it falls in a straight line, you can deduce from this principle of Galilean relativity, which is a consequence of Newton's laws, that you will fall in a parabola otherwise. Another consequence of this is that if you're sitting on a spaceship, and please forgive my terrible drawings throughout these lectures, okay? They're only going to get worse. So, if you're sitting here on a spaceship and you throw a ball with some velocity v, then imagine that also the spaceship is moving. Okay? If the spaceship is moving with some bigger other velocity, capital V, then the ball appears to move at a velocity that's just the sum of the two of them. And that's just a completely intuitive fact. Okay? If you're running along and you throw something, then it's going to be moving with a velocity given by the sum of those two things. That's another consequence of Galilean relativity. And Galilean relativity in due course was understood as a simple consequence of Newton's laws. Okay? But it has a disturbing consequence. The disturbing consequence, maybe I should before going here. The disturbing consequence is that because of this, it's possible to send signals between here and there as fast as you like. Okay? It's really easy. If you want to send it from here to there and your ball's going slow, just hop on a spaceship and make it go faster. If that's not fast enough, hop on another spaceship. It'll make it go even faster. There's no limit to how fast you can throw something from here to there. And that means there's absolutely no limit on how far you can extend your reach of influence. Okay? Arbitrarily distant regions of the universe, incredibly distant regions of the universe, can nonetheless have an effect on what's going on here because of this very basic fact that these velocities add. You can always make something go faster. Okay? Now, this is a disturbing idea. It may bother you, as it bothered Newton's contemporaries, that things arbitrarily far away can have an impact on what's going on here. You may wish to change that. Okay? You may wish to say, no, that shouldn't be the case. There should be some limitation on the range over which things can affect each other. But you see, if there is such a limitation, that must mean that there is a maximum speed at which any signal can possibly be transmitted. And that maximum speed must be exactly the same for everybody, no matter how they're moving. If it wasn't, then you could always go faster than it. Okay? And that's the whole point. That's what got us into this puzzle to begin with. So that means that there's got to be a maximum speed, let's call it c, for any signal transmission, but which must have the peculiar feature that every single observer agrees that when you're sending something that maximum speed, it's going at that speed c. So it doesn't matter if you're standing on a rocket ship or not. If you throw something with this maximum speed, everyone will always agree that it's going at the same velocity. Now, this quote-unquote c, of course, turns out to be the speed of light, around 300,000 kilometers a second, which is a gigantic speed compared to anything we're used to in our everyday life. But nonetheless, there is such an upper limit. And that basic fact, that very basic fact, you see, we demanded something that seemed innocuous. We don't want arbitrarily distant regions of the universe to be able to affect us. But that basic fact has startling consequences for the relationship of space and time. For example, imagine that there's a little box here that emits at some time a beam of red light and a beam of green light that go in opposite directions in a box. I'll draw pictures like this often in this lecture. This is just a picture of position in this direction and time in that direction. So here, sitting here at the origin here is when the green beam went off in one direction, the red in the other direction. And these x's are the splat that occurs here and the splat that occurs there. And you might be tempted to say that the red light hits one end of the box at the same time as the green light hits the same other end of the box. The word simultaneously makes an appearance. Okay? They're happening at the same time. But if it's true that there's a maximum speed, and that speed is the same for all observers, that is a fake notion. Because imagine the box was moving that way. Well, that speed is always the same. It's always 300,000 kilometers a second, and that end of the box is running towards it. That end is running away from it. So the red light hits that end before the green light hits that end. Or imagine the box was going the other way. Then you reverse the order in which the events happened. Depending on your state of motion, depending on whether you're at rest relative to the box, running relative to the box, you will come to a different conclusion about whether these events happened at the same time or not. Okay. So this was one of the first thought experiments that Einstein did that really bugged him, okay? Because it seemed to suggest that the notion of time wasn't absolute, that you couldn't say in some absolute sense that these two things occurred at the same time. This is a bedrock piece of Newtonian thinking, that there was such a thing as time that sits there ticking along at uniform rates for everything in the universe, but this seems to make that impossible. The word simultaneously is meaningless. There is no such thing as simultaneity as a simple consequence of this fact that there's an upper speed limit. Now, that's just the beginning of a remarkable fact. You see, what we just saw there is that depending on how fast you're running, you can either have things happen at the same time, or slightly earlier times, or slightly later times. There's no such thing as simultaneity. And that seems to imply that there's some sort of strange mixture between time and space going on. Okay? In fact, there is a strange mixture between time and space. And to prepare us for the idea, I'm going to talk about something much more prosaic, which you're all used to, which is a not strange mixing between space and space. Okay? So imagine you have, I don't know, a red arrow lying on the ground. There it is. It exists. There is such a thing as the red arrow in the world. But two different people, person one and person two, want to decide to describe the position of the arrow. They want to describe the tip of the one end and the other end of the arrow. Person one might come along and say, aha, this arrow, I can describe what it is by saying that there's two coordinates, an x-axis and a y-axis. They're orthogonal to each other, like I learned in school. And so I can say that one end, well, there's one end, and in the x direction there's an amount x1, and the y direction there's an amount x2. And that's it. I've given the coordinates of the tip of the arrow. Okay? If I walk x1 meters in this direction and y1 meters in the orthogonal direction, from one end of the arrow, I arrive at the other end. Okay, but someone else, person two, can come along, and without knowing at all what person one did, just do it differently. Right? Here's person two, could set up a completely different way of giving you exactly the same information. They're going to walk this way and then walk in the orthogonal direction. And the directions in which they walk are rotated relative to each other. That's all. They have no idea. One has no idea what the other did. Okay? They then compare notes. They say, hey, I saw a red arrow. Did you see a red arrow? Yeah, I saw a red arrow too. Right? Oh, really? Did we see the same red arrow? Oh, tell me, what are the coordinates of your red arrow? And one of them say, oh, my coordinates are 10 meters for x and 3 meters for y. And the other one would give two different numbers for x and y. And let's say, geez, it doesn't seem like we're talking about the same red arrow. Until they realize, wait a minute, maybe you were walking at a different angle than I was. Let's see. Let's see if it's possible. Well, there's a simple check we can do to see if we're discussing the red arrow. There's something we should both agree on, which is the length of the arrow. Okay? And you all learned in high school how to compute the length of a right-angled triangle like this. You just take the sums of the squares of the two lengths. So there's x1 squared plus y1 squared is what person 1 would call the length squared of that arrow. And x2 squared plus y2 squared is what person 2 would call the length of that arrow. And while x1 and x2 and y1 and y2 may not agree, if they're talking about the same arrow, they had damn well better agree on the length squared. Okay? So that's a check they could do. And to see if they're equal, they're probably talking about the same arrow. The arrow has some independent meaning all by itself. The coordinates with which it's described do not. They can depend on who you are. They can depend on various random things, but the actual length doesn't. So we can make a plot of all the possible x and y values that random different people could assign this arrow. And what we find is that person 1 is here, person 2 is there, there's some other person there, some other person there, some other person there. But we find that all the different x, y values that they could measure would all lie in a circle. Okay? And in that circle, the radius of that circle, the length squared of that circle would be L squared. So x and y can change, but there's something that's invariant, something that everybody agrees on, which is x squared plus y squared. Okay? We could say this more poetically by saying that position in the x direction and position in the y direction don't have an independent meaning. Only a mixture between the two of them has an independent meaning. We can rotate x into y, y into x. There is just such a thing as the plane itself, the xy plane. All right, this is very familiar, but it gets more interesting in the context if we go back and now think about relativity. Because in fact, exactly the same thing is happening in relativity. There's just some minus signs here and there. Okay? So let's go back to this picture where there's a light bulb going off and sending two beams of light in two directions, one seen by the eye of this blue eye and one seen by this purple eye. Okay? Now, and let's now draw, once again, here's the picture. Here's what one observer how one observer would describe what happens. Let's say, okay, here one went that way and it was seen by this guy there, and the other went there and was seen there. Okay? Another observer that's running relative to the first one at some fixed velocity would make a different conclusion. We just said, right? It could even say which one it hit first can depend. One can happen before the other. The word simultaneously doesn't make sense, and so on. So the second person would say, OK, that one's there, and that one hits there. So they will not agree on what the values of x and t are. By the way, always when I write these things, I multiply the times by the speed of light. That's just because the speed of light times time has the same units as distance. So it's just it's a simple way of going back and forth between distance and time. Okay? But the thing that they all agree on is that light is always traveling at the same speed c. That's the thing that they all agree on. And that means that no matter what that coordinate is, that its magnitude, its length, is the same as, in x2, is the same as c times t2. It's moving on 45-degree lines here. And similarly, that one, its magnitude is equal to c times t2. A nicer way of summarizing that statement is if you square the value of x, the square of the value of x is always equal to the square of the value of ct. Okay? That's just reflecting the fact that both observers agree that the light is moving at the same speed, c. So the first observer says x1 squared minus ct1 squared equals 0. The second observer says x2 squared minus ct2 squared equals 0. But that immediately tells us something rather remarkable. That there is an invariant that everybody agrees on, even though the actual x and t coordinates may disagree. And that invariant is not x squared plus y squared, like it was for the length of the little red arrow, but is x squared minus c squared t squared. Everybody agrees that the values of x squared minus c squared t squared are the same. So if we do the same exercise as we did before, imagine all possible observers. Imagine all possible x and t values that they might be able to assign to given events. Then instead of lying on a circle, they will lie on lines on curves where x squared minus c squared t squared is the same. So let's say we're talking about events, some event that took place here at the origin near x equals 0, but some time later. Okay, another observer might see it there. Another observer might see it there. But all observers would agree that it lies not on a circle, but on a hyperbola. Okay, that hyperbola. See, observers moving really, really, really fast might see that it happens out there. But it's going to lie on the same hyperbola. And that's how they can all agree that they're talking about the same event. They're talking about exactly the same event if this x squared minus c squared t squared is the same for everybody. If instead you have an event that happens over here, then it lies, all possible observations of that event would yield these possible values of x and ct that lie on this hyperbola. Okay? But apart from that minus sign, it's exactly like our x and y story. And we've mixed up space and time. Okay, so we can rotate space and time into each other. This fact had a number of remarkable consequences. For instance, let's imagine that an event here is the birth of something and the death of something later. Okay? That takes some amount of time, let's say 80 years if you're lucky. Okay? But another observer, moving very, very fast relative to that one, will see the birth at the same place with the death happening very, very far away. That means that to this observer, it seemed like the time span between birth and death took a lot longer. So it just seems that by running really, really fast, so if something is moving very, very fast relative to you, and if it lives 80 years, you might think that it lives a lot longer. Okay? That's called time dilation, and it's a real effect. We see it all the time. It's a commonplace phenomenon in our part of physics. One dramatic example is that the Earth is bombarded by very high-energy particles that hit the upper atmosphere and produce, amongst other things, a particle that we call the muon. Now, if the muon was just sitting here in my hand, it would decay and disintegrate in 2.2 microseconds. Okay? So it disappears really, really fast. If I just took it and I threw it really fast and ignored this time dilation effect, there's no way that it would make it from the upper atmosphere down to the Earth. It would just disintegrate too quickly. But precisely because it's moving really fast, this effect stretches out its lifespan. Okay? And that's how it manages to make it to the ground. This is real. Another effect, which I won't have time to explain, is length contraction. So things that move very fast shrink. And again, it's not in your head. It's meaningful. If you take a steel cable, you attach it between two spaceships, you start the two spaceships accelerating at the same rate, so they're moving faster and faster, the spaceships always keeping the same distance between each other. This rod actually contracts in size. Eventually it'll snap. Okay? Despite the fact that at all times the distance between the spaceships is the same, they're accelerating at the same rate, but the rod is moving faster and faster, it contracts, and it really snaps. It would really snap. Now, how big is this effect in everyday life? Let's say I wanted to make sure, I will not survive more than 80 years, but if I ran really, really fast and then stopped, I might get to see what the world looks like in 3,000 years. Okay? But as fast as I could possibly run, and I don't think I can run at 30 kilometers an hour for my entire life, but if I could, this would gain me 10 seconds over my entire lifespan. Okay? So you need to be going really close to the speed of light in order for this to be important, which is, again, why people manage to go for so long without noticing it. Another remarkable consequence is that mass, energy, and momentum got unified. So time and space got unified, but many other things, which were apparently unrelated, became unified in this way. So famously, E equals mc squared says that mass can spontaneously change into energy. Other notions, electricity and magnetism, were seen to be different aspects of the same thing and could be mixed up with each other in the same way that space and time could be. So this notion of relativity enriched a notion of space and time to something new, space-time. And Einstein went further to show that, that even this wasn't some static arena, but that space-time could be curved, and that the curvature of space and time was associated with gravity. So the Earth goes around the sun because it's taking the shortest possible path it can in this curved space-time. And again, this notion that space-time had some internal dynamics of its own and wasn't just static led to a number of dramatic consequences. For example, you've all heard that the universe is expanding, but it's not expanding into anything. Okay? When we say the universe is expanding, we really mean that at a steady rate, space is being invented all the time between all the particles that are out there. Okay? If you have these two galaxies, two red galaxies here, what's going on when we say the universe is expanding is a few billion years later, the universe has doubled in size. That means that there's space being invented constantly at a fixed rate between all these points. That's why it looks like they've separated now. Not because they're moving into anything, but because the space is being generated and created between them at a steady rate. Okay? That's a remarkable notion you couldn't even have thought of, you couldn't even have conceived of, if you didn't understand that not only were space-time unified, but that they had, but that they weren't some fixed mesh in which everything else happened. They responded to the presence of masses and particles, and that response had to do with gravity and other things. Another dramatic consequence of this extension of our notion of space-time is the idea of a black hole. You know that if you're on the surface of the Earth and you throw a ball at 5 kilometers a second, that's pretty fast, but the ball will still land on the Earth somewhere. But if you throw the ball at 11 kilometers a second, it'll escape the gravitational field of the Earth and just go as far away from the Earth as you like. So there's a simple formula that tells you how fast you have to throw something in order for it to escape from so much mass in such and such region of space. And you can ask what happens when that speed approaches the speed of light. Okay? If you put so much mass into such a small region of space, then it can simply become impossible even for light to escape from that region. Okay? When that happens, simply nothing can get out. Absolutely nothing can get out. And that means that something very peculiar and new happens. That there are regions. It's possible to make regions of space and time completely inaccessible to us. You just put enough mass in there, you can collapse a region into a black hole. If you fall into it, before you cross this so-called event horizon, before you get too close, you can send signals to your friends, everything's great, life is fine, everything's okay. Then you cross over that event horizon, and no signal you ever send will ever make it out after that. This is again a consequence of the extreme bending of space and time that's allowed and made possible by these enriched notions of what space and time are. A better way of drawing this is that really, you imagine there's this throat that you can get sucked down, and if you're far enough away, you can send a light beam and have it get out, but right at the event horizon, if you just try to flash a beam of light out, you'll find there is no out. It'll just go zip around the horizon. Again, it doesn't even go 1 millimeter out. It zips around the outside of the horizon. And if you are a little bit inside it, just simply nothing you do will ever get signals out. And in fact, deep inside is a place that has a very unpleasant end for you. There's absolutely nothing you can do to run into this so-called singularity, and nothing you can do will avoid it. Okay? In fact, any amount of struggling will just make your demise take place more quickly. Okay? So again, this is remarkable. As I said, there could be regions of space that we'll never access that are because space and time are now dynamical things. Let's move on to discuss quantum mechanics. Quantum mechanics is in many ways, as I mentioned, much more radical than relativity is. A reason for that is that as phenomenal as Einstein's achievements were, they're largely involved taking existing concepts. Time and space were existing concepts that people talked about for hundreds of years. And he just figured out the right way of thinking about them. But when we came to quantum mechanics, we had to invent entirely new concepts and entirely new ideas that had no classical antecedents whatsoever. And that's why it was a much harder slog. A lone genius in a patent office could figure out relativity. But it took the German and English academic hierarchy with roughly 10 or 15 people working over 20 or 30 years to figure out quantum mechanics. It was not a lone genius working in a patent office. It was these guys wearing ties, you know. It really worked, but it took this great collective effort. All right. Here, too, quantum mechanics unified seemingly very disparate parts of physics before. So before quantum mechanics, there were phenomenon that seemed to have a particle-like character, like baseballs moving around, and things like light that seemed to have a wave-like character. So that was the situation in the 1800s. There were particles in the world, there were waves in the world, and that was that. In our modern understanding, there's no such thing as waves. Everything is a particle. But they're not classical particles. They're particles that move according to quantum mechanical rules. Sometimes large macroscopic collections of quantum mechanical particles behave as classical waves, and sometimes these large macroscopic collections of quantum particles behave as classical particles. But it's really the underlying quantum particles that manifest themselves in a certain limit in two different ways, wave-like or particle-like. The most remarkable thing about quantum mechanics is that it signaled the end of this dream that began with Newton, that there was a clockwork universe where we could predict if we knew everything, at least if we knew everything about what was going on at a given time, we could predict everything everywhere in the universe later. Okay? There's this picture of determinism. And this picture was completely smashed by quantum mechanics. So there's a variety of slogans that go with it that you've probably heard of. For instance, there's the uncertainty principle. This is just one big blow to this idea of determinism. Remember, Newton tells you that to predict what goes next, you have to give me at a given time where the particle is and how fast it's moving in what direction. The uncertainty principle says, that's impossible, I'm sorry. You might be able to ask the question in the English language, where is the particle and how fast is it moving? But it's a meaningless question that just does not have an answer. You can know that the particle, you can know where it is within some precision, but that's inevitably associated with some spread in the direction in which it's moving. And there's no way that you can make both of them, you can know both of them perfectly. These are encoded in these famous uncertainty principles that say the product and the uncertainty of the position and the momentum, you remember, is the mass times the velocity of a particle. But this product can never become zero, the way you could in a Newtonian world, but is always bounded by this number, known as Planck's constant, written here as h, with a little slash through it. Something similar is true for energy and time. And another slogan is that we can't, not only is the world is not deterministic, the only thing we can predict is probabilities for certain events to take place. And this is really, honest to goodness, true. It's completely nuts, but it's true. Okay? You can take two radioactive atoms, atom 1, atom 2. They're completely identical. They're produced in identical ways. They're in every possible way identical. Radioactive 1 will sit there and disintegrate in 1 minute. Particle 2 will sit there and disintegrate in 2 minutes. It just actually happens. Okay? It's a true fact about the world. That means that there's just nothing you can do. If you hand me one of them, I just can't tell you when it's going to disintegrate. Okay? That's a tremendous loss of predictivity for a physicist who thought they could predict everything. We can't even do something as dumb as tell you when some radioactive particle is going to decay. Tough luck. That's just the way the world is. What we can do, however, is if you give me a very large collection of these radioactive atoms, I can tell you on average when they will decay. Okay? What happens if you put a big vat of them in a box and you measure when every single one of them decays, and you just plot the fraction of them that decay in any given time, you'll find as you put more and more atoms in this box, this fraction will become more and more sharply peaked around some particular number. Let's say 86 seconds. Okay? So you can say that on average, they decay in 86 seconds. And that really means something. It means that if you give me 17 gajillion of them, then by far the vast majority of them will decay in 86 seconds. And the fraction of them that will decay in 86 seconds gets closer and closer to 1 the more and more particles that I have. Okay? So we can predict things on average. We can predict probabilities, but we can't make predictions for individual events, for individual occurrences. Okay? Now, once again, all of these uncertainties are very small for typical objects. So here's a typical object, me, okay? And just so you have an idea, if the uncertainty in my position is the size of an atom, then the uncertainty in my velocity, due to the uncertainty principle, is 10 to the minus 35 centimeters a second, okay? That's not very big. That's not very important, okay? So large macroscopic bodies will move around in a way where these effects are not important. But they become important on very small scales. And actually, there's a very important proviso to that, which I hope I have time to explain. But we'll see if I get there. Okay? All right, so here's a variety of, now it seems really depressing. There's so many fewer things we can predict. Okay? The world is not deterministic. But far from being depressing, quantum mechanics is the most successful physical theory we have ever had. Okay? And all of these things, the uncertainty principle, this indeterminacy and everything, plays a crucial part. There's an awful lot of nonsense said about quantum mechanics, and people relate it to New Age things and Eastern mysticism and stuff like that. And it's all complete load of crap. Okay? There's nothing sharper and more well-defined and harder with a harder coordinate than quantum mechanics. The reason why matter is stable is because of quantum mechanics. Atoms exist and are stable and make sense because of quantum mechanics. In a classical picture of the world, and this really caused people lots of consternation, you might imagine an electron spinning around the proton, but nothing stops the electron from just running into the proton and just banging into it. Okay? There's no reason you would have stable atoms. That's because the energy of the electron can be made smaller and smaller and smaller by getting closer and closer to the proton. That's the effect of the attraction, the electrical attraction the proton has on the electron. Not so in a quantum world. In a quantum world, what happens is that, you see here, the lowest possible energy, what the electron wants to do is to be on top of the proton and not moving, right? But the uncertainty principle says that's impossible. If I know it's right on top of the proton, I have no idea how fast it's moving. It could be moving so fast that it's actually escaping out of the proton, okay? And vice versa. So instead, if you were to try to visualize it, you would have to, and this isn't very precise, but it'll do for now. You should think of it as a cloud that's surrounding the proton. And what happens is that as you start getting too close, there's some inevitable energy due to the fact that you have some momentum, you're moving. And that extra bit of energy, due to the uncertainty principle, actually makes the energy go back around and increase. You can't get too close. Okay? So there's a nice stable place. And if you work it out, that gives you actually the size of the atom. That's what Bohr did. That's why Bohr is famous. Okay? So quantum mechanics, this uncertainty, this indeterminacy, goes into making matter stable. If it wasn't for that, atoms wouldn't be stable. And more than that, the fact that an atom there and an atom there and an atom there all more or less look the same is also because of this. Okay? So these are all, the stability of matter is a direct consequence of quantum mechanics. There are other strange features. You might imagine that there's a poor ball stuck here at the bottom of this well, and it's just sitting there at rest. And that's it. Its permanent future is to explore the vicinity of its little bottom here. Okay? But in a quantum mechanical world, that's not true. In a quantum mechanical world, there's always some tiny chance that it has, I don't know exactly where it is. I don't know what's exactly at the bottom. There's always some tiny chance that it could have some momentum that could kick it over and make it go to the other side. Okay, that's a phenomenon known as tunneling. This is impossible in a classical picture of the world, but becomes possible quantum mechanically. You see, again, this uncertainty allows a richer diversity of phenomenon to happen. Nothing would stop you. This conserves energy. Everything would be the same. Just taking the ball here, tuck, moving it over there. Nothing bad has happened. The energy is the same. Everything is fine. But it just can't happen in a classical world. But it can in a quantum world. The quantum world allows more things to take place. It unifies things that otherwise couldn't talk to each other in a classical world. This is also a very important phenomenon, which is, however, only important for small objects. There is some tiny chance that me sitting here will tunnel through that wall and spontaneously appear on the other side. Okay? Let me do the calculation for you to tell you what that probability is. The probability is around 10 to the minus 10 to the 30. Let's say that number again, shall we? Okay? It's not 1, it's not 10 to the 30, it's not 30 ones followed by 0. That would be 10 to the minus 30. It's 10 to the 30 zeros followed by a 1. Okay? This is an unimaginably small number, literally unimaginable. In fact, if I waited around long enough to see whether this happened, before that there would be some fluctuation in my brain that would make me think that something else happened. Okay, so it's completely unreasonable to even talk about probabilities that are this small. Okay? On the other hand, imagine that you're an electron sitting in the middle of a hunk of metal. Okay? And in this hunk of metal, there's a bunch of positively charged particles. Okay? And there's some well of energy. Okay? There's a well of energy just like the little well we drew before. And in a classical world, the electron would be perfectly happy to sit here, or sit there, or sit there, or sit there. And it would just sit there for all time and wouldn't move. But in a quantum mechanical world, that's not true. As we said, there is some probability for it to tunnel. And for electrons and metals, that probability is not small. In fact, it's very close to 1. This is where currents come from. Okay? currents are a consequence of this quantum mechanical fact that electrons are actually tunneling from place to place to place as we move along a piece of metal. For small things, this is an important and interesting effect. For me, it's not very important, which is why people didn't notice it for 2,000 minus 100 years. Okay? Another very important consequence of quantum mechanics is that the states of minimum energy, whatever they are, the minimum energy is never zero. Okay? This is going to be a fact that's going to come back and haunt us in the third lecture. Imagine you have something as prosaic as a ball hanging on a string. In a classical world, what's the smallest possible energy you could have? Well, it's zero. It could just be hanging and not moving. Okay? It has no potential energy. It has no kinetic energy. Nothing. In a quantum world, that can never happen, because I can never know exactly that it's actually hanging. There's always some uncertainty in this position, and associated with that, there's some uncertainty in its momentum, and there's some jiggling. There's constantly some quantum jiggling. You can do a very simple estimate that tells you that the minimum amount of energy is actually that Planck constant that we talked about times the frequency of this of the motion of this pendulum. Okay? So there's a tiny, for anything that oscillates, there's a tiny minimum amount of energy associated with it, given by this number h times frequency. This is historically where the quantum in quantum mechanics came from, because it suggested that lumps of energy couldn't be made as fine and be divided up as finely as you like, but came in little packets. And the size of the packet, as Planck first enunciated, had this sort of behavior. Okay? Okay. Now, when did I start? I have 10 minutes? Okay. All right. All right, let me try to see how much of this I can do. I want to just quickly try to give you, this may go a little too quickly, but I'll be very happy to discuss it in more detail if anyone's interested in coming down right after the lecture. I want to, often in discussions of quantum mechanics, we get very qualitative, and it leaves you, if you're not in the subject, it leaves you wondering whether we're just sort of BSing all the time. Okay? It's all uncertain. You don't know exactly what you're doing. What the heck are you doing? On the other hand, you say, no, this is the most spectacular physical theory we've had of all time. Trust us. Okay? So I just want to give you a taste of what quantum mechanics is really like. Okay? This is an honest description of the quantum dynamics of what you might think of as a particle moving around a circle. Okay? We're going to make our life easier and imagine that the particle can only live in certain bins that are placed around this circle. Let's start off imagining that it could live in 3 bins, 1, 2, and 3. Okay? And the rules of quantum mechanics, the underlying rules, there's no uncertainty principle and indeterminism and all that stuff. Those are words, those are consequences of an underlying very sharp set of laws. And the sharp set of laws tell us to talk about the state of the system in a very particular way. So let's start talking about this notion of a state of a system. Let's imagine that we have the particle living there in position 1. Okay? Okay, it's really sitting there in position 1. We definitely know it's sitting there in position 1. And we describe that by writing a little vector. Okay? It's called a wave function or a state vector. But it's really simple here. You see, I'm just writing 1, 0, 0. Imagine this is the first entry is supposed to refer to bin 1, the second to bin 2, the second to bin 3. So this would be, I told you that no matter what state the system is in, it's associated with some wave function or a state vector. This is the state vector associated with the ball definitely being in 1. That's a state vector associated with definitely being in 2. That's a state vector associated with being definitely in 3. So far, so good? Okay. Okay, now the magic begins. And the magic is that we're allowed to talk about other states. We're allowed to talk about completely general states that have not just 1, 0, 0, 0, 1, 0, 0, 0, 1, but actually any entries, A, B, C, or psi 1, psi 2, psi 3, if you want to be a little fancier. Okay? So you can really think of this as having a 3-dimensional space as being a little vector. Okay, being a little three-dimensional vector in this three-dimensional space. And its first entry is psi1, the second entry is psi2, the third entry is psi3. Slight deviation from normal vectors is that the entries of this vector aren't normal numbers, but are so-called complex numbers. Okay? If you don't know what complex numbers are, it's really simple. I'll tell you how to think about it. Each one of these numbers, think of it itself as being a little vector in a two-dimensional space. This is some other two-dimensional space. Each one of those numbers, each one of these little entries is actually a little arrow. Okay? There is a little arrow for 1, there's a little arrow for 2, there's another little arrow for 3. I'm done. If I give you these 3 little pictures of the arrows, I've completely specified the state of the system. Okay? Now, you can ask, what happens if I measure whether the particle is in bin 1, or in bin 2, or in bin 3? This is where the strangeness of quantum mechanics comes in. We can only predict probabilities. But quantum mechanics tells you that the probability to measure that you're in 1 is given by, you just look, there it is, psi1. You look at that little vector, you take its length, and you square its length. Okay? So the probability for finding the particle in 1 is a square of the length of the associated vector. Similarly for 2, similarly for 3. Now, that's how I describe the state of the system at any given time. What happens as, let's say I give you at some time, at some later time it's going to move around. Okay? This state is going to move around. There's something important about it. The total length of this little vector is always 1. That's because the ball is either in 1 or in 2 or in 3. The sum of all the probabilities has got to add up to 1. So as a particle moves, as the state moves in time, this state vector also moves around, but it moves around in such a way that the length of this vector is always 1. And a final thing I have to tell you is that if I have 2 state vectors, A and B, and here's what they are at 0 seconds, and at 1 second they evolve into these new vectors, then I might imagine a third state vector, which would be just adding A and B together. Then if I saw what happened to that guy later it would just turn into adding A and B at this time. So if I have A and B here, A goes there, B goes there, then A plus B would just go to this A at the later time plus B at the later time. Okay? So this is technically known as the fact that the evolution in time is linear. Believe it or not, I've given you all of the postulates of quantum mechanics. Okay? These are the central tenets of quantum mechanics. So how does life become interesting? Well, let's now imagine that I have many bins. So let's say there's 20 bins here. To specify the state, I'll have to give you 20 of these little arrows. So there's 20 of these little arrows. I'll get tired of drawing them in the vector, so sometimes I'll just draw them around a circle like this. So again, that little arrow is psi1, that little arrow is psi2. If I want to know the probability that this funny state will be found in 3, I just look, there's 3, I take the length of that little vector and I square it. 4, I take the length of that much smaller vector and I square it. So evidently it's much more likely to find this particle in 3 than to find it in 4, even though there's some small chance that it will be found in 4. Okay? So this is just some random state. Any old state is going to look like this. But now I'm going to show you the picture of some very special states. Okay? So consider this special state. So remember, these are just the values of those little vectors, right? So imagine this special state where that little vector, whose length gives you the probability, remember, right? As I go around the circle, it actually just sort of tracks the movement around the circle. Okay? Tack, 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 tack. Okay? That's a rather pretty looking state. Notice that the length of all these vectors is the same. Oh, I don't know what happened there. Sorry about that. The dangers of Microsoft Journal. Okay? Anyway, all these vectors have the same length. That means that if you measured to see, is the particle in location 13? Is it in location 17? Is it location 3? There would be equal probabilities to find them anywhere. All those lengths are exactly the same. Okay? But this is not just some uncertainty in is it here or is it there or is it there? Did I flip a coin or flip a 20-sided coin to decide where I found the particle? It's not like that. In fact, this state has a very interesting property. it has a definite value not of position of the particle, but of its momentum. Okay? This state turns out to correspond to the particle actually moving around the circle with a very definite momentum. It's the momentum being Planck's constant divided by the radius of the circle. Okay? That's what a state of definite momentum looks like. You see, it looks nothing like the state of definite position. The state of definite position would just have one of these arrows in one slot and zeros everywhere else. The state of definite momentum has equal length arrows everywhere, but what tells you what momentum it has is the fact that the arrows are cycling around the circle and coming back to the starting point. Okay? You might imagine other things. Maybe as the arrow goes around, it cycles around twice before it comes back to the starting point. That's what I've schematically represented here, where I got tired of drawing all the rest of them. Okay? Well, that corresponds to a particle moving with a momentum 2 times h bar over r. Okay? So the value of the momentum is encoded in this interesting way the angles of these little arrows move as you move around the circle. What if the arrows moved around the other way as you went around the circle? Well, that corresponds to the particle moving in the opposite direction. Okay? So the states of definite momentum, these are them. They're not the states of definite position, but there isn't some gibberish, right? There is one states that are definite positions, the other states are definite momentum. This is the meat of the uncertainty principle in action, but now you're seeing much more sharply what it actually looks like. This is a completely honest description of what as I said, of the description of the quantum mechanics of a particle moving around a circle. This is actually how we do it and how we teach it in courses. Okay? A final comment. I told you that for large objects, these quantum uncertainty effects were irrelevant. But that's only part of the story. For large objects, it's true that there are certain states, like me, roughly speaking, sitting here with small uncertainty in position, small uncertainty in velocity. Okay? Those states exist. That's very nice. They're sort of approximately classical-like states. But you might wonder why we don't see other crazy states in nature. For example, nowhere in the previous example did I say that that little ball was small. That little ball could be me. Okay? Nowhere in this example. So how come we don't see me in these crazy states? Okay? Why don't I walk in the room and see me in a state where you don't know exactly where I am, but I'm definitely moving that way, okay? And by the way, it's not, again, it's really meaningful. If you put little turnstiles in the way, that all be spinning, okay? You would see that I'm moving that way, even though you had no idea where I was. But how come we don't see that? How come when you walked into this room, this state of horrible and utter chaos isn't what confronted us, and instead you find people roughly well localized sitting in seats and so on. Okay? These other things are also perfectly decent states. They're there. Why don't we see them in nature? So the statement that quantum is small and classical is big is only part of what's going on. There's actually something deeper. The really correct slogan is not that quantum is small and classical is big, but that quantum is open and quantum is closed and classical is open. By which I mean simply the following. The reason why we don't see these crazy states is because of something that so far in this entire discussion I've neglected. In this whole discussion, we pretended that all that was going on was this ball moving around the circle and everything else. But there's something else going on. There's air molecules in the room. There's all sorts of other things out there. They're also part of the system. Even if there is some measuring apparatus that's going to be measuring what's going on, that's also part of physics. There isn't some separate weird part of physics which is measurement and the conscious mind of the experimenter that's wondering what's going on. It's all part of physics. Okay, we can describe all of it in one gigantic large system. And in fact, if we imagine here all the air molecules in the room, at some initial time, here's the state that the particle's in one, the air molecules are all over the place here. What would happen after a very short time? Oh, the particle would still be in location 1. Now the air molecules will be in some different location. And the precise location where they will be will depend on the fact that the particle was there. Now some of the air molecules bounced off of it there and are moving in a different direction because it was there. Okay? Many of them will bounce off of it and move in different directions because it's there. So if I wanted to specify the state, I'd have to not only specify the state of the ball, but also the state of all the air molecules. And a short time later, that state of all the air molecules is in something different, but it's something different that's correlated with the fact that the particle is sitting there in 1. there's something else that would happen correlated with the particle sitting there in 2 and correlated with the particle sitting there in 3. Now let's say I took one of these crazy states, which was a sort of uniform amount of all of them. By this principle of linearity that I told you earlier, I can make a precise prediction for what the state of everything is later. The state of everything later is, again, the particle 1 is sitting there, but now there's a state of the air molecules correlated with the fact that 1 was there. Similarly for 2, similarly for 3. That happens very rapidly. Okay? But now let's say I just want to study what's going on with the ball. I have no idea what the air molecules are doing. I'm not keeping track of all the details of what the air molecules are doing. I'm just looking at what's going on in particle 1. That fact of not paying attention to the air molecules, ignoring the air molecules and just studying the system itself, completely destroys this remarkable quantum coherence. Remember I told you the precise momentum, for example, that we had the state which were these particles going around the circle, right? And I said this was a magical state. The precise value of the momentum, for example, this is not just some random state where you don't know, you throw a 20-sided die to decide whether the particle is here or there. Okay, it's a very special state where there's extra information. The extra information, it has some momentum. And that momentum is encoded in the very special relationship between the arrow in this direction and the next direction and the next direction and so on. Okay? But the second there's any tiny interaction with this environment, that information becomes lost. That information is there, but to recover it, you also have to keep track of what happened to all the other air molecules out there. And we don't do that. Okay? In a technical sense, the overlap between the state of the air molecules 1 and the state 2, in other words, those states that were correlated with the particle being in position 1 and being in position 2, is some absurdly small number, another one of these absurdly small numbers. That's because a huge number of air molecules interacted. Even if any one of them changed by a tiny amount, there's so many of them that the net change is inevitably gigantic. And those states have nothing to do with each other. They're essentially completely independent, separate states. That fact, so this number is 0 for all practical purposes. And a little bit more detailed analysis tells you this completely destroys those delicate relationships between these arrows from one place to another that allow for that very interesting quantum state to exist. So the bottom line is the reason when you walk into the room, you don't see these crazy quantum states all over the place is because long before you walked into the room, everything was interacting with the air molecules. Okay? The presence of the air molecules measured already where everyone was sitting. And unless you look in extreme fine detail at what those particles are doing, these very peculiar quantum mechanical states don't make an appearance in everyday life. Okay? But they're there. They can really be there. And if you make things cold enough and protect them enough from the environment, it's possible to make even macroscopic objects really have that property that I said. You walk into the room, you have no idea where they are, but you definitely know they're moving that way. And the bottom line of this is that it is possible to make exact predictions in quantum mechanics, but it's predictions for peculiar sorts of observations. Okay? To make exact predictions in quantum mechanics requires two kinds of infinity. You have to take some system and study it with some measuring device. You have to do the experiment an infinite number of times because you don't know what's going to happen every time. We can only predict the probabilities. But furthermore, we have to do the experiment with an infinitely large apparatus. Okay? Again, if you don't make the apparatus infinitely large, there's always some chance that the apparatus itself suffers a quantum fluctuation and does the measurement wrong or thinks something else or something worse happens to it. Okay? So it is possible to make exact predictions in quantum mechanics, but it involves two idealizations, two infinities, an infinite number of experiments and an infinitely large apparatus. I go through these points in quite some detail because they're going to play a crucial role in the doom of space-time and the trouble with the macroscopic universe that we're going to get to in a couple of lectures. Okay. All right, let me skip that. Okay, so let me end. So I told you the story of quantum mechanics and relativity, and I hope you're struck by something. Something that always strikes me when I think about it, which is that these big revolutions, which are so celebrated, are actually associated with a dramatic decrease in the amount and number of things we thought we could predict about nature. Before quantum mechanics and relativity, remember in this Newtonian picture of the world, we could, in principle, predict everything about everything. There was no part of the universe that was beyond our reach. There was nothing that we couldn't, in principle, predict with arbitrary precision. It's an enormously powerful conception of what the power of the physicist might be. Okay? But we discovered something very important, that there are limitations to what we can talk about. Even in relativity, we can't understand we can't access what's going on inside a black hole. In quantum mechanics, even worse, there's no determinism. We have to do these experiments infinitely often to measure probabilities with big apparatuses. We have to have the separation between big apparatuses and small systems that we look at. Okay? So it's very peculiar that we seem to be finding out that we can predict fewer and fewer things about the world. But there's a strange paradoxical flip side to that, that the more we understand these things, the more we see that relativity and quantum mechanics unified a seemingly completely different phenomenon and made them turn out to be different aspects of the same underlying thing. Space and time became unified. Energy and mass, waves and particles. Okay? So it's strange. On the one hand, we seem to have fewer and fewer things to predict. On the other hand, the things that are left seem to be more and more closely related to each other. This is probably not an accident. You see, what this is really, the fact that there's fewer and fewer things to predict is actually, there's a deep reason for it. It's because there are fewer and fewer things because what seem to be very, very different things in the classical world turn out to be different aspects of the same thing. There are fewer and fewer things we can predict is related to the fact that the things that are left are really all the same thing. Okay? So these are two important flip sides of each other. Again, I stress this fact because in the third and the fourth lectures, we're going to see big generalizations of this. There are even fewer things that we can predict when we push to the limits in this philosophy of radical conservatism, the theories that we currently have. There's even fewer things that we can predict, and yet, as we'll see, even more and more things are going to seem to be unified with each other. Well, we can all extrapolate what the end point of this might be, but I don't know if we're going to get there anytime soon. Let me just end by giving the advertisement for next time. The marriage of space-time and quantum mechanics, so we talked about relativity, we talked about quantum mechanics. As I said, much of the rest of the 20th century was about putting these two concepts together, which turned out to be a remarkably constrained, difficult, but ultimately successful thing to do. And the marriage brought a whole variety of further surprises that tomorrow is going to be about. For example, the fact that antimatter has got to exist. That for every particle in nature, there's some antiparticle. If they met, they would annihilate into energy. Okay, there's electrons and anti-electrons. They really exist. We make anti-electrons routinely in high-energy physics experiments. There could be an anti-me out there somewhere. Okay? Who would finish lectures on time. And associated with that, a really radically new picture of what we conventionally think of as empty space. In fact, as we'll understand, empty space is not only not really empty, but almost everything that we do in fundamental physics is about trying to more and more deeply understand the properties of the vacuum of empty space. But that's for next time. So that's where we'll pick it up tomorrow. Thanks a lot.
Take a few questions.
Absolutely. Absolutely. Well, no, but this is, yeah. So this phenomenon, which I described briefly, which really deserves a whole talk on its own. But the phenomenon the reason we don't see these funny quantum states is because things are interacting with an environment around them. That phenomenon is called decoherence. The question was whether this phenomenon of decoherence explains the famous Schrodinger cat paradox, or gives an explanation for why we don't see cats that are both alive and dead in Schrodinger's famous paradox. Absolutely. It's because the cat's being bombarded with air molecules all the time. Right. Right. A very, very cold cat would. Right. An exceedingly cold, well, they'd be dead for other reasons. Right. But yes.
For two reasons. One, if I'm in one of the spaceships and I'm not moving, and so the rod wouldn't snap, and the snapping or not snapping sounds as if it should be.
We can go through this in detail. Maybe we can go through this in detail offline. It's a wonderful true fact that if you take and it's really because this phenomenon of length interaction is actually real. The explanation again has to do with the failure of simultaneity. The explanation to your question, again, has to do with the failure of simultaneity, because when I said that I'm starting them off like this, and then at the same time they start accelerating, okay, then right. So that breaks the symmetry that you're talking about, right.
You seem to have said that quantum mechanics has a limit for us, we predication.
Yes.
What do you think us out of the equation?
It has nothing to do with us. Right. No, I meant we in the royal, very royal we sense. One. Yeah.
Does the universe know what it's doing?
Apparently. Now, I really want to stress this, that really an awful lot of nonsense is said about quantum mechanics. And it's true, there are mysterious things about it. It's true, it's strange that the world isn't deterministic. The real mysteries, there are mysteries involved with measurement and the sorts of problems that come up. But all of them have to do with the words gravity and cosmology. Okay? If the words gravity and cosmology don't make an appearance and someone says there's something mysterious about quantum mechanics, they're selling you something. Okay? In particular, when we do measurements down in a lab, when normal things happen, these are completely beautifully described by the standard laws of quantum mechanics, and there's no difficulty whatsoever. This basic phenomenon of decoherence solves almost all the old paradoxes. I should say that this was a point very well appreciated by Bohr and Heisenberg and their friends. Bohr was such a horrible writer, an explainer of this sort of thing, that it didn't really penetrate. But it was really revived in the 1980s and is really a perfectly well understood thing. The process of measurement is not some different thing, okay? It's part of nature. It's insane to say otherwise, okay? It's actually part of nature. You know, a measuring device is made out of the same stuff everything else is made out of. There's no mysterious consciousness involved with the process of measurement. There's no such thing as wave function collapse. Words for cognoscenti who at least might worry about some of these things. Everything is just good old-fashioned quantum mechanics. But there is something important about the fact that when you have interactions of small systems with very, very, very big systems, then these quantum coherences can very quickly become lost. That's the reason why classical physics emerges. It's the reason why measurements yield well-defined answers. But it does mean that if you want to make arbitrarily sharp predictions, you have to get these two idealizations to happen. You have to do the experiment infinitely often, and you have to do it with an infinitely large apparatus. And it sounds like a complete technicality until we get to the doom of space-time in lecture 3, okay, which turns out to be a direct consequence of these facts combined with gravity.
One more question back there.
But I'm just concerned that your wonderful number of 10 to the 10 to the minus 30
Yes.
should have some units per time.
Yes, I'm sorry. So I didn't put any units, Paul, as I'm sure you appreciate, because the units are irrelevant when the number is that small. So you could call it per second or per age of the universe, and it won't make that much of a difference. But you're right. It should have some units. He's absolutely right. Of course, if I just know for a fact that I'm here, then 10 to the minus bajillion seconds later, I'm still here. So there's some probability for unit time for tunneling across the wall. And I didn't give the appropriate units, but the number was so tiny that it doesn't make any difference. For the electron, when I say the probability is 1, it does make a difference. And there are some typical characteristic velocities with which electrons will move around from one well to the next. There, I really should have responsibly put in a per second. I just didn't know the number off the top of my head. And today I want to tell you how those general physical principles are realized in our actual universe. Okay? Before I do that, I just have a quick coda to some of the things said in yesterday's lecture. So those of you who weren't here yesterday, just ignore me for 2 minutes. First of all, it was pointed out to me by a couple of people that I said something very confusing about the radioactive decay of particles. The very first example I gave of quantum uncertainty was the statement that if you take 2 radioactive particles and let them decay, we can't tell, we can't predict ahead of time when one of them will decay. One could decay after 1 minute, one could decay after 2 minutes, and that's a very vivid illustration of quantum uncertainty. But I said that we could make a prediction for the average lifetime if we had many of them. The problem is that I was using the word lifetime for something that we in particle physics always use the word lifetime, but which normally stands for the phrase half-life. So you can make a very specific prediction for the half-life, but it of course is not true that if you take 1 million particles, all of them will decay, or a big fraction of them will decay at some intermediate time for 86 seconds, like in this example. What happens actually is if you take this large number of particles, and you just plot when they decay, just a fraction of them that are left as a function of time. If there's just 2 of them, you get some very choppy histograms. But if you have many of them, it'll start looking like a smoother and smoother histogram. Of course, any particular collection of them, it won't be perfectly smooth. It'll have little bumps and wiggles in it. But if we went to an infinitely large number of particles, there's a perfect curve, which is an exponential, beautiful, smooth curve. So the fraction of particles that's left would be something 1/2 to the power of the time divided by something that you might call the half-life. So this is what quantum mechanics predicts. Okay? That curve, the shape of that curve, the fact that it's an exponential is a precise prediction of quantum mechanics, even though it's not true for any finite collection of particles. A little graph like this that I drew yesterday refers to what you might talk about as a measurement of the half-life. So if you take the material and you wait to see how long does it take for the first half of it to decay, how long does it take for the next half of it to decay, how long does it take for the next half of it to decay, you could make a plot of when that time is. And of course, if you have a small number of particles, that plot will be very choppy. But as the number of particles becomes larger and larger, the plot will become more and more sharply peaked around the answer that we call the half-life. It's just, unfortunately, this is what we call the lifetime in particle physics. And so I said it in a confusing way, so I apologize for that. The second thing that I wanted to say, which is something I didn't get to last time, but we ended last time by marveling at how incredibly different the quantum rules were from classical physics. And they're so different, and the rug is so pulled under you from the point of view of the classical physicist, that you might wonder how we ever have a hope of figuring things out. Okay? If whatever we know now can change so radically compared to what we think, it seems like, okay, maybe we got lucky a few times, but this is going to be very, very tall order. But as I mentioned in the beginning of the lecture yesterday, that's not how revolutions in physics work. It's never the case that there is no possible connection to the previous theory. Okay? There always has to be a connection to the previous theory. Often the way of finding it, and in fact it's often a good way of finding what the next theory might be, is to try to understand more deeply and in as many different ways as you can the theory that you have already. And I just wanted to quickly mention that this fact that quantum mechanics isn't deterministic, but classical mechanics is, which is the feature, the hallmark of quantum mechanics, and the thing that makes it so radically different from classical physics. Okay? That fact, the absence of determinism, really had an avatar in classical physics. There was a clue sitting there in classical physics for 150 years that this might be coming. And that clue was an observation made by people about 100 years after Newton, that there was a completely different way of talking about classical mechanics. Not in terms of a particle goes from one point to the next because some force acts on it, and it goes from one place to another because some force is telling it where to go next, that extremely deterministic picture. But people found instead that there was a completely different picture for what might make a particle go from A to B. That a particle would go from A to B by picking a path that minimizes some quantity from A to B. It minimizes the average value of the kinetic energy minus potential energy. Okay? That turns out, it's not obvious, but it turns out to be a complete reformulation of classical mechanics. Okay? Completely equivalent to Newton's laws, but it's not manifestly deterministic. In fact, when you say it, it sounds startling. It's like what? The particle sniffing out every way it could go from here to there and choosing the one that minimizes the action. It turns out to be deterministic, but it's not. But it's not hardwired into the formulation. It's easier there's an analogous statement for light. Light goes from A to B just to minimize the time. It's really cool. So, for example, if you want to make it bounce off a mirror, then light goes from A to B in such a way that it gets from A to B as quickly as possible while being forced to bounce off the mirror. That forces this famous fact that the angle of incidence has got to equal the angle of reflection. Okay? Or, if you want to go from A to B, and I don't know, this is glass, so light goes slower in glass than in air, then it turns out that the fastest way to go from A to B is the way that satisfies the famous Snell's law that probably you all learned in high school. So, but this is a formulation of physics that's not manifestly deterministic, but turned out to be completely equivalent to the standard classical rules. Those classical physicists might have wondered, why is it true that there's such a reformulation of the theories we have that's so different in philosophy than the clockwork deterministic Newtonian picture? We now know the answer. This formulation exists because the world is not deterministic, but it's quantum mechanical. And as Feynman taught us, in a specific sense, the particle actually does make use of all those other paths from A to B. It does sniff out every possible path from A to B. It takes every possible path from A to B, with a particular state vector associated with each one of them. And for big objects, the biggest contribution comes from the classical path, which is how classical physics is partially emergent. So I just wanted to go through this because it's a beautiful example of this philosophy of radical conservatism. Okay? Things never just go haywire. Okay? There's always some connection between the old theories and the new ones. And we just have to find out what that connection is. And the way of thinking about the theories we have that makes that connection as transparent as possible. Okay? So even quantum mechanics, which is so incredibly different than classical physics, is not that different. It's not so different that there isn't a hint of it sitting there already in alternate formulations of classical mechanics. All right, that's it for the end of yesterday's lecture. Okay, so let's talk about what's actually in the universe. Okay? So there's 4 basic interactions that we know of. Gravity that keeps the Earth going around the sun, electromagnetism, as well as the less familiar ones, the weak and the strong nuclear forces. The weak force is what's responsible for radioactive decay. The strong force, or what we now understand is some very residual relative of the strong force, is what's responsible for keeping the protons together inside the nucleus. You know, in a helium atom, there's 2 protons and 2 neutrons. The 2 protons are repelling the heck out of each other. Something is keeping them confined to the nucleus, and that was called, a long time ago, the strong force. And anyway, there's modern relatives of it, but these are the 4 basic interactions that we call. And this is a picture of all the length scales we know of in nature, okay, that we probed experimentally. At the biggest distances, around 10 to the 28 centimeters, is the size of the observable universe, which is expanding, as we'll discuss. A million times smaller than that are galaxies. Okay, a whole bunch smaller than that, 10 to the 13 centimeters is the size of a solar system. Us, DNA, atoms, okay, around 10 to the minus 8 centimeters. Protons and neutrons around 10 to the minus 14 centimeters. And bracketing all of these things are 2 important scales, which are both clearly physically important and happen to represent the frontiers of what we've probed so far. Okay, so this largest scale, the size of the universe, is also called the Hubble scale. Down here at 10 to the minus 17 centimeters is actually another interesting length scale. Okay, it has a name. It's had a name for 70 years. And it's called the weak length scale. Okay, it didn't have that name for 70 years. But people have known about it for 7 years. And we now call it the weak or the electroweak length scale. So, as I said, this represents the frontiers of our experimental probe of nature. At the largest scales, we have a whole variety of experiments probing cosmology at very large distances. And at the very, very smallest scales, we probe those distances using very high energy accelerators. And the Large Hadron Collider, which is now running, is designed to and will thoroughly probe physics at distances around 10 to the minus 17 centimeters. So that's around 10 times smaller than the smallest distances that we've probed so far, around 1,000 times smaller than the nucleus of the atom, and around 1 billion times smaller than the atom itself. So now I'm going to clean this picture up and tell you about the scales that we think about in our subject. So that's the entire previous transparency. And the two scales that we think about are the extremes. Okay? So the very largest scale, the middle scale. There's actually a third length scale that we talk about that's even much, much, much tinier than those, called the Planck length. It's around 10 to the minus 33 centimeters. And let me tell you a little bit about these scales. These are going to be our friends for the next number of lectures. Okay? Before I do that, I want to make a note on units. I'm not going to crucially use this so much in the rest of the lectures, but I just wanted to say it because I can't give lectures like this without saying it. Okay? When we talk, I'm going to use centimeters and standard units, so don't worry so much. But you should realize that these are extremely artificial units. Okay? When we measure something in meters, every single number that has any meaning in physics doesn't have any units. It's some pure dimensionless number. When we say that such and such is 1.8 meters high, what we really mean is that there's some bar sitting in Paris. Okay? And if we take that bar and we put 1.8 of those bars up next to the thing, then they'll be commensurate with each other. Okay? But these units are completely artificial human units that have to do with some bar sitting there in Paris. Okay? And the fact that we have many different sorts of units, we have kilograms, units for mass, units for length, units for time. In fact, there's only one unit. Really, there's no units because everything is dimensionless. But given that we're going to be doing both relativity and quantum mechanics here, it makes a lot of sense to work with units with h bar and c are 1. Okay? Now that sounds a little bit confusing. Planck's constant, the speed of light, is 1. But what it really means is that I can trade a distance for a time using c. I can trade an energy for an inverse time using h bar. And so I can measure everything in one consistent set of units. Okay? Those units could have units of length, they could have units of 1 over length, they could have units of mass, energy. Any one of those suffices, and I can get everything else from them. Now, in particle physics, we really like to use a unit which is 1 giga electron volt, a unit of energy. Okay? And one reason it's convenient is that as an energy is approximately the rest mass of the proton. Okay? So, getting practice with these units, the size of the proton is around 10 to the minus 14 centimeters, and it's around the inverse of its size. It's 1 over a GeV in size. Okay? So the proton, you could say it's an inverse GeV, or you could say it's 10 to the minus 14 centimeters. So that tells you a conversion. Inverse GeV is 10 to the minus 14 centimeters. Okay? So for example, I am 10 to the 16 inverse GeV tall. Okay? Now, you see, that has real physical meaning. If I wanted to communicate to an alien how tall I was, okay, it would do me no good to say, if you put me up next to 1.72 bars in Paris, oops, sorry, if you haven't been to Paris, you don't know what those bars are, shoot, how am I going to tell you how tall I am, right? But their protons are the same as our protons. So I could say and said, if you stack 10 to the 16 protons on top of each other, that's how tall I am, okay? It's physical. These are correct natural units. That's why they're called natural units. My mass is 10 to the 29 GeV. That has real information. I'm made of around 10 to the 29 atoms. That's what I learned from them. Okay? Because basically all the mass is, roughly speaking, 1 proton. It's more than that per atom. But it tells me something about how many protons I'm made of. This lecture time, if you're lucky, is 10 to the 27 GeV inverse. These units tell us something actually very deep and fundamental about the kinds of forces we know in nature. For example, you all know that the electrical forces and gravitational forces are both inverse square law forces. You probably learned all that in school. So if we talk about the electric force between two electrons, or the gravitational force between two electrons, they both go like 1 over the distance between them squared. The electric force is repulsive, the gravitational force is attractive. Okay, so I'm writing it instead of a force, I'm writing it in terms of the energy, the electric energy or the gravitational energy between two electrons. And this is what the electric energy is. It goes like 1 over the distance. Okay, and there's something which, if you have dim memories from high school, involves a product of charges and something called K, and there's all sorts of terrible things. You measure them in coulombs. I can't get any of that straight. Okay? But actually, forget about all of that. If we use natural units, we actually learn something quite important. You see, energy has units of 1 over time, which is the same as 1 over distance. Okay? In these h bar equals c equals 1 units. So that means whatever this coefficient is, the 1 over distance already has the same units of energy. So whatever that coefficient is just some number. Just a number. That number turns out to be around 1 over 137. Point something, which I don't remember. Okay? That's fascinating. There's an actual pure number associated with the strength of the electric force. That's a pretty small number. 1 over 137 is some interesting pure number in nature. Okay. Let's do the same thing for gravity. For gravity, we say that it's there's g Newton times the product of the masses over r. Okay. Now this is different because E and R have this, 1 over R have the same units, but there are these two masses. So whatever g Newton is has to have units which are inverse of mass squared, which is the same as a length squared. Okay? So in these natural units, g Newton is 10 to the minus 33 centimeters squared. That was that third length that we talked about, that I said we haven't gotten anywhere close to probing this tiny scale, 10 to the minus 33 centimeters, but we know there's something interesting about it, and this is why. The Newton constant, gravity, is associated with this tiny, tiny number, 10 to the minus 33 centimeters. Okay? Now, this is really interesting, because this strength is not a pure dimensionless number. It has units. So that means that there is no real sense in which you can say gravity is weak or strong. Gravity is weak at very large distances compared to 10 to the minus 33 centimeters. It's astonishingly weak. But at distances comparable to 10 to the minus 33 centimeters, or even shorter, thereabouts, it should be very strong. Okay? There's nothing else to compare it to. You have to compare it to something to be able to tell if it's a strong or a weak effect. It's not invariantly strong or weak. It just depends on whether you're at long or short distances. Of course, most of everyday life is at enormous distances compared to 10 to the minus 33 centimeters. And that's why gravity is an enormously weak force. Okay? This electric force between two electrons is 10 to the 42 times stronger than the gravitational attraction between them. Okay? The only reason why gravity dominates at very large distances is that we're mostly made out of neutral things. Okay? But fundamentally, it's an incredibly weak force. Okay. So back to our pictures. This is just an advertisement for the next couple of lectures. Just this picture, everything in this picture contains all of the central sort of theoretical crises we have in physics today. Hopefully, fertile and important crises. His revolution will teach us everything we want to know about. But down here at 10 to the minus 33 centimeters, this is where the effects of quantum mechanics and gravity become important, and as we'll discuss tomorrow, space-time is gone. And we have to figure out how to replace it with something else. And there's another extremely salient feature of this picture, which is that there are these gigantic separations, right? There is this Planck length, and there's this huge gap till we get this interesting new scale, the weak scale, and even huger gap till we get to these much, much larger distances of order the size of the universe. So this is simply saying that the universe has many very, very separated important length scales from each other. Despite the fact that there's microscopic physics and microscopic laws, there is a big macroscopic universe. Okay? That turns out to be a very major puzzle. It's almost impossible to accommodate it in our current understanding of physics. We barely manage to do it, but in such a ridiculous way that it's clear we're missing something very, very big. So the answer to that really basic question, why is there a big universe, is also likely to teach us a lot and is likely to propel us through some new understanding. So those are the major discontents that I was referring to, and the discontents are going to be discussed at much greater length in the next two lectures. All right, so let's come back to our story of what's in the universe. Well, one of the big themes of the past 400 years since Newton has been the realization that everything that we can understand, all the apparently large, dizzyingly diverse array of phenomena, as we understand more, seem to be different aspects of the same thing. This really actually started with Newton, who realized that the same force of gravity pulling the apple down to the Earth was exactly the same force that was keeping the moon going around the Earth. Okay? That's something that's so seemingly obvious now we teach it in kindergarten, or whenever we teach it. Okay? But it took Newton's genius to realize that it was true. It's far, far from obvious. Amongst other things, the moon goes around in a circle and the apple just falls down. So he had to understand everything else about motion in order to see that this was not obviously a ridiculous statement. It was not just not ridiculous, it was true. Electricity and magnetism. You know, what the heck could lightning and these funny rocks that attract or repel each other have anything to do with each other, right? But Maxwell realized in the 1800s that there are also different aspects of the same thing. And furthermore, that light, which was the third thing that seemed to have nothing to do with the first two, was just undulations of electric and magnetic fields. So more and more things come into an underlying common rubric. As we discussed yesterday, relativity and quantum mechanics continued this in a very significant way, unifying space and time, unifying waves and particles into quantum particles. As we learn more and more, we see that everything that's out there is an underlying reflection of less and less. Okay? There's more and more unity, and we just have to figure out how to crane our necks around and see exactly why it is that everything, exactly how it works. But often in subtle ways, in often shockingly beautiful ways, we find that very different phenomena are different aspects of the same thing. So this is where we got to yesterday. And now I want to continue by telling you what happens when we try to put quantum mechanics and relativity together. It turns out that putting them together is not easy. Okay? One reason that it's not easy is that they use different words. Okay? Well, for one thing, relativity is deterministic and quantum mechanics isn't. So relativity is just an update of Newton's laws. Quantum mechanics changed everything. So, but whenever we say we combine quantum mechanics and something, in the last 100 years, what that's meant is that we take the something else and we make it consistent with quantum mechanics. Okay? So it's not that quantum mechanics has never once been modified since it's been written down in 1927. It's such an incredibly rigid structure, it's very hard to imagine how you could monkey with it in any way, which isn't to say that people have tried. But every success that we've had is by bending theories together in such a way to make them consistent with the laws of quantum mechanics. Anyway, but it's possible. It's possible to have put them together. But it's not easy. You might have given up, but it is possible. But the union between them turns out to have really unexpected consequences. And one of these consequences that I'll discuss is that putting quantum mechanics and relativity together, perhaps I should have said one more thing. Another major difficulty is that the basic laws of quantum mechanics, as I briefly discussed them yesterday, does make time very important. Okay? You say you specify the state of the system at some time, and then you evolve to see what happens at some other time. You say the word time just as often in quantum mechanics as you do in classical mechanics. Okay? However, relativity says, oh, the time, space, they can be mixed into each other. Okay? But that's the hard part. How do you get a set of laws in quantum mechanics that like to use time and make it consistent with the fact that you can mix time and space into each other? That is the challenge. It turns out that you can do it, but it has a number of remarkable general consequences. And one of them is that it forces the existence of anti-quantum. This is a prediction that was so strange and so counterintuitive that even the people whose theory predicted it, Dirac in particular, refused to make this prediction. antiparticles popped out of Dirac's theory. But it was so weird that he tried to call them something else for a long time. And it wasn't until actually Hermann Weyl, who had no stake in whether Dirac's theory is right or wrong, said, look, your theory predicts antiparticles. And it does. And of course, dutifully, it was discovered in atomic rays a number of years later. But it's remarkable that this unification of our extended notion of space-time, together with quantum mechanics, doubled the world. Now, I want to tell you roughly why this works. There are some holes in this argument, but it gives you the spirit for what is the right argument. Okay? It all has to do with this basic conflict between causality and quantum mechanics. Let's go back to relativity. Remember, in relativity, nothing can go faster than the speed of light. A way of seeing that is, let's say you have something at A, and it transmits a signal faster than the speed of faster than light to B. Okay? Why is that not allowed? That's not allowed because in another reference frame, running very fast relative to this, remember, we can move along hyperbolas, and in another reference frame, B would have occurred before A. So you fire a gun, you kill someone at B faster than the speed of light, in another reference frame, they're dead before the gun was fired. Okay? That's complete conflict with causality. Forget determinism. Remember, quantum mechanics means that you can't predict what happens next. Even more basic than determinism is causality, that what happens next is at least only a function of what happened before, for heaven's sake. Okay? So something even more basic than determinism is causality. And causality in special relativity forbids signals to go faster than light. Okay? However, in a quantum mechanical world, you can't forbid anything. Okay? For example, there's always some tiny chance that you thought you turned it on at A, but by the uncertainty principle, it's really turned on over there, it made it from there to there. You just think that it went faster than light from A to B. But one way or another, there is some signal leaking out outside of this light cone. And if you go to another reference frame, it indeed happens earlier in time. That's just inevitable if you have quantum mechanics. So what do? You could give up and say these things are not compatible with each other. We need a massive revolution that's going to upend both things. Or you could say, no, let's work harder. Is there some possible way to make sense? And there is one way out. The one way out is to give this process a causal interpretation. Say, how do you know something went from A to B? What, you say there was some flow of electric charge forward in time from A to B? Great, there was a flow of electric charge forward in time from A to B. You think there's a flow of charge, of negative charge, backwards in time from A to B here, but here's another way of interpreting it causally. There's a flow of positive charge forward in time from B to A. So your attempt to interpret what's going on that's forced on you by quantum mechanics causally gives you one way out, but it makes it a necessity for there to exist some particles out there of positive charge, otherwise completely identical to the electron, but with a positive charge. So you interpret its flow of charge forward in time for the meaning of this process. That's why antiparticles must exist. They're particles with identical, everything identical except their charge, with opposite charges. Now, that's a very basic consequence of putting relativity and quantum mechanics together. And it has a number of remarkable consequences. One of them is that the vacuum, even the vacuum, empty space. Remember, our march from Newton to now is endowing more and more and more structure to emptiness. Or to what Newton would have just thought as a very static arena. Space and time is a static arena where everything takes place. Relativity mixes up space and time. General relativity curves space and time. Now, even emptiness has some structure. Even the vacuum is exciting. And the reason is that there's really no sense in which the vacuum is, there's no useful sense in which you can think of it as empty. So let's imagine I take a magnifying glass. That's my sad magnifying glass. Okay? And let me try to use it to verify that indeed this region of space is empty. Doom-de-doom. I'm looking at the region of space. Nothing there. That's great. Okay? Nothing there. But in a quantum mechanical world, in order to probe what's going on at a short distance, by the uncertainty principle, I need a lot of energy. as we'll discuss on Friday when we discuss this golden era of experiments, that's also very expensive. You need to build very high energy accelerators to smash particles into each other at very high energy so you can probe very short distances. That's a direct consequence of the uncertainty principle. Okay? So if I want to probe what's going on in a smaller and smaller region of space, I need to use higher and higher energies. Now what happens is when that region becomes sufficiently small, I put so much energy into that region that nothing stops me from producing a particle and an antiparticle. Charge is conserved, energy is conserved, everything's conserved. Okay? Nothing stops me from producing a particle and an antiparticle. The act of trying to verify that this little region of space is empty produces for me a particle and antiparticle pair. So, and every such act will do that. Of course, the world is quantum mechanical. Every time you look, it'll look different. Okay? But one way or another, any act of trying to probe what's going on at short distances will produce particles and antiparticles. I told you we use accelerators to probe these very short distances, and we'll discuss at greater length on Friday. And people often describe accelerators as the world's most powerful microscopes. But you can ask, what are they looking at? They're not looking like at a piece of hair or something like that, right? They're looking at the vacuum. They're taking snapshots of the vacuum and figuring out what the vacuum looks like at these very tiny distances. Okay? And those snapshots are so interesting that we have to build $10 billion experiments to understand them. So if you have this boring picture of an electron sitting there, a point-like electron sitting there, and with electric field lines going out forever, that's really not correct. Surrounding it all the time are these particle and antiparticle pairs that are popping in and out of the vacuum all the time. What that means is that's a better mental picture than thinking that it's empty. That's a mental picture that's closer to telling you what actually happens in an experiment. Okay? Any act of measuring what's going on at those distances will inevitably produce particle and antiparticle pairs. Now that's one of the general consequences of quantum field theory, putting relativity and quantum mechanics together. There are other consequences, and there's actually there's a completely well-defined mathematical framework for how to put the two of these things together. Okay? And really, when I said yesterday that a lot of the development of physics in the 70 years after relativity and quantum mechanics was conservative, it was conservative in the sense of more and more deeply understanding this marvelous structure called quantum field theory, which turned out to have incredible layers of depth and complexity and ability, richness, ability to describe nature in surprising and subtle ways that took all that time to sort out. And we're still not done understanding it. We're still not done fully appreciating it, all of its properties. But as far as describing the world is concerned, these developments culminated in the 1970s with the invention of a very specific quantum field theory that does describe all the known interactions that we know, together with the way they interact with all the matter, everything down to distances of 10 to the minus 16 centimeters. It's a spectacularly successful theory that's given the highly overly modest name of the standard model of particle physics. If it was, that's because, well, if it was today, this would be the most super duper awesomest theory of all time, but people hyped things less back then. But I cannot overemphasize how important it is that this theory exists. Okay? There is not, I mean, the situation is really, really different than it was 100 years ago. 100 years ago, before relativity and quantum mechanics and quantum field theory, there were basic questions about the world. Why is this table hard? Why is water wet? Okay? We didn't have answers to those questions. You know, forget deep philosophical questions about. We didn't have answers to basic questions about what the world around us looked like. Quantum mechanics and relativity and their full glorious generalization into the standard model leaves any question about everyday world completely answered. Okay? There's nothing, of course, it can be complicated systems, it can be hard to work out the equations, but there's no, that's it. Okay? We know everything we need to know to talk about the physics of the everyday, where the everyday goes down to nuclear distances, down to subnuclear distances. And not only do we know how to describe that, but we also understand what we don't know very, very well. So what the actual frontier is is very sharply defined in a way that was simply not true 100 years ago, where there are so many questions left unanswered that it was a really different situation. This is it's a great achievement. And it's a very successful, quantitatively successful physical theory. For example, if you take this picture that you have these particles popping in and out of the vacuum all the time around the electron, then one consequence that it has, if you imagine these particles popping in and out, the electron in the middle has some electric charge, and it will attract a little bit the positrons, repel a little bit these other electrons. And that has the effect that if you're really, really, really far away from the electron, you will measure some value for its effective electric charge. But as you go closer and closer in, you're sort of penetrating this cloud of electrons and positrons. And you're seeing more and more of this unshielded value of the charge. Okay? So this phenomenon is a lot like what happens, well, it's called vacuum polarization. And it's really something you can calculate precisely. You can calculate precisely that while at very large distances compared to 10 to the minus 11 centimeters, it turns out, the strength of the electric charge is basically constant, is this number 1 over 137. As you start going to shorter distances and you start seeing these electron-positron pairs, the strength really goes up gradually. It's very gradually. It goes up logarithmically. But it goes up. It's a measurable effect. People have measured it. In fact, you can take the effects of these virtual particles into account in a very precise way. And use it to predict all sorts of other things. This is the most famous example, and it's an example that owes a lot to work done here at Cornell. The electron has magnetic properties. It has a little spin. The reason why magnets work is because the electrons are spinning around, and they all have individually little magnetic fields that pile up. But precisely how magnetic it is something that you can actually compute. And there is some standard value you might expect. In some units, it doesn't matter what it is. It would be 1 or 2. But there are some deviations that you would expect from the presence of these cloud of particles. And this is the number. Okay? 001159652181 ... And you'll notice that I didn't put whether that's an experimental number or a theoretical number, because those numbers are actually the same. Experiment and theory agree to this 11 decimal places. And that's, so this isn't airy-fairy stuff. Okay? You do there's a whole machinery that tells you how to do this, and it works. I don't think we've ever had a prediction in science that's good to 11 decimal places. But in a sense, much more important than the fact that we can do these very quantitative predictions is that for the first time, this theory, this standard model, has allowed us to see that all these different forces that we talked about, while we don't yet see them really precisely as different aspects of literally the same thing, for the first time, we see that they're described in exactly the same language, exactly the same rubric, exactly the same words, exactly the same formulas. For the first time, it becomes possible to entertain the idea that they're actually, in a sharp way, different aspects of the same thing. Okay? All of these forces, all of them, are associated with little stick figures like this that tell you how particles of matter, electrons, neutrinos, quarks, interact with other particles that transmit forces. So electrons interact with photons. That's where electromagnetism comes from. Electrons and things called neutrinos interact with other kinds of particles called W particles. This is where weak interactions come from. The proton turns out to be made of things called quarks and gluons, as we'll review in a second. But we fundamentally have interactions between quarks and gluons. It turns out that gluons can self-interact with each other. Photons can't. Electrons and gravitons have the same kind of interaction. Gravitons can interact with each other. But you'll notice it's the same thing, the same 3 stick figures, always 3, okay? And you just have to, each one of these things is associated with a very sharp formula, and all you have to do is put these things together in all possible ways, and you get you get specific rules for how to predict, in principle, anything. So, for example, if you want to collide 2 electrons, as Feynman taught us how to think about things in this way, then you put this stick figure together with another one like that and get a process that has 2 electrons coming in and 2 2 electrons going out. If you want to have 2 electrons making an electron and an anti-electron annihilating and making a muon and an anti-muon, then you draw these pictures together and you put them together in other ways. But that's it. There's just these little, there are these little twiggy stick figures, and you put them together in all possible ways, and that tells you everything that can happen and gives you a rule for computing it. This is the really important point. Those forces, as I described them, couldn't have looked more different from each other. Okay? There was gravity, electromagnetism. At least both gravity and electromagnetism were associated with things that looked like inverse square laws, but they look in detail very different. Then, of course, the weak and the nuclear forces look utterly different completely than the other ones, right? But it turns out that that's just an illusion. It's a long-distance illusion. At short enough distances, they look identical. Just as you'd be led to expect from this picture. There's nothing really different. Everything is the same, 3 stick figures put together all the time. Okay? There's nothing really different. So let's see how it works. So, for example, there is an interaction between, let's see what I mean by long-distance illusion. We know that if I have 2, this stick figure interaction is associated with electromagnetism, and I know one consequence of that is if I put an electron here in space, there's an electric field that goes out forever, I can measure it far away, and so on. Okay? So that's an immediate consequence of that stick figure. Whatever it means, even if you don't know what it means, one thing it must do is give you electric fields if you put an electron there. Great, I'm saying that quarks and gluons have the identical stick figure. So how could it possibly be? Because no one has seen such a thing as a quark sitting there with its gluon electric fields coming out. If you had seen it, we would have studied it in high school. Okay? We haven't seen it. How come we haven't seen it? Actually, it turns out to be for a remarkably malicious reason. Well, it's malicious for some people. For other people, it gets them a Nobel Prize. It turns out that it's actually basically true. It's basically true that if you popped a quark down, it would have some gluon electric fields coming out of it. And if you were to look at nature at very short distances, much shorter than 10 to the minus 14 centimeters, which is around the size of a proton, that's more or less what it would look like. But again, there's constantly these things are constantly being surrounded by a cloud of virtual particles around them. Okay? And it just turns out that because of this funny feature that gluons can self-interact, but photons can't, that this screening phenomenon I was mentioning to you earlier, remember the electric charge gradually gets stronger as you go to shorter and shorter distances because you penetrate this cloud and you see more and more of this sort of bare charge of the electron? It turns out that there's just the opposite sign of this effect. Okay? If I could explain it in 5 minutes, Gross, Wolchak, and Pulitzer would not have won the Nobel Prize for it. But it's true. It's just, and it's basically exactly the same calculation. You don't do, it's not all that different. It's basically the same setup, basically the same question. You turn the same crank, but you get a different answer. Just the sign is different. It's still slow, it's still gradual, it's still logarithmic. At very short distances, okay, it's different, the sign is different, but you don't care all that much. However, as you go to longer distances, the fact that this is anti-screening means that the strength of this interaction grows and grows and grows. Remember, for electromagnetism, it was like 1 over 137. Here, let's say it starts off at 1 over 10. Okay? But it grows and grows and grows and grows, and it eventually becomes really strong somewhere. If you give it long enough, it becomes really strong. It turns out it becomes really strong at 10 to the minus 14 centimeters. 10 to the minus 14, and that's the reason why protons and neutrons are the size of 10 to the minus 14 centimeters. If you looked inside a proton and a neutron, you would see a proton would be made of 2 up quarks and a down quark surrounded by a sea of gluons. Okay? We can't pull any of them out of the proton just because these interact, I mean, at short distances, shorter than 10 to the minus 14 centimeters, no problem. If you shoot a light beam to see what happens to it, and you shoot it with high enough energy, so it's probing what's going on at 10 to the minus 16 centimeters, what's going on would look exactly as if the light beam came in and hit a happy quark that was wandering along and bounced off. It would look just like there was a quark sitting there and it had its gluon electric field and all that stuff. Okay? But you can't separate them, you can't see them because it's a long distance property. Just this accidental fact about this minus sign means that the quarks and gluons are permanently bound up. Inside the proton and the neutron. Similarly, let's draw this stick figure. So the stick figure that we had for electromagnetism had another consequence. There was a long-range force, electric force, between two electrons. Okay? If I scatter two electrons off each other, if I go to arbitrarily large distances, there's some scattering. They repel each other. It doesn't matter how far apart they are. Okay? And that's associated with this picture. You should think of this picture as doing the following thing. These little stick figure pictures are taking advantage of the quantum uncertainty. What they're really doing is saying this electron can come along, but because there's this quantum uncertainty and the quantum fluctuations all the time, there's some chance that it can emit a photon. Okay? It's not a real photon because I'm borrowing from the uncertainty principle. Okay? So if I wait long enough, if I don't pay attention long enough, okay, I can have borrowed the photon and then it disappears, and I look again at a sufficiently large distance, and there's some scattering that was mediated by that borrowed photon. But because the photon is massless, I can go to arbitrarily large distances and get some effect from it. Of course, the effect gets weaker and weaker. That's fine. The force gets weaker and weaker. It goes like the inverse square law. In fact, it gets just as weak as you would expect from this borrowing picture. However, it turns out that the W particle, its only difference from the photon is that it has a mass. It's not massless. It has a mass. And its typical size is around 10 to the minus 16 centimeters. So it looks exactly the same, but because we happen to have been stuck for 2,000 years at distances large compared to 10 to the minus 16 centimeters, it looks radically different. Okay? But at short enough distances, it's the same. So these apparent huge differences are a long-distance illusion of something that at short enough distances is really identical. The structure is identical. I have to say that this is why we do high-energy physics. This is why we do particle physics. You know, it's hard, it's expensive, but we do it not capriciously. We do it for this reason. Often, this part of physics is described as the desire for understanding the fundamental building blocks of matter. And that may be the motivation for some people, but I don't think it's the motivation for most of us. After all, it could be Russian dolls all the way down. That's really not why I'm interested. There's this whole zoo and cacophony of particles. You know, who cares about them? Or there are all these other interesting things to explain in the world around us. The reason we do it, the reason we go to short distances, is this hard-earned lesson that the fundamental beauty, unity, and simplicity of the laws of nature is revealed at short distances. We would never have been able to see that the fact that there's really one thing going on here that's masked at long distances. We see it at short distances. What we're interested in is the laws. We don't care that much about the particles. The particles are like the alphabet. The laws are the novel. We're interested that the particles tell us something about the laws. It's the laws that we're interested in. And it's the structure of the laws that are becoming so similar and so unified as we start studying them at shorter distances. I want to make a final comment. Oops. That's a little bit reversed. Let me do this first. So you don't need to understand anything about this other than just to see that it exists. Okay. So I've told you about some of the particles that are out there: up quarks, down quarks, electrons. I don't want to go through the names of every single one of them. Okay. Partially, I'm a little bit embarrassed because some of them have silly names like charm and strange, because some of these things were invented in the 60s and 70s. Okay? But it's also really not that important. Okay? What is important is that there is a very specific menu of particles that we've seen in nature. Again, it has a separation between the matter particles and the particles that carry and transmit force. The things that carry and transmit force are associated with a very specific sort of mathematical structure called Yang-Mills theories. Doesn't matter, but we know what we're doing. Okay? We know how to compute them. We know what the rules are. So the gluons that I talked before are associated with one factor of the group. The W's in the photon are associated with another two factors. And these, we have quarks, we have leptons, like the electrons, muons, neutrinos, and so on. And it turns out we have 3 groups of them. There are 3 so-called families. So the ones that are familiar are one of the families, but there are 2 other ones. And in any case, this is just a table of how each one of these things interacts with each one of the other guys. Right? It looks a little bit complicated, but that's just life. That's true. This menu tells you exactly which stick figures to draw. Okay? So different possible menus, you would draw different stick figures, and then you would turn on the machinery. You would turn the crank, you would make all sorts of predictions, but you have to give a menu. Who's the matter, who are the forces, who is in a stick figure interaction with who. Now, I told you that to all these forces, strong, weak, electromagnetism, they all look similar, they have the similar sort of laws. What are the strengths of the interactions? The strengths of the electromagnetic interaction, remember, that was interesting. It was a pure number. It's around 1 over 137. The strength of this weak interaction is around 1 over 60. The strength of the strong interaction is around 1/10. Remember, these numbers aren't absolute. They change slowly as you go to different distances. Okay? But this is at around a distance of 10 to the minus 16 centimeters where we measure it. You see, not only are the mathematical laws very, very similar, the actual numerical values aren't all that different from each other. This is really a long way to come from Newton, where he said, oh, wouldn't it be great if gravity was a 1 over r squared law? But it could have been a 1 over r point 2.1, and you wouldn't have blinked. We can't do that. We can't monkey with anything. Okay? We have extremely rigid set of rules, and a very, very few parameters that we can adjust. Actually, in this theory, there's, depending on how you count, between 19 and 26 parameters, like these, dimensionless numbers that we can adjust. That's it. That's still a reasonably large number of parameters, but it's way smaller than infinity. Okay? And again, there really seems to be some essential unity behind it. Okay. There's one basic problem which is left. So this theory is supposed to answer any question you might want to ask about the particles and the forces, and the one basic problem that's left is understanding the origin, at least of the masses of some of the particles, like the electron, or the W particle, why the weak interaction is short range. And I wish I could give you a better answer, a better description of of how this physics works. I've thought about it a long time, and I've never managed to come up with a good explanation for a more general audience. This is the best that I and many other people can do, but you're going to complain right away. Okay? So, but let me say the words. So the words are that the way to think about where the mass of the electron comes from is that somehow the universe is filled with a condensate of some sort of field, kind of substance. Immediately you say, aha, isn't that just like the ether, you idiot? Right? And the best I can say is, it's a kind of condensate that's not like the ether. It looks the same to every observer, okay? So don't give me a hard time. But what happens is that as the electron moves along, it actually bumps into this condensate at regular intervals. And that's what gives it its mass. Otherwise it would zip around at the speed of light. Okay? Again, at short enough distances, everything looks basically massless, okay? Because these interactions haven't taken place yet. But at long enough distances, they will look like they appear to have mass. There are other particles that have a bigger, strong interaction with, like those W particles and other things called top quarks and Z particles. They're sort of banging into it all the time. For very good reasons, it turns out that the photon doesn't interact with it at all, so it just sails through, which is why it's exactly massless. So that's where mass comes from this constant interaction with this condensate that's everywhere in the universe, but that's not like the ether. Okay? Now, the typical length scale between these collisions is around 10 to the minus 17 centimeters. You remember I told you that 10 to the minus 17 centimeters number was actually a number in nature. It was a natural number. It's like 10 to the minus 33 centimeters was the strength of gravitational interaction. This 10 to the minus 17 centimeters is a number that tells you how far electrons and top quarks and W's and so on move before they bang into this condensate that gives them their inertia. Okay. So it's an important length scale. It was an important length scale 3,000 years ago. It'll be an important length scale 10 million years from now. But we happen to be living in the era where we're about to go there. And it's interesting that we're about to do these experiments at the Large Hadron Collider, but I won't control exactly those distances. Now, one thing that simply must happen is when we excite things at 10 to the minus 17 centimeters, when we excite them at those scales, no matter what we do, we have to put some ripple in this condensate, whose typical size is around 10 to the minus 17 centimeters. Okay? Now, a ripple in this condensate is putting some energy in it, and that energy is going to come out in the form of particles. These ripple excitations of this condensate is what's called the Higgs particle. And this is one thing that's essentially guaranteed to show up at the LHC. The Higgs particle, or something like it, must show up at the LHC. I've bid years of salary on this. And unfortunately, I've done it in public enough that at this point I'm getting weekly emails from people around the world asking to take me up on it. But it's really an unfair bet because it's really precisely the statement the Higgs or something like it must show up. Something like it has a very specific meaning. But let me just say that if the Higgs or something like it doesn't show up, then quantum mechanics is wrong. Okay? It isn't something that's in this theory, maybe not another theory. It's just that really something like it must show up. And we'll talk about that at greater length on Friday. All right. Let's see. I've run out of time. All right, I think I'll keep going for. Okay, you can vote with your feet, but I won't go on too much longer. I don't have that many more meaningful transparencies. The other thing that I wanted to talk about, it was slightly ambitious to try to talk about both particle physics and cosmology in my lecture, but let me give it a brief go. Actually, we'll be returning to some of these themes on tomorrow. So if it goes by a little fast now, we'll do it again today. So everything that we're talking about now was focused on the physics of the very, very small. I'm now going to switch gears to tell you about the physics of the enormous, the entire universe. Okay? As you'll see in a second, these two kinds of physics are intimately related to each other. And they're, surprisingly perhaps, they're intimately related to each other because the universe is expanding, which has the corollary we'll come to in a second. Okay? Now, the universe is expanding, it's a fact. And as I mentioned yesterday, the statement the universe is expanding is really the statement that space is being invented all the time at some rate. Okay? So imagine that here's 3 galaxies, these 3 red galaxies. After some time, the universe doubles in size. What that really means is that just more space is invented everywhere. Just make, I just put an extra square everywhere between everything, and I double it in size. Okay? But you see, this has an interesting consequence. The distance between that distance used to be 1 unit, now it's 2 units. Okay? That distance used to be 2 units, now it's 4 units. Okay? And this all happened after some fixed amount of time. Let's say, I don't know, after 5 billion years. Okay? So that means that if you're sitting on top of this guy, you would think that that guy is moving away from you, right? How fast is it moving away from you? Well, it's moving 1 cell per 5 billion years. Okay? What about this guy? You'd think that guy is also moving away from you. Okay? But it now has moved even further away, so its velocity away from you is even bigger. So there's a very basic prediction of this picture that no matter who you sit on top of, because space is expanding at a uniform rate, you will see everybody else moving away from you, and the further and further away things are, the faster and faster they'll be moving away from you, with a linear relationship. Okay? There is no center, because anyone would come to this conclusion, and it's a consequence of the fact that it's not expanding into anything, but just that space is being invented at a uniform rate. Okay, so that means that if you plotted the relative velocity as a function of distance, you would find that that these more and more distant objects would lie on the straight line, so the velocity would be some constant times d, and the distance. So this doubling time you can call the so-called Hubble time, and it would be the inverse of that parameter h. Okay? So that's a basic fact about an expanding universe. This is how Hubble deduced that the universe is expanding, by seeing that. And I should say that one of the reasons it gained such immediate acceptance amongst many, many theoretical physicists is that the expanding universe is an instant, immediate consequence of Einstein's theory of gravity. Okay? It's such a natural consequence that Einstein should have predicted himself. It's another instance of theories being smarter than theorists, okay? Which happens very often with good theories, and unfortunately not often enough with bad theorists. It's a prediction that was so dramatic, Einstein refused to make it. Just like Dirac refused to predict antiparticles, even though it was correct. Okay? So it's so natural for the universe to be expanding. It was great. Oh, thank goodness it's expanding. General relativity is correct. Of course it's expanding. That should have been and was the attitude. Now, the rate at which it's expanding, this doubling time, has to do with the actual content of the universe, what energy and mass there is in the universe. Okay? And there's a very simple formula you can derive for it. We won't need it in too much detail. But it says that this parameter that gives the doubling time, or its inverse of the doubling time squared, it has to do with gravity, curvature of the universe, so it has to know about G Newton. And gravity talks to energy, and in this case you can't be talking about the total energy of the universe. Things are accelerating or expanding here, so it has to do with the energy per unit volume, what you might call the energy density. But anyway, this is a formula that tells you the rate at which things are expanding as a function of the energy density. Now, we know the universe is expanding now. If we run it backwards in time, that means that the universe was smaller before. Again, smaller doesn't mean that it was a smaller ball. It just means there was less of it. Okay? That there was less of this space had been generated between all these points. But that means that everything was closer together before, and this density was higher before. So that means that the rate at which it's doubling in size hasn't been constant forever. In fact, the rate at which it was growing in size was bigger before and is smaller now. Okay? Just to have a number in mind, the rough energy density of the universe today is around 10 to the minus 3 electron volt per millimeter cubed. It's a minuscule, minuscule, minuscule number. It's roughly speaking the energy, well, the energy in this radiation that fills the universe that we'll talk about in a second. Now, so we know that as we go earlier in time, the universe is getting smaller and smaller. Everything that's around us is going to get closer and closer. They're going to start banging into each other more and more. It's going to start heating up more and more. And if we extrapolate earlier in time, we come to the realization that if you go somewhere before around the age of the universe now minus 100,000 years, or 100,000 years after the Big Bang, I haven't said the word Big Bang yet, that's why I didn't want to say that. But at early enough times, everything is a dense soup of particles. Okay? As we go to early and earlier times, it just gets hotter and hotter and hotter. Now, if we extrapolate it very, very, very far back in time, then we hit something called the Big Bang that we can't extrapolate beyond. But what people call the Big Bang theory really has nothing to do with the Big Bang part of it. We have no idea what happened to the Big Bang. That'll be part of the theme of tomorrow. We don't even know if the question is sensible. When we say the Big Bang theory, we really mean the aftermath of the Big Bang theory. We really mean that we're talking about the fact that the universe was once very hot and very dense. Now, it turns out that we have incredibly good evidence that that was true. And that's because if you imagine that the universe gets hot and dense enough, then various nuclear reactions would have taken place early in the universe that would have produced the nuclei of lots of the elements that we see around us. Helium, lithium, beryllium, okay? These nuclei, and you can actually calculate how many helium nuclei, how many beryllium nuclei, how many lithium nuclei would you get out of these hot early nuclear reactions when the universe was so very, very hot that these reactions were allowed to go. But the universe cooled, and then these reactions stopped, so you're left with some particular prediction for the abundance of helium, lithium, beryllium, and so on. Those predictions are all dead right.
to a few percent accuracy each. So there's sort of 5 or 6 predictions accurate at the few percent accuracy level each that give us very strong evidence that really the universe was once hot, dense, smaller, and all of this happened. So, and of course, it's nice that, again, it's an immediate consequence of general relativity, so it's a good thing that it's true. Okay. So early on, the universe was hot and dense. This is why the physics of the very small relates to the physics of the very big, because our entire universe early on was also very small. And the physics there involved very, very high energies. And because of the fact that we can pop particles in and out of the vacuum, if we have high enough energies, as we go to earlier and earlier times, and things get hotter and hotter, all the particles and forces and everything that are out there are going to play a role. It just gets smaller and smaller, hotter and hotter, everything that's out there can be made and understood. Now what happened if we run the picture forward in time is that in this hot, dense soup, even photons couldn't move very far before they banged into something else. So you shouldn't have the picture of the early Big Bang. You couldn't see anything if you were there. The light from your eye would just immediately get absorbed by something else along the way. But around 100,000 years after the Big Bang, the universe became dilute enough that light could just stream freely. And the rest of the matter became trapped up in atoms. And so you would expect to see then some of the remnants from this time, around 100,000 years after the Big Bang, when the light finally streamed freely, would arrive and hit us on the Earth. So that's a very direct prediction of this Big Bang idea, that we should see in every direction of space around us, we should see that there was some remnant, some photons that, at some temperature. And you can even predict the temperature ahead of time. This is the famous cosmic microwave background radiation that was indeed dutifully observed and found. But this is another prediction which is correct. Okay, now, just a few more things and I will stop. One of the really remarkable things about this microwave background radiation is that the temperature, you can measure it with an antenna. You point it that way, you point it that way, you point it that way. The temperature is basically the same everywhere. No matter where you point it, the temperature is the same. Okay. So it's very, very uniform. Actually, people discovered that with much more precise measurements, that there are tiny, tiny non-uniformities in the temperature. The scale of the non-uniformities is around 1 part in 100,000. Okay? So there was some difference in the temperature here and there and there and there, which are around 1 part in 100,000. That tells you something very interesting about this early period. It says that in this early period, mostly everything was very uniform, but there were tiny inhomogeneities of 1 part in 100,000 here, there. Okay? Those inhomogeneities is where we came from. Because if the universe was totally perfectly homogeneous, then there's no reason for anything to clump. We're very clumpy. But where did this clumpiness come from? It came from this underlying 1 part in 100,000 difference between here and there. How is that possible? It's because there was this 1 part in 100,000 difference. The universe eventually cooled. But the fact that there was this 1 part in 100,000 difference meant that there was 1 part in 100,000 more mass over there than over there. Okay? And that's all gravity needs to take over. Even if it's 1 part in 100,000 more gravity here, it'll gradually start collapsing right around here. Just a little bit more mass here than over there, but they'll attract each other more, and that 1 part in 100,000 starts amplifying here. Then you're left with a little empty space here. And over there, that part starts collapsing. And so this 1 part in 100,000 grows and grows and grows, and turns into protogalaxies, turns into galaxies, turns into solar systems, turns into us. So these 1 part in 100,000 differences between the temperature there, and everywhere is where all the structure of the universe came from. Now, it turns out that, forget about this 1 part in 100,000, in the standard picture of the Big Bang, if we assume that all you had was this hot soup going back earlier and earlier in time, we understand Einstein's equations and all the physics perfectly, we can run all the equations, And we find the following paradox, or people found the following paradox, that it seems very hard to explain why it is that that part and that part and that part of the sky are at the same temperature. So this is something I'm not telling you why, I'm just telling you the fact that, if we imagine again drawing a space-time diagram going all the way back to the Big Bang, which I'm representing here as that scary place, okay? That if that's a spot on the sky over there, and that's a spot on the sky over there, you can trace back in time all the places earlier in time that could have possibly affected that region and that region. They'd have to be inside these 45-degree lines. But there's simply no way for these things to overlap each other before the Big Bang is reached. That just turns out to be, again, I'm unfortunately not explaining it. I'm not telling you, deriving it for you. But it turns out to be true. The standard Big Bang picture, what that means is that that part of the universe and that part of the universe were actually never causally connected to each other. No signal could have possibly transmitted information from one side to the other. You see how different this is than the picture of the Big Bang, meaning everything comes out of a point, right? Because if everything came out of a point, obviously everything is talking to everything else. It's not like that. It's the whole universe that's shrinking everywhere, losing space as we go back in time. And it's just doing it at just such a rate that it's impossible for information from over here to go over there. So that just makes it a real puzzle. How come they're all at exactly the same temperature? No physical mechanism could communicate between them to say that they're the same temperature. So everything else I've told you about cosmology is rock solid. This is speculation, but it's as close to it's the closest we have to rock solid speculation in physics today. Okay? And that's the idea of inflation. That actually something different happened than just this hot soup going back in time. And that very early in time, there was a period where the universe expanded at a ridiculous exponential rate. Very, very fast exponential rate. You should think of it as taking a really tiny region of space and blowing it up to be the entire universe, essentially. Okay. And it turns out that in the space-time picture, it effectively gives you way more time for things to come into causal contact and completely solves this problem. But it does so by making things expand vastly faster than we normally thought. In fact, expanded at an exponential rate. Well, we'll talk about this whole phenomenon more tomorrow. But anyway, so you should think that the even more modern view of the Big Bang is there something happened in the Big Bang. Who knows what that is? I was going to say God knows what that is, and then there was this period of incredibly rapid exponential expansion, and then the universe became hot, and we have the standard aftermath of the Big Bang that we're talking about before. This picture has, the reason I was going through this was just to tell you this truly remarkable punchline, because it's one of the most amazing things in all of science today, which is that this picture gives us, not only explains why it is that that part of the sky and that part of the sky should have basically the same temperature, but it also tells you why they should have slightly different temperatures. And the reason is that during inflation, just like at every other time, there's quantum fluctuations constantly. Okay? Now, normally there's quantum fluctuations in this room, but as we've said over and over again, they sort of average out as you go to large enough distances and you don't see them. And even in cosmology, even though the universe is expanding, it's normally expanding at a slow enough rate that those fluctuations cancel out. You don't see them in large distances. But when you make the universe inflate, when you make it expand exponentially, the following remarkable thing happens. That if early on, during inflation, there are some fluctuations, just fluctuations in space, these quantum fluctuations, inflation takes those fluctuations and it doesn't let them cancel out. It actually blows them up and makes them macroscopic. These underlying quantum fluctuations are amplified by inflation to become these macroscopic fluctuations that are exactly this 10 to the minus 5 difference in the temperature here, there, and everywhere. If inflation is correct, you and I are here because of quantum mechanics, in a very direct sense. And the initial conditions for the universe question, what determined them, what gave rise to us precisely, ultimately has the answer of quantum uncertainty and quantum indeterminism. I told you before, this indeterminism wasn't all bad. It gave us stability of matter, it gave us all the way the world is the way it is. It gives us a standard model, it gives us everything else. This gives us, okay? The origin of all structure in this picture of the world is quantum fluctuations that are spread out by inflation. Okay, there's a variety of other things to discuss, but I won't discuss them now. I'll discuss them, there'll be appropriate places to discuss them later. But so let me just end and remind you what we'll be talking about in the next couple of lectures. So that's a snapshot of our pictures of particle physics and cosmology. And the next two lectures will be devoted to the various discontents. We will talk about the difficulty of quantum gravity, why we have to jettison space-time when we discuss physics at the Planck length, and we will talk on Thursday about the mystery of why there's any macroscopic universe. Thank you very much, and sorry to go.
Before I open up the floor for questions, just two historical comments. So those little stick figures that Nima referred to, those are actually invented in this building.
Yes, they were. Yes, they were.
And inflation, I lose the positive here, but it's
and yet another thing, perhaps the most, it won't occur to you that this is the most important thing in this talk, but the actually most important thing, it didn't occur to you because, oh my goodness, I forgot, yes. Well, actually, let me tell you. No, it turns out, as a truly, boy, I feel terrible. This is the most important slide in the entire talk. It's actually extremely important. Those poor guys are leaving. They're not going to hear the part of this thing, remember I told you that these basic things are these stick figures, right? You might ask, why aren't there other more complicated things? Why can't I have stick figures with 4, 5, 17 things coming out, right? These are all these other stick figures. Right? If we could have that would be very bad. If all those things were important, then we're not going to be able to explain anything, right? We have to know about what all these different stick figures mean. There would be no notion of some simplest, most important set of which everything else is a consequence. Okay? But really, remarkably, that does not happen. This is maybe the biggest insight into the nature of quantum field theory that people had since its conception. And these were ideas that Ken Wilson and Fisher and friends developed here. And that's the point that in fact, at any given energy scale or length scale that you want to talk about physics, there is a fixed number of particles you could be talking about and a completely fixed number of interactions you should be talking about. There aren't zillions of interactions. There's only a fixed number. There's a very finite, small number of relevant interactions. And the reason really has to do, once again, with the uncertainty principle. All of these pictures I told you have to do with some probability of a quantum fluctuation occurring, right? Those fluctuations are getting bigger and bigger at shorter and shorter distances, smaller and smaller at longer and longer distances. Okay? That means that is the chance that there's a quantum fluctuation involving 3 particles, 2 electrons and one photon. Right? There has to be some fluctuation that did that. I told you that strength turns out to be a dimensionless number, 1/137. That's an extremely special fact that's only true for these tree-stick interactions. It's a little bit intuitive. Let's say I had 2 electrons and 4 photons coming out. Well, for that to happen, 4 photons have to fluctuate with the electron in the same spot. That's now quite a lot of quantum fluctuations to have to all have occur in the same spot in order to make that interaction happen. Those fluctuations are getting bigger and bigger at shorter distances, but they're getting smaller and smaller at longer distances. So that means that the strength of that interaction cannot just be a pure number. It actually gets weaker at longer distances. There is some interaction associated with that. Okay, such a thing could be there, but it has a length scale associated with it. So whatever it is, it's not important at sufficiently long distances. long here can mean, short compared to anything we care about, but from the point of view of fundamental physics, at any given energy scale, you only have to ever talk about a small number of dimensionless interactions. And what they are always the same ones, always the stick figures. You just have to provide the menu. And that's it. You may encounter new things as you go to shorter and shorter distances, but those new things will have their own stick figures. This separation of the possible interactions between the ones that matter and the irrelevant ones that don't is a very big conceptual, was a very big conceptual breakthrough. It gave us this idea that all the theories that we're talking about are effective theories, and they can be replaced by other theories as we go to shorter and shorter distances. But that's very important because it means that this is why there's only 19 parameters, 19 or 26 parameters. So that number comes from a very simple rule. You take the menu, you draw all the possible stick figures, and you count how many of them you have. That's it. Okay? But as I mentioned, it's shockingly different than Newton, who could have had any continuous power you wanted for the force law. 1 over r squared, 1 over r to the 2.001. They're all equally good. Right? Now, all of our uncertainty about what the next scale of what's happening to the next scale of physics is encoded in these very small number of parameters, and that's a very, very important insight. Thank you so much for allowing me to. Okay, on the excuse of giving Cornell credit.
Another thing that you could have mentioned that we've done here was the theory behind the T-2.
I did say that. Yes.
Okay, so I also wanted to remind the audience that the bars are no longer used as the standard of length. They actually have switched to natural.
I know. but meters, right? Well, meters were historically involved. But yes, indeed, for some reason, people are now defining, right? Yes, all is correct. But right, but it shows how silly it is, right? because we could just be working with natural units for everything and not have to define the meter to be some number of wavelengths of some color of light, which I don't remember. But yes, historically it was a bar in a class jar in Paris. How is it defined now? Actually, I don't even know.
Standard of time, instead of light being 2.9979248.
Right.
It just fixes it to your number.
Right.
And then you define length in terms of the standard of time, more accurate to measure. So it is a natural unit of length.
Thank you.
That's next question.
Yes. Yes. Yes, that's actually very, very important. So that was a very yes. The question was that I said that some of these nuclei, like helium and lithium and beryllium and so on, came out of the Big Bang. But the question was, don't they also come out of supernovae? I mean, this is the story that we all hear. We are made of stardust, stuff like that, right? Actually, this is the reason why. It's the reason why everything is in principle synthesized early in the Big Bang, because there's sort of less and less and less of the heavier and heavier nuclei. And this is why you only make the predictions from things like helium, lithium, beryllium, and so on. These much lighter nuclei are less likely to come from supernovae because they burn through heavier and heavier and heavier nuclei. They get down to iron, then everything explodes out. But it's harder to get these lighter nuclei out of supernovae. Now, it's not impossible. It's now impossible. I mean, when people were first thinking about this, there was a possibility that the people who liked the steady state model of the universe and not the Big Bang tried as hard as they could to make sun and supernova and stuff like that generate the light nuclei. But it's very hard. And of course, the other thing you can do is try to go as far away as you can from obvious places that could have been contaminated by supernovae going off and things like that. So you can see what the actual primordial abundance was. And now there's extremely good evidence. There's actually completely primordial helium, lithium, and so on. So those are the things that you actually, you really make sure that they can't have come from superposition.
Carl.
If I could go back to what you told us about yesterday about decoherence, you described how the macroscopic world interferes and ruins the quantum phases. But I was thinking all night about the problem of a superconductor, like a big piece of lead.
Absolutely. Right.
Why does that escape your argument?
Because the interactions are small. I mean, that's actually the whole point. That's really the whole point. And because, right. The whole point is that the distinction between quantum and classical isn't between big and small. It's between open and closed. And you can have big things that are very quantum mechanical as long as you prevent the interaction with the environment that would cause the loss of coherence. So make superconductors cold. Superfluids or closed condensates, which also helps. So you have tons and tons of particles in exactly the same state. This is why coherent states of light, the classical wave interference is quantum interference of those coherent states. Classical waves are the quantum probabilities for the photons. They're not being decoherent again. They're in a nice coherent state. They have weak enough interactions with anything else. They move coherently, and as you know very well, if you take big buckyballs and you make them cold enough and you shield the interaction with the environment enough, then you would see the same thing. So it's really the distinction between open and closed, not big and small. Big and small allows the classical world to even be possible, allows those states to be possible. But you need something else. You need the decoherence, not to have all the other kinds of states. And conversely, without decoherence, even big things can be quantum.
Last question.
Correct me if I'm wrong, but for example, what you said, is it true that because of the nature of weak and strong interactions, and we actually do have the free atoms forever?
Yes. Well, I mean, you can go up a little further.
Okay, so I think we have taken a good time to stop, and we will continue tomorrow at 5 o'clock. Thank you.
I must say that, is this on? Yeah. I must say that from the moment I met Maxime, it was clear he was going to be a big shot professor at a big shot university one day. But I have to say it's still it's a particular pleasure to be introduced by him, and thank you very much for your kind words. And I have really been enjoying reading your papers from 10 years ago, which were really beautiful papers. It's only too bad 5 people were working on it at the time. So I'm going to be talking about a dramatic subject today, which is the end of space-time and what we're going to do without it, or how are we going to deal with the fact that we have to replace it with something else. This is the first of the set of lectures which are really explicitly devoted to questions we don't have complete answers to. That was the point, right? It's the future of fundamental physics. So I will start by telling you what the major issues are and the really significant progress that has happened in theoretical physics in the last 15 years, taking a very major step on getting a good part of the answer for at least what it might look like. But I will really end by telling you what I think the central conceptual challenges in our field are today that we just don't have good answers for. And I'll tell you what some of the strategies and attempts are for proceeding. So that'll happen towards the end of the lecture, and we'll also dovetail in parts with tomorrow's lecture. But we're now starting to go into uncharted territory. Okay. All right, so let's go back to the picture of the scales that we think about in this part of physics a lot. And today is really all about, it's at least going to begin to be all about what's happening near this Planck length of 10 to the minus 33 centimeters, where, as we've said a number of times, the effects of quantum mechanics and gravity become important, and space-time is doomed. So I told you already one understanding of what that 10 to the minus 33 centimeters scale is. Yesterday we saw that in the appropriate natural units, the Newton constant that controls the strength of gravity is roughly 10 to the minus 33 centimeters squared. And the fact that it was such a tiny number compared to any other length scale that we are used to talking about is simply a reflection of the extreme weakness of gravity relative to the other forces. I want to open this up in a little more detail and actually tell you what would happen if we took a pair of electrons and actually looked at the force between them as we brought them closer and closer and closer, okay? So we get a more physical feeling for what's happening at the Planck length. So imagine that we have this pair of electrons at very large distances apart from each other. At those very large distances, there's a gravitational attraction between them, there's an electric repulsion between them, and as we said yesterday, the electric repulsion is 10 to the 42 times stronger than the gravitational attraction. And you've all learned in school that, that both the electric force law and the gravitational force law go like 1 over the distance squared. So it would look like no matter what distance you put them from each other, that ratio would always be 10 to the minus 42. Gravity would always be way, way weaker than the electric force. That's true until you get to distances that are comparable to around 10 to the minus 11 centimeters. 10 to the minus 11 centimeters is the length scale associated with the mass of the electron. What that means is when you start trying to put two electrons much closer to each other than 10 to the minus 11 centimeters, then the uncertainty principle forces the electrons to have some kinetic energy, right? I'm putting them closer and closer together, so they have to have some uncertainty in their momentum. So they have to have more and more energy. But at around 10 to the minus 11 centimeters is the first time when that amount of kinetic energy they have starts becoming comparable to their mc squared energy. Okay? So it's starting to affect the amount of actual mass that's in the system at around 10 to the minus 11 centimeters. As you start pushing them closer and closer together, you have to supply more and more energy in that region of space to hold them closer and closer together, again by the uncertainty principle. And because gravity talks to mass, the gravitational force is proportional to the mass of the two bodies, you start seeing that the strength of the gravitational force starts going up. Simply the mere fact of holding them so close together is forcing so much mass into that little region that the gravitational force starts taking off, starts getting bigger. The electric force, remember, its strength was this dimensionless number, around 1 over 137. Okay? Very gradually varying with distance, but we're going to ignore that. But the gravitational force starts taking off and getting stronger and stronger. And what happens is that it actually gets stronger and stronger and stronger. And at some point, actually around 10 to the minus 31 centimeters, if we kept extrapolating, it would cross the electromagnetic force. It would become as strong as electromagnetism, around 10 to the minus 31. At that point, that'd still be both relatively weak forces. That number, 1 over 137, is a kind of small number. The strength is kind of small. But at that point, it's caught up with electromagnetism. And if we keep on going a little further, at around 10 to the minus 33 centimeters, we find it's just massively strong. Okay? Absolutely massively strong. So that's one way of talking about this Planck length. In the neighborhood of the Planck length is where gravity catches up in strength with all the other forces. That actually happens a little bit earlier than this Planck length, at around 10 to the minus 31 centimeters. At this 10 to the minus 33, it's just the strongest thing around by far, dominating everything in sight. Okay. Of course, that distance is vastly smaller than anything we've seen. Our highest energy accelerator is going to go to 10 to the minus 17 centimeters. That's 16 orders of magnitude smaller, larger in length than the Planck length. But still, we can, in our mind's eye, do this extrapolation, and that's what's happening around the Planck length. Okay, another very important thing about what's happening at the Planck length, and this is really the little thought experiment that tells you that space and time just don't make sense, is the following. You remember we learned, because of the uncertainty principle, that we can't know the position and the velocity of a particle at the same time. But that's okay. We can understand and probe physics at any distance we like, perfectly compatible with the laws of quantum mechanics, so long as we're willing to add more and more energy. Okay, so if I want to probe things at shorter and shorter distances, I just have to pump more and more energy into the smaller and smaller region of space in order to see what's going on there. Again, as I've mentioned already, that's why we build these giant particle accelerators. They have to be so big to accelerate particles to such high energies, ironically, to probe very, very small distances. And that's just a direct reflection of the uncertainty principle. So for a long time, that just works. You just keep going to shorter, 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 shorter distances. But something new happens at some point. At some point, you put so much energy into such a tiny region of space that there's so much mass by E equals mc squared in that region that you collapse the region into a black hole. You are trying to figure out what's going on inside this region of space by doing experiments at higher and higher energies, but the mere fact of doing the experiment by the uncertainty principle puts so much energy into the region you're trying to look at that you collapse it into a black hole. And you can't get any information out. So you defeated your own purpose. You were trying to understand what's going on at 10 to the minus 33 at very short scales, and it stops working. It stops working when those distances you're probing at around 10 to the minus 33 centimeters, the times are 10 to the minus 43 seconds, and so on. What if you say, damn, that's not what I wanted to happen. Let me build an even higher energy accelerator. Let me build an even more powerful microscope. What would happen? You make an even bigger black hole. It gets even worse, right? If you wanted to probe what was going on at 10 to the minus 31 centimeters, okay, that would be okay. You could do it with a very, very high energy accelerator. But you go to even higher energies, you make a little black hole. You go to even higher energies than that, you can't even know what's going on at 10 to the minus 31 centimeters anymore. That's being collapsed into a black hole. Okay? So this means that there's simply no operational way of measuring or probing physics in any way at distances and time smaller than 10 to the minus 33 centimeters, 10 to the minus 43 seconds. Okay? Now, at this point, you could take two attitudes. One of them is that space and time actually do exist. They're there. It's just we can't measure it. Everything we've learned in the history of physics says that that's a very reactionary attitude. And every quantity that we haven't managed to associate with something that can in principle be observed, that's telling us something very important. It's telling us that that quantity actually doesn't exist. Okay? There's no such thing as space-time at arbitrarily short scales. Something has to give. Now, at this point, let me dispense with one very naive idea that you might have. This naive idea is the basis of a number of other research directions, but it's really naive nonetheless. So I don't want to spend a lot of time talking about it, but let's just mention it. You might say, oh, I know what's going on. What's going on is that there's some kind of atoms of space-time, right? It's just like in this table. If I look at the table at shorter and shorter distances, of course it doesn't look like a table anymore. I start seeing that it's made up out of other stuff. That's what's going on. It'll be just like before. It's so exciting. It's atoms of space-time, okay? You get down to very short distances, maybe you see some kind of lattice. Maybe there's some sort of discrete structure. There's little cells whose size is of order of the Planck length, something like that. Okay? Now, if you think about it one more second, there's a big problem with that idea. And that big problem is, in whose reference frame is the size of the lattice 10 to the minus 33 centimeters? If it's in 10 to the minus 33 centimeters in my reference frame, someone else's reference frame, it could be a lot longer. Someone else's reference frame, it could be a lot shorter. It's very difficult to come up with this idea because of relativity, because of special relativity. It's very difficult to come up with an idea of discreteness in space-time in any way consistent with the laws of special relativity. And indeed, all the people who pursue this idea are perfectly happy to abandon special relativity, and they do. Okay? But another lesson I think we've learned over and over in the history of physics is that things don't progress. Things progress by making things more and more and more restrictive in a tighter and tighter straitjacket. Not that all of a sudden there's anarchy and all rules, all bets are off and everything changes. Okay? So I'm not going to talk about atoms of space-time, and essentially it's because it's in flagrant contradiction with the laws of special relativity. We will see instead what sort of thing can replace it. And when you see the sort of thing that can replace it, completely consistent with the laws of special relativity, and you see how subtle and interesting it is, you will really appreciate even more deeply what's wrong with the idea of atoms of space-time. Okay, I want to say one other thing. Often this problem of this set of problems is associated with the words of making sense of quantum gravity, which makes sense, right? We are putting together this issue arose precisely because of quantum mechanics and general relativity said in the same sentence. Quantum mechanics forces the uncertainty principle, more and more energy, smaller and smaller region, gravity turns it into a black hole. Okay? So it's quantum mechanics and gravity. So it's really the problem of putting quantum mechanics and gravity together. But often, especially in popular expositions, you'll find statements like, our difficulty is that we don't know how to put together general relativity, which is a theory of the very big, with quantum mechanics, which is a theory of the very small. Okay? And this is really overly simplistic. In fact, we have no difficulty talking about quantum gravity at large distances compared to the Planck length. Okay? The real difficulty is we don't know what happens when gravity gets strong and all these fluctuations are gigantic at the Planck length. But at very large distances, there's no difficulty at all talking about quantum mechanics and gravity. In fact, people have calculated, well, let me get to that. People have calculated what the first correction to Newton's laws is due to quantum mechanics. There it is. Okay, it's GMM over R squared. You've seen that. This 1 minus 27 over 2 pi squared G. There's an H bar. There's a C. It's a quantum gravity correction to Newton's laws. Okay? There's a 27. So someone has actually done some work. Okay? Okay? And I want to emphasize, you can really calculate this. It's an honest quantum gravity calculation. It's a tiny effect no one gives a damn about. Okay? It's a minuscule, minuscule effect. But you can calculate it. It's something in principle you could measure at very large distances. Our difficulties are not saying the words quantum mechanics and gravity in the same sentence. It would be absurd if that was our difficulty, right? I mean, after all, we drop atoms in gravitational fields. We can do quantum mechanics and gravity, no problem. Okay? So our difficulty is that we don't know what's going on at very short distances when these quantum gravitational fluctuations become very large. We can calculate this so reliably because it's small, but we can calculate it. Okay? So the difficulty all has to do with what's going on at the Planck length. Now, where else are these issues important? These issues hit you in the face in a variety of situations. For example, we talked about this idea of the Big Bang. So we go back, the universe gets smaller and smaller. At some point, the curvatures in the universe become comparable to the Planck length. Okay? When that happens, we simply don't know what's going on. Often people ask the question, what came before the Big Bang? Well, the real answer to the question is, before we get to the Big Bang, we hit a situation where we don't know what time and space mean anymore. So the whole notion of before probably ceases to make sense. Okay? It's one of the lessons we've learned again and again. Questions you can phrase in the English language are not necessarily good questions about the universe. And this is a good example of it. The whole notion of space and time is breaking down in the neighborhood of the Big Bang. We don't even know if before makes sense. We don't know if space makes sense. Okay? Something is going on there, but to understand it, we have to come to grips with these issues. So that's one situation. Another situation is what happens in the center of a black hole. In the center of the black hole, all mass is getting crunched down to arbitrarily high densities until it hits the Planck scale, and then we don't know what's going on again. Okay? Incidentally, I'm sorry to draw this picture in this way. This is a very misleading representation of what happens. There is no center of a black hole in the sense that you fall in, and then there's like a sinkhole somewhere, and you're like, oh no, but you get sucked towards it. Okay? Really, the singularity inside of the black hole is a moment in time. When you fall behind the horizon of the black hole, what happens is no matter what you do, no matter how you struggle, you hit the singularity and go kaput. Okay? But it's not some point in space. But anyway, I will sometimes abuse, it's not artistic license, I guess. It's scientific license, which is much worse. But draw it as a point. Okay? But anyway, we don't know what's happening there. This is not, it's a situation where the laws we have, our theories just break down. They're just telling us we don't know. They throw up their hands. They beg for mercy. We don't know what's going on there. Okay? That's the sort of question we'd like to have an answer to. When the theories you have, you push them to their limits and they beg for mercy, that's the time you know that you're asking a good question and that something has got to give, and so we have to figure out what's going on. Okay. Now, there's another aspect to this, which also goes a little distance to showing you that there's something more subtle going on than some sort of discreteness in space-time. And this is it's a more refined and a more subtle point, but it's a very deep point about putting quantum mechanics and gravity together. Remember, something we learned about quantum mechanics is you've got to be very careful what actual observations make sense, right? What is it that actually has sharp meaning? And in quantum mechanics, we found out that the world isn't deterministic, it was probabilistic, and the things that have sharp meaning, ultimately, are doing an experiment infinitely many times with an infinitely big apparatus. Okay? That was a conclusion that we came to yesterday. So there was two infinities implicit in the discussion of any perfectly sharply defined quantity in a quantum mechanical theory. Do the experiment infinitely often with an infinitely big apparatus. When we add gravity, something bad happens. When we add gravity, one of those infinities is taken away from us. Let's say I want to know what's going on. I want to do some observation of some system in this room, okay? Of course, we know we can do it. We can get the errors to be very small, smaller than anyone would care about. But let's say you're a really hard-nosed person. You want to get that error down to 0, right? Get a really sharp measurement. So you start making the apparatus bigger and bigger and bigger. You have to do that, right? But as you make the apparatus bigger and bigger, it becomes heavier and heavier. And at some point, the apparatus becomes so heavy that it collapses the room into a black hole. All of our problems are with these damn black holes, as we'll come back to in a second, okay? But this is devastating, right? Because it means that if you want to do any sharply defined, any sharp measurement in a fixed size room, it's just impossible. So, but that's what we talk about when we're talking about doing measurements in space and time. I do the measurement here, I do the measurement there, I do it in a fixed size room, I write down the answers on my piece of paper. None of those things will ever converge to something perfectly sharply defined. So we saw already that quantum mechanics implied a drastic reduction in what we could actually talk about relative to classical physics. And now combining quantum mechanics to gravity seems to be even further drastically reducing what we can talk about. We can't sharply talk about any measurement done in any fixed size room. What can we possibly do? What can possibly make sense? Well, the slogan is that the quantities that do make sense in a theory of gravity are observables that are not in the inside of the space-time, but are at the edges of the space-time, at the boundaries of the space-time, far away at infinity. Let me give you a simple example of what one of these observables can be. Let's say I take a big measuring apparatus, right? And I just make it bigger and bigger and bigger and bigger, as big as I like, but I start moving it further and further and further away from the regime where something is going to happen. Okay, that's fine. This apparatus is huge here. It's not going to make a black hole over there. Let me have it shoot out a particle. So this apparatus shoots out a particle. Another really one shoots out a particle there. Another big one shoots out a particle there. We let the particles come in. The particles merrily collide with each other. They do whatever they do. They go back out. And they're measured by really big apparatuses very far apart away from each other. They're not going to collapse anybody into a black hole. Everyone's fine. Okay? So that's an experiment that I could do infinitely many times with an infinitely big apparatus and get an exact result. But it doesn't involve an experiment, merrily in the inside of the space-time. You've got to get out to the edges of space-time and throw things in from infinity and see what happens when things go back out to infinity. Okay? These things are called scattering experiments for obvious reasons. Okay? So these sort of scattering experiments could yield perfectly defined observables. But they don't involve the inside of the space. I mean, the actual observation doesn't involve the inside of the space-time. The way you might want to think about how it takes place might involve the words that the particles come in, they hit each other here, and they go back out. But the ultimate thing you observed is not located inside of the space-time, but far away at infinity, at the boundary of the space-time. Okay. Now, since all of our difficulties here, in one way or another, stemmed from these black holes, let's just pause for a second to say a few words about them, because some of their properties are going to be important for the rest of the discussion. So black holes, even in classical physics, caused people some consternation when they started thinking about them. It's interesting that I think I told you that Einstein refused his prediction of the expanding universe. He refused to believe that his theory predicted an expanding universe. It did. He also refused to believe that his theory predicted black holes, which it does. Okay? He tried as hard as he could to make these solutions go away because they were very confusing. But they don't go away. They're perfectly good solutions. In fact, they're one of the most dramatic solutions of general relativity, where it flexes its muscles and shows how different it is from Newtonian physics. Okay? But one of the difficulties with them is, as we've discussed, there are regions of space-time where you can't ever get information back from them, right? You can throw something into a black hole and it's gone. Goodbye. That was disturbing for a variety of reasons. One thing that bothered people is it seemed that, like, black holes might allow you to violate some very well-established laws of physics. For example, there's something I won't have time to explain in detail, but I'm sure you've all heard about, that this idea of entropy. Entropy always increases. Okay? There's this thing called the second law of thermodynamics. Entropy increases. Entropy is a measure of the disorder in a system. And the total disorder in the universe is just increasing. Okay? So black holes seem to give you a way to get around this. Because you could take some region of disorder, just throw it into the black hole. Oh, that's nice. Things are much more ordered now. Okay? It's just in the black hole. It's okay. Right? So that was a little bit strange. So that was one puzzling thing. But people also noticed other interesting things about black holes, also puzzling. For example, people noticed that if you had one black hole and another black hole, if they merged, well, it makes sense that they make a bigger black hole. Okay? But they noticed that something more specific was true, that if you merge two black holes together, the new black hole, the area of the black hole, would be bigger than the sum of the areas of the two black holes that made it up. All right? That was just again, this is just facts about classical black hole physics. This fact, coupled with this strange feature that you seem to be able to lose entropy into a black hole, started this vague and then sharpened feeling in the early 70s that it actually makes sense to ascribe entropy to a black hole. Okay? And what should its entropy be? Whatever it is, it makes sense. It should probably be proportional to its area, because its area is a thing that always increases because of this fact. Okay? So there started to be this idea that black holes should have an entropy, and it was somehow proportional to the area. People weren't quite sure what the constant of proportionality should be, but that black holes, in some sense, had an entropy. Now, this was an idea that, amongst other people, Stephen Hawking found ridiculous. He found it ridiculous because he thought, well, normally things that have entropy, they have a lot of disorder, and things that have disorder are hot. So if the black hole is going to have an entropy, it had better be hot. In other words, it had better be emitting radiation constantly. But every idiot knows that black holes are black. They don't emit radiation constantly. Except he found out that they do, because of quantum mechanics. Okay? So black holes are, in fact, hot. This picture of a classical black hole as just nothingness is just wrong, quantum mechanically. And roughly speaking, what's going on is this. It's again a consequence of these pairs of particles that can pop in and out of the vacuum all the time, right? Remember, the horizon of a black hole is this point of no return. If you're on one side of it, you always get sucked into the black hole. On the other side, you have a chance to escape. Now imagine that you're a poor particle and antiparticle pair that had the misfortune to pop out of the vacuum right in the neighborhood of the horizon. Your friend who popped out on the other side is just gone. Okay? You have a chance to escape out to infinity. But this process of the particles and antiparticles popping in and out of the vacuum right in the neighborhood of the horizon gives rise to a phenomenon that particles come streaming out of the black hole. Okay? And of course, total energy is conserved, so the black hole will gradually start losing mass. Okay? So Hawking set up and did this calculation, tour de force, brilliant calculation, and he found that not only does it emit radiation, but it emits radiation exactly as if it had a finite temperature, like a perfect black body
what we call in physics a perfect black body, but really it's the beautiful, perfect, it has exactly the properties that you need to ascribe it an entropy. And the entropy you should ascribe it is indeed the area of the black hole, but he also figured out precisely what the constant of proportionality is. Constant of proportionality is 1 over 4 times g Newton. Remember, g Newton in these natural units had units of length squared, so the area over g Newton is indeed a number. It's a pure number, which is the entropy. Okay? So quantum mechanically, what happens is you make black holes and they evaporate. Okay? They evaporate by giving off this Hawking radiation and getting smaller and smaller. Now, after Hawking realized this, he realized something else. And he found this, made this extremely interesting thought experiment, whose resolution had to wait 20 years, but which I'll now describe, which really drove a lot of thinking in this field. So here's the thought experiment. Let's take one of these experiments that we even said we're legally allowed to do, that are even a real observable. I'm going to send things in from infinity, I'm going to collide them with each other and see what comes out. Okay? But now let's send so much stuff in. I'm just going to aim a whole bunch of laser beams in just the right spot, so I put so much energy into that region, I make a big black hole. Big, fat black hole. Okay? Now, I make this big, fat black hole. Now, by the way, so let's say I did that, and right after I did that, I decided to get rid of my laptop, some books, okay? Just for the heck of it, right? Just, my latest enemy, just chuck them in towards the black hole too, all right? So there's an awful lot of things there in the black hole now. There's lots of information about my laptop, my former friend, okay? Okay, great. So now what happens? Okay, we made this big black hole. The black hole starts to radiate. At first it's big, and so it's radiating relatively low energy radiation. I should have mentioned before that the temperature of the Hawking radiation is around 1 over the size of the black hole. Okay? Again, 1 over the size of the black hole in natural units. So it's pretty cold, but it's still radiating. For a macroscopic black hole, it's so cold that we can't actually see it. For an astrophysical black hole that's out there in the center of the galaxy, this radiation is so cold that we can't see it, but it's there, and it's big for microscopic black holes. Anyway, so then it shrinks in size after it's given off a lot of energy, and then now it's smaller, so it's giving off blue light, higher energy, then really gets really small, and then poof, just disappears. That's what Hawking said. It's just gone now. Now I have all of this light streaming out. But at every step, this black hole was radiating as if it was just perfect black body. In other words, the way the black hole radiates, it doesn't care at all where the black hole came from. If it's a black hole, the way it radiates is always the same. So you make a black hole, and what comes out, apparently, that's what Hawking's calculation said, bears no memory whatsoever of what it took to make that black hole. You could make that black hole by aiming these laser beams. You could do it by aiming other laser beams. You could throw in your friend, not throw in your friend. Doesn't matter. If you make the same black hole, it'll radiate in exactly the same way. What comes out will look exactly the same. Okay? So that was the puzzle. The puzzle was that it seems like you can lose information. That what happens at the end, knowing what happens at the end, we can't reconstruct in principle what happened in the beginning. Okay? Now, of course, you might say, but isn't that true? Haven't you just told me in quantum mechanics nothing is deterministic, et cetera, et cetera? That's true. So what I really mean is that we would have to do the experiment not with just one black hole. We'd have to do this experiment infinitely often, make infinitely many black holes, do the experiment the same way every time. But ultimately, there are some quantities that we can extract, right? There are these sharply defined quantities that we can extract. And in principle, those quantities we can use to back reconstruct in the usual formulation of quantum mechanics. From that final information, we can fully reconstruct what the initial information was. Okay? What the initial information of the initial state vector, if you like. The initial state, the initial wave function, completely determines the final wave function, and vice versa. Okay? And yet, this calculation seemed to say that that doesn't happen. Now, this is a beautiful example of
one of the things I told you about in the very first lecture, that we never know in physics ahead of time whether the thing to do is to be radical or conservative, and it's not even often obvious which is which, okay? So let me tell you what Hawking's attitude was. Hawking took what seemed like a very radical attitude. He said, this is great. This means that quantum mechanics is wrong, and I just proved it. Okay? Other people found this very hard to swallow, partially because it was very hard to see how you could modify quantum mechanics in any way that was consistent with very basic principles. Okay? So there was a real impasse. What do you do with this paradox? That's a real contradiction. Either quantum mechanics is wrong, or somehow the information gets out. Either way, something is wrong. Okay? So Hawking had what sounded like the radical attitude, but there was a smaller group of, at first, apparently curmudgeonly physicists who were like, no, we can't just throw out quantum mechanics like that. It's the most spectacular, successful theory of all time. Somehow, quantum mechanics has got to be right. And this calculation has got to be wrong. Okay? And that's how it stood for many years until the problem was finally resolved. Okay? Well, we'll see what the resolution looks like, but the answer is that indeed, quantum mechanics is right. Hawking's calculation was very, very, very subtly wrong. Okay? But in fact, the nature of the answer that we're going to see in some ways is much more radical and involves really remarkable new ideas. Okay? We'll see what it takes for quantum mechanics to be right. For quantum mechanics to be right really needed the end of space-time. Okay? And we'll see in a very specific sense how that comes about and how quantum mechanics manages, normal theories manage to do it. And I think by the end, you'll get a sense for how remarkable the picture that's emerged has been. Okay, well, there are many of these qualitative puzzles. There are also other quantitative puzzles, and people started trying to make sense of putting quantum mechanics and gravity together. And the most ambitious and successful of these ideas has been related to string theory. Now, one could give a whole series of lectures on string theory alone, which I'm not going to do, and I'm only going to focus in this lecture on its aspects that are really specifically relevant to this problem of quantum mechanics and gravity. There are other aspects to this whole program that I could unify all the forces and give us a consistent picture of everything and all that stuff. Let's put that aside. I'll talk about that to some extent tomorrow. But let's just talk about its initial raison d'etre, which was to come up with a consistent way of putting quantum mechanics and gravity together. So here's very roughly the way the story works. I want to tell you the story the way string theorists thought about string theory before 1995, and the way string theory is described in popular books in 2010, which is that the whole big idea here is that we're replacing particles with strings. Okay? Instead of having point particles, we have little loops of string. Those little loops of string are around 10 to the minus 31 centimeters big, not 10 to the minus 33. Okay? They're around 10 to the minus 31 centimeters big. Remember that 10 to the minus 31 centimeters was around the distance at which electromagnetism and gravity became comparable. Okay? So the strings are actually a little bigger than the Planck length. This is very important. It's an important part of what makes the theory tractable. Okay? And the idea is that, okay, so we don't have points. We have these little loops of string. And an advantage of having them be big like this is that those little microscopic black holes can't eat them up. They're bigger than the black hole is. Okay? So you can start imagining scattering these particles together, these strings together, seeing what happens. You could hit these Planckian energies, and now things aren't necessarily going haywire. Okay? I should say that you say, why stop here? Why not have it be something else? Not little loops of strings, little loops of membranes or something else. We'll come to that in a second. But there was a very good reason people were excited about strings. This is a sort of thing that's harder I mean, it's something you'll just have to take my word for or their word for. But it took a number of miracles for this picture to be mathematically consistent. Anything else is just impossible to make mathematically consistent. It was really remarkable that this even had a prayer. People had talked vaguely about this
going all the way back to the 1940s and 1950s, and no one could make any sense of it. It seemed very hard to imagine that it would make mathematical sense. The fact that it did make mathematical sense in rather surprising and intricate ways was what convinced people that was interesting and on the right track. Anyway, string theory has a variety of consequences I'm not going to spend a lot of time talking about because they're not that relevant for our discussion. They'll be relevant later. One of the things that comes out of it is a really remarkable extension of our notion of space-time associated with the word supersymmetry. There's something that's much less interesting than supersymmetry, but is still there, and that's these ideas of extra dimensions of space. Supersymmetry is really a much more, it's a much deeper and more interesting idea, but extra dimensions come along as well anyway. And there was this picture that we don't see these extra dimensions because they were curled up on these tiny sizes compared to our big macroscopic four-dimensional world. I'm not going to talk about it a lot again because it's not very relevant to our discussion. If we imagine how this picture that you have strings instead of particles impacts our picture of these stick figure interactions we were drawing before, we see that instead of having a stick figure interaction like that, all these particles are replaced by little loops of string, and it looks like something much smoother. Okay, so that had a number of very nice consequences, and people could start doing concrete calculations, and life was good. But there was something hanging over the head of the string theorists, even in the 1980s, where this picture first developed through to the early 90s, which is that eventually they would also have a problem with black holes. Not when the black holes were 10 to the minus 33 centimeters big, but if you collided these particles at high enough energies, the black holes would get bigger and bigger, and they would eventually become 10 to the minus 31 centimeters big and swallow up even the strings. Okay? So there was a problem. It still wasn't completely solving the problem. It was helping you get going. It was a step in the right direction, but there was still something missing. Okay. That was string theory before 1995. After 1995, well, something happened in 1995, evidently. Okay? And after 1995, people realized that, amongst other things, string theory is not a theory of strings. Okay? In fact, we're going to see in a bit that string theory is actually particle physics. But we'll come to that in a moment. It's not a theory of strings. There's all sorts of interesting objects in it. There are strings. There are even point-like particles in the more correct formulation of the theory. And there's even higher dimensional objects, membranes. And these things can all talk to each other. So strings can end on membranes. They can interact with each other in a very interesting way. And another interesting thing that happened is that the actual size that these things ended up needing to have could actually be quite a lot more variable now. The strings could be bigger. The extra dimensions could be bigger. There was just many, many more options that became available. Okay? Again, that's a topic for maybe tomorrow or Friday. But the theoretically most important realization early in this period was that, in fact, this theory that people were talking about and trying to describe in various approximations turned out to be seen to be a single theory. There was one theory, and it wasn't of a variety that we had encountered before in physics. See, normally, we think about classical theories, and we take classical theories, we imagine quantizing classical theories, but we're used to the idea that we have some quantum theory and it has some classical limit. But there's one classical theory and one quantum theory, and they just go hand in hand. Okay? This was the first example of something really rather remarkable and new, which is that there's a single quantum theory, but the single quantum theory turned out to have both many, many different kinds of solutions and also many different kinds of classical limits. So that's very strange. You would take two classical theories that look utterly, completely different and think that surely these theories have nothing to do with each other. Okay, I can make them quantum mechanical. They had nothing to do with each other before. They'll have nothing to do with each other after I make them quantum mechanical. But it's the other way around. There was one quantum theory which turned out to be possible to have several classical limits. Okay? This was a very early surprise that said that there was even more unification going on in this set of ideas than people had realized. Okay? An immediate consequence of all of these ingredients that I told you is that people managed to understand where this entropy of the black holes came from. Remember I told you
that, that Hawking figured out that the black holes have a temperature and they have an entropy. Okay? But remember, we also know that entropy is a measure of the amount of disorder in the system. And if you wanted to really understand where that entropy comes from microscopically, you'd have to understand what the microscopic constituents of whatever you're looking at are, right? The entropy just counts how many different possible ways could you put those microscopic constituents together so they look the same macroscopically. Okay? When you have a bigger entropy, it's made out of more stuff. You can put it together and arrange it in different ways so that it looks the same macroscopically. But if you want to come up with a microscopic, a real deep understanding for where that entropy is coming from, you should be able to actually see what's making it up and just count. How many ways could you put it together so that it looks the same macroscopically? Well, people managed to put all these ingredients, strings and brains together, and understand, not for the sorts of black holes we were talking about a second ago, but cousins of them, very special sorts of black holes that carry both mass and a variety of kinds of electric charge. But for these very special sorts of black holes that also have entropy, people were able to figure out how to count precisely all of those microstates in terms of these strings and the brains. Okay? And roughly speaking, they managed to set up a situation where you could gradually turn a collection of strings and brains into a black hole in such a way that you weren't changing the number of microstates at any point in the process. So you could keep track of every single thing. And so, therefore, you could count the number of states to begin with and then match it to the number, to the entropy of the black hole at the end. They did this calculation, and it came out exactly area over 4g Newton with every pi, every factor of 2, everything perfectly correct. Okay? It wasn't some vague squiggle. This was another tour de force calculation. And big qualitative ideas are very, very important in physics. Concrete, solid calculations that work are also very, very important for telling you that you're on the right track. When something works to every factor of 2 and every factor of pi in this surprising way, you feel like there's something correct about it. Okay? So that was a huge accomplishment of this period. But still, even this calculation didn't address this question of what happened to the information. Okay? I wasn't talking about the sort of black hole that can be made and evaporate. These were very special sorts of black holes that turned out not to evaporate, okay? For reasons I won't explain. One of the reasons that the calculation could be performed. Okay, so another qualitative insight emerged, which started heading in a more radical direction. Okay? So, and this has to do with another remarkable fact about black holes. They have an entropy. In fact, not only do they have an entropy, but if you have some region of space, okay, and if you want to imagine what's the biggest amount of entropy that I can have in that region of space, the biggest amount of entropy you can have in that region of space is if you make it a black hole. Okay? Any smaller amount of entropy, it will not be black. For example, just as a simple example, let's say you take a big hot ball of gas. Big hot ball of gas, okay? And you put so much of it in there that it's just about to collapse into a black hole. Just a second before it's about to collapse into a black hole, you can open up your undergraduate textbooks in thermal physics and calculate the entropy inside that amount of radiation. Then a second later, it collapses into a black hole. But you can ask, what was the entropy just as it was about to collapse? The answer is it's minuscule compared to the final entropy of the black hole. Okay, it's actually proportional to the area over g Newton to the power of 3/4, which if the number is huge, rating the power of 3/4 is vastly, vastly tinier than the final entropy. Okay? So the entropy goes up dramatically when you make a black hole. But the entropy is telling you, at least, is telling you what the maximum number of possible well, it's telling you something about the number of sort of microstates that you can have inside the region, right? Again, the entropy is a count of all the possible ways you could put something together so that it'll look the same from the outside. But if you can't possibly make the entropy bigger than the entropy of the black hole, then that suggests that there's a sort of maximum number of possible different configurations you can have inside. But what is that maximum number of possible configurations? It's the area of the it's the area of the region. in units of the Newton constant, in units of the Planck scale. That's very perplexing. Because normally in physics, if we're talking about the number of possible degrees of, the number of possible different states of air molecules in this room, you would think that that number of states would scale like the volume of the room. If you made the room twice as big, so it was 8 times the volume, well, in every little cell you have exactly the same amount. Everything looks the same. So you would think that everything is, you're increasing by a factor of 8 the total number of possible states you could be talking about, the total number of possible, more technically, the total number of possible degrees of freedom you could be talking about. But that seems to be wrong. It seems like that the maximum number of degrees of freedom that it makes sense to talk about goes like the area of the room. Okay? This is another very important qualitative observation and suggests the following startling picture. That actually, to describe what's going on inside this room, the actual correct physics resides on the boundary of the room. Okay? If you want to think there's little pixels, and the pixels have an area which are little Planckian cells, okay, that in order to describe anything going on in this room, you just cover the boundary of the room finely with these pixels, and little lights go off here and there. Okay? As things move around the room, they're encoded somehow in lights going on and off in the pixels that are on the boundary of the room. Okay? If you put more and more stuff in the room so that it starts getting close to being a black hole, more and more of these pixels are lighting up. If you put so much stuff that it's just about to collapse into the black hole, all the pixels are lit up. Okay? But all the information is at the boundary. It's not inside the volume, it's at the boundary. You see, this is yet another indication of what we saw from our more general arguments about quantum observables. It's not inside the space. It's at infinity. It's far away, or it's at the boundary. It's somewhere else. It's not what you would think. The inside of the space doesn't make sense. What's controlling the physics lives on the boundary of the space. As I said, this was another important qualitative idea. And when I said that the subject made spectacular progress in the last 13 years or so, it's because a completely quantitative and working version of this idea was finally discovered in 1997, which I want to tell you what it is. But by the way, this whole thing, the slogan is that the world is a hologram. Okay? That just like a hologram is really two-dimensional, it looks three-dimensional. It encodes three-dimensional information in a very non-trivial way, right? Holograms were invented by extremely smart people, and they encode the information. They make things look three-dimensional because of lots of interesting correlations between what's going on in the hologram. Okay? But still, it's fundamentally two-dimensional, and it mimics and it fakes a third dimension. But it's really fundamentally two-dimensional. So similarly, that's the idea. Quantum mechanics and gravity force the world to really be like a hologram. Okay, so now I want to tell you how this works in an example. So, and the statement is the following. Let's talk about what quantum mechanics and gravity might look like in a world that's not exactly like our world, but could be made so close to it for so many purposes that it certainly suffices for many of the questions we're asking. Okay? The technical name for this world is an anti-de Sitter space. But what it really is some curved space-time. Okay? It is a curved space-time. Our space-time is also a little curved. There's the sun there, there's the earth there, and so on. But on average, it's pretty flat. But this is really a space-time that's sort of uniformly curved everywhere. Okay? There's a uniform, it's uniformly curved everywhere. Of course, even if it's uniformly curved everywhere, if the scale of the curvature is 10 million light years, then I wouldn't notice it in this room. Okay? So it could well work. What I'm telling you could well work to describe a universe that has a curvature that's 10 million light years. Okay? But it is important that it's curved. Now, in this space, once again, the kinds of observables that we want to talk about is you might So The important feature of this curvature turns out to be, and we'll talk about what this geometry looks like a little bit more, but the important point turns out to be that there's really naturally a boundary in this space. There's naturally a boundary in this space-time. But the boundary of that space-time is just like a normal 3+1 dimensional universe. Okay? The boundary is just flat 3+1 dimensional space. In that case, the interior would be a 5-dimensional space. So this would be a 5-dimensional theory of gravity on the inside. And it would have a boundary, just like this room is 3-dimensional and the boundary is 2-dimensional. Okay? It would be, it's just like that. Okay? It really looks like a tin can. Okay? It's a universe that looks like a tin can. It has a boundary. It has an inside. And we want to describe how to do physics. If you don't want to imagine a higher dimensional world, we could just do everything else, imagining that it's 4-dimensional inside and the boundary is 2+1 dimensional, literally like that wall, except the wall is at infinity. Okay? And the space has this uniform curvature. Now, in this situation, we can ask again. We sit at this boundary, we send particles in, they bang into each other, they go back out, we make all the measurements, and that's what we should try to hope to predict and understand. That's the problem of figuring out what quantum gravity looks like in this space-time. Okay, so there's an answer to the question. What describes quantum gravity in this d+1 dimensional space? Okay, and if this 4-dimensional quantum gravity on the inside of this tin can, what is the theory? What is a theory that tells you what happens when you scatter all these particles together? The answer is that it's a good old-fashioned quantum field theory of ordinary particles interacting according to the laws of special relativity, just the standard old particle physics sorts of theories that we were talking about yesterday and the day before, which lives on the boundary of that space. Okay? Every single question you might want to ask about what's going on inside is secretly answered by a theory that doesn't have an inside. There is no inside. The theory doesn't even have gravity. The theory doesn't have strings. It's just a relatively boring particle physics theory. It's not all that boring. It's in a range of parameters of such theories that we didn't know how to consider before or didn't know how to study before. When these interaction strengths between the particles become very, very large. But still, it's a theory we could put on the computer. I mean, we know exactly what to do with it. There's no deep mysteries about space-time or fluctuations or anything. It doesn't have gravity. Okay? This is the shocking, startling thing, that we knew that somehow on general grounds, the only observables were associated with things going on at the boundary. But the really remarkable thing is that the theory that computes what those observables are doesn't even have an inside. Okay? It's just a good old-fashioned quantum field theory that lives on the boundary. So there's many slogans. So this deep, mysterious thing is just the same as something that is just an extreme limit of a theory or set of theories written down by people and studied since the 1930s. String theory equals particle physics. Okay? There's no gravity emerges, string emerges, this whole space emerges. But it emerges as from the dynamics of something that we understand much, much better. So it's another example. We'll see how it works in a little more detail. But it's another example of something, of the phenomenon we've seen over and over again. Remember I told you that even when we got to quantum mechanics, wasn't it strange? We lose so much predictivity about the world, right? We can predict so many fewer things that we could in classical physics. And yet, strangely, we find that what was left that we could predict was somehow much more unified than we would have suspected before. The same thing just happened to us, right? We had these thought experiments about gravity. We're like, oh, that's just really terrible. The only things that we can predict are out the boundaries of the space. What about the inside of the space? That's really too bad. And it's true. But we can predict even fewer things, but it allows two things that seem to have nothing to do with each other to be identified. Good old-fashioned particle physics is the same as quantum gravity in one higher dimension. Now, I really want to tell you, this will not go over a long way, but I want to tell you really what this looks like in some detail, because it's pure magic, okay? So first of all, let me tell you a little bit more about this space. As I said, this is a curved space, okay? It's a uniformly curved space, and there's a variety of ways of representing what this curvature looks like, but one of them is like a trumpet, okay? It's like, so this is really a picture of what distances and times look like as you head in towards the middle of the space away from the boundary. This is out towards the boundary, that's going in towards the middle of the space, and as you see, the areas around you are contracting, okay? That has a very interesting consequence, that if you talk about some big region here, which is large compared to the scale of this curvature, the areas and the volumes are proportional to each other. Okay? So that's good because this is going to make it easier for this to satisfy this holographic principle. Because there isn't such a big difference between the area and the volume after all in this highly curved space. Okay? That's one interesting thing. Another fact about it is if I go back to the tin can picture, there is a sort of gravitational this curvature, this warping of the space means that if I put a massive particle off here, somewhere not quite at the boundary, off here somewhere, what it wants to do is just bounce back and forth around the middle. Okay, so it just sloshes back and forth. It's getting gravitationally attracted towards the center of the space. Light, of course, can make it out all the way, and actually can make it all the way out to the boundary and bounce back in a finite time. So it's an infinite amount of distance off to the boundary, but things can get there and come back in a finite time. Okay? I'm just trying to get you to visualize what this space looks like a little bit. Now, how can it possibly be? How can it possibly be that a theory that doesn't have the interior, a theory that just lives on the boundary and only knows of the boundary, how can it possibly be that it describes physics in the middle of the space? For example, how are you going to tell it if a particle is over here or over there or somewhere else? Just something as basic as where is it in this extra direction? What information can encode where it is in the extra dimension, in this extra direction? The answer is lovely. If you put a little point mass here, what corresponds to it in this hologram? What corresponds to it in this boundary? It's just putting a lump of energy that has some size here. So a particle sitting here in the middle of the space corresponds in this other description to a little lump of energy. A particle that's sitting further away towards the middle is a bigger lump of energy. Okay? Even further would be even bigger. So the position in this extra space is the overall scale size in what's going on at the boundary. Okay? Remember, what I'm telling you is that there's a description for everything that's going on inside this tin can where you never have to say there's an inside of the tin can. Okay? You only ever talk about things that are going on the outside. So I have to tell you how to translate everything that makes you think there is an inside of a tin can. I have to tell you how to translate every one of those things into a statement that you can just say on the boundary. And this is one piece of the dictionary. Okay? Being in different positions in the middle just corresponds to having different sizes of lumps of energy. Okay? Now, here's another remarkable thing. So if I take two particles now, two particles out in the middle of the space, they're sitting in the middle of the space, and Newton tells us that they attract each other gravitationally. Okay? Just classical gravitational attraction out in the middle of the space here. How can I possibly include that? That's gravity, right? That's gravity. How am I going to get that if I don't have the middle of the space? The answer is that, okay, you have these two particles, so you have this lump of energy here, and you have a lump of energy there. Do you remember this basic vacuum polarization effect that we talked about a number of times? That when you have some particle sitting here, something else sitting there, that you can affect what's going on in this cloud of virtual particles in its vicinity? Okay? And that we've seen the effects of that a number of times already. Well, in this theory, it turns out that this guy over here affects the virtual cloud around it. That guy affects a virtual cloud around it. And the net effect of this very quantum mechanical process is that there's an attraction between these two lumps of energy. And that attraction is exactly what you would compute from Newton's laws in the interior. Okay? Of course, it's Newton's laws in this curved space, but Newton's laws in this curved space are nothing other than this quantum attraction between these lumps of energy in this boundary description. Okay? So this is really remarkable. A classical force, what you call a classical force on one side, is due to a very highly quantum mechanical process on the other side. Okay? So there's no inside of the space. There's no gravity. Okay? What you have is a theory of nice particles and forces as I said, in a particular regime of its parameters, but which mimics everything that you would like to call gravity and the space and everything on the inside. So I'm just telling you more and more about how to decode this hologram. Okay? More and more about what properties of what's going on at the boundary you should associate with things that are going on in the middle of the space. Okay, something else. What about a black hole sitting in the middle of the space? Okay? A black hole sitting in the middle of the space corresponds to just heating up the entire boundary, just making it a hot fluid, hot soup. Okay? That's great. Hawking radiation, all of those things are just completely obvious. You're just heating everything up. So if you take what's going on in this boundary, you just heat everything up uniformly, then all of that physics is identical to as if you had a black hole sitting in the middle of the space. So this immediately tells you that there can be no information loss. Because let's say I wanted to now model the process, that I take these particles, I send them into the middle of the space, I make a big black hole, I wait that they evaporate, they come back out. In the middle here, everything is riddled about confusions, about quantum mechanics, space, time, all this stuff, right? But we have a completely equivalent description of that process in the boundary. What's that? What does the hologram tell us? The hologram tells us we have two lumps of energy. There's no inside, right? We have two lumps of energy. They're going inside means that these two lumps of energy grow, they hit each other, they make a hot soup of messy interacting stuff that cools down and things go back out. Okay? There's no gravity here. There's no reason for any violation of the laws of quantum mechanics. In fact, the theory is just quantum mechanics and relativity of the sort that I told you about 2 lectures ago. There's in particular no information loss. Okay? So this really just conclusively proves that, that in fact, there was no information loss. Quantum mechanics is valid. But what gave is that this picture of the inside of the space was just not there. There is an equivalent description of what's going on. We did get rid of some of space-time. We at least got rid of the space on the inside. We got rid of gravity on the inside. And there is a completely equivalent description of what's going on in terms of this much more standard physics, but encoded in these very subtle holographic ways. I hope you see now how different this is than atoms of space-time. Okay? So this is something which is much, much more interesting. And it doesn't violate the laws of special relativity. And it doesn't violate the laws of quantum mechanics. Okay. So why are we not happy? Why aren't we done? If I can just take a few more minutes. This is, that was the success. Okay? So why aren't we just done? We're not done because for many questions we are sort of in principle done. Okay? But in fact, there's a very, very important difference between this universe, which we in principle understand very well, and our own universe. This universe was like a static tin can, right? Our universe came from a Big Bang and is expanding. It's not static. It's time dependent, okay? For a long time, it was expanding, 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 and the rate of that expansion was slowing down. People thought for a while that would probably go on forever, and we would eventually just keep decelerating, decelerating, decelerating. The universe would get bigger and bigger and bigger, and eventually it would become infinitely big.
So if you waited long enough in this world, you would see everything that there is. Okay? The light from everything that was ever emitted, you would be able to collect and see what it was in principle. Even this picture of cosmology, by the way, is still restricting us a lot more for the sorts of observables we can talk about. Okay? Because now there is a Big Bang in our past, so we're not free to set up any initial states we want, scatter them any way we want, and so on. Okay? There's even fewer things that we can talk about still, even fewer things. But there are some things we could talk about. If we waited for a long, long time, we could count to see how many red stars there were, how many blue stars there were. We could do that with very, very big apparatuses without collapsing everyone to a black hole and so on. Okay? So there's still something to talk about. But 13 years ago, something very dramatic happened, which is that there was evidence that the universe is actually not decelerating, but just started picking up again. And the rate of expansion, instead of decelerating and slowing down, has started speeding up. And it's speeding up at a constant rate. It's accelerating. And people first noticed this by seeing that when you look at the velocity of these more and more and more distant objects, they first did it with supernovae, that instead of lying on the straight line, it actually went up and up and up and up a little more. So it was getting faster and faster the further and further back you went. Okay? So that was the first evidence. In fact, the experiments that measured it were designed in their design reports. They were designed to measure the deceleration of the universe. And they had to report the negative value for the deceleration, okay? Because they actually saw that it was accelerating. Okay? No one expected that. Now, the fact that it's accelerating is often said to be due to something called dark energy. But in fact, we have a very good idea for what it could be. There's a completely straightforward thing that it could be, which is just a non-zero energy density of just the vacuum. So if the vacuum had a non-zero energy per unit volume, then exactly this phenomenon pops straight out of our standard understanding of general relativity and cosmology. The formula I wrote down yesterday for the rate at which a universe expands, the formula that looked like this, where rho is the energy density of the universe, if you just make rho a constant, which is what you would get if it was just the energy of the vacuum. There's always vacuum there. You can't get rid of it. As the universe gets bigger and bigger, there's always vacuum there. So if that vacuum energy is there, then what would happen is the universe would start doubling in size at a uniform rate. Okay? It would have it would start accelerating in its expansion. So we actually live at an interesting time. Earlier in the history of the universe, it was completely dominated by radiation, photons. It became matter took over from radiation a while ago, 100,000 years after the Big Bang. Back then, the value of the vacuum energy was totally minuscule compared to everything else. But just in the neighborhood of where we are today, all of them are sort of comparable to each other. We're living in a very interesting cosmological times. Okay? So that it was possible to discover these things. But anyway. Now, this means that the deep future of our universe, it will just start doubling in size at a uniform rate. Every 10 billion years or so, it'll double in size. And it won't slow down. It'll just keep doubling in size, double in size, double in size. Okay? That means something. That something that's right now 20 billion light years away from us, let's say it emits a beam of light. Now, okay, we'll never ever see that light. There is a poor piece of light trying to get to us. Okay? This is this guy far away. 10 billion years later, we've doubled in size. The light's moving as fast as it can, okay? It's moving over one cell, but it can't beat the fact that the next time it moves over, we've put, it moves one cell over, we put 2 cells in the middle of it. It moves one cell over, the next doubling size, we put 2 cells in the middle of it. We're just inventing space all the time at such a fast rate that even light can't overtake it, okay? Nothing is moving faster than light. It's just the rate at which space is being invented everywhere is so fast that even light screaming along just can't make it. Okay? So if we can draw a sort of picture like this, that there was a Big Bang, we talked about this period of inflation, we talked about a hot universe,
But in a sense, we're starting to inflate again now. We're accelerating. We're doubling in size at a uniform rate. Okay? We're accelerating again. And light from this guy will just never reach us. Okay? Just never, ever reach us. So that means that this is what the universe will look like in a long time. Okay? In 100 billion years or so, there will just be me. Well, not just me, but me and, me and all of us in our galaxy. Okay? Me and all of us in our galaxy, which are being held together gravitationally. We're not being ripped apart by this expansion of the universe. We're being held together. But we'd be sitting there. Everything else around us is getting sucked away. Everything else around us is getting pulled apart from us away by this accelerated expansion. Okay, so we'd be lonely sitting there in our galaxy, looking out. We wouldn't see any other galaxies anymore. Okay? In fact, even this thermal microwave background radiation that we talked about before, even most of that would be stretched out and gone. This would be a very bad time to be a cosmologist. Okay? It would be very hard to convince people that there was a Big Bang. They would say, well, sure looks like we rule the universe. Here we are. We're all alone, right? I don't see any cosmic microwave background. They say, no, you don't understand. It was there. It started accelerating and inflating away. Yeah, right, sure, right? So this is a particularly good time to be doing cosmology because it'll start getting harder pretty soon. But it means something very startling. There are regions of space that we'll never see again. Okay? There is something out there, the light from out there we'll never see again. What we see out there basically today is what we're ever going to see. If this picture of the accelerated expansion is correct, we're never going to see more. In particular, we'll never see an infinite amount of anything. We don't have an infinite amount of material out of which to build detectors. Okay? We can't separate things from each other arbitrarily in order to minimize the interaction they have with each other. Okay? On top of all of that, the situation is really quite analogous to being, roughly analogous to being inside a black hole. Okay? There isn't a singularity that's going to kill us. Well, we'll talk about that tomorrow, but not obviously, not very obviously. But there is this sort of horizon out there, and just like black holes radiate, that horizon also radiates. Now, this temperature is very, very, very low, but there will be radiation coming from, it's really like we're on the inside of a hot tin can. Okay? So the situation is that our future is finite. We don't get access to any more things, and we're furthermore being slowly cooked all the time. Okay? A very low temperature, but slowly cooked all the time. Okay, this is a really severe paradox. Well, I don't know if it's a paradox, but we don't know what we're doing. Okay? Because of quantum mechanics, if I want to make any predictions about what this universe, any sharp predictions in this world, I have to do an experiment. We've heard the mantra now many times, with an infinitely large detector an infinite number of times. I can't do either one of those things in this universe. I can't do it with an infinitely large detector because I don't even have an infinite amount of material. I'm stuck in this finite-sized tin can. And actually, it turns out I can't do it in infinitely many times either because I'm constantly being bombarded all the time by these pesky radiation coming from the horizon, which has got a really low temperature, it's true. But if you're cooked at a uniform rate, even at a very low temperature for 10 to the 120 years, you'll start feeling it. Okay? It'll start interfering with your ability to do the experiment and not have some random fluctuation in your apparatus because of the fact that it's constantly being bombarded. Actually, it turns out to be around 10 to the 120 years, but anyway. But it's a real question. We don't even know what to talk about in such a universe, right? In that other tin can universe that we're talking about, where quantum gravity was the same as quantum field theory, everything was great. Okay, we could talk about these observables on the boundary. We found a theory for them. Everything was fine. But we don't even know what to talk about. But this is what our universe is, not this other imaginary universe. Our universe forces us to come to grips with these issues. All of this is pointing to something, which is that
that previous picture that we talked about that was so wonderfully successful, space emerged, gravity emerged, strings emerged, all of those things happened in a quite magical way. There was one thing that did not emerge. You did not hear me say that time emerged in that picture. That's because time didn't emerge. The time that happened inside the space, things moving along in time, was exactly the same time that happened in this boundary, right? Things moved in time in the boundary. Things also happened in time on the interior. But the two times were the same. We didn't have to abandon the notion of time. We got rid of basically everything else, but we didn't have to abandon the notion of time. And that's clearly the next frontier. Okay? We have to figure out how to get time out of nothing. We figured out how to get gravity, strings, space out of nothing. We have to figure out how to get time out of nothing, and that's really the hardest thing, because physics, if absolutely nothing else, is about talking about things, the relationship between things at one time versus another. So we don't know how to do that. All right, I don't have time to tell you about these other things, but let me just end by saying that, so we've seen that, I hope you've seen space-time is doomed. We have some ideas for what replaces it. There are some beautiful ideas about how space can emerge and gravity can emerge. We have real issues about where time comes from. And tomorrow we're going to pick up the story once again with this accelerating universe, but with a different feature of it that I didn't emphasize at all, which is that if we go back to this realization that our universe is accelerating, I told you there's no problem. We have this energy density of the vacuum. It's that number. Everything is great. Well, tomorrow I will tell you that that number is absolutely insane. Okay? No one in a million years would have predicted that that should have been the energy of the vacuum. Okay? It's a completely insanely tiny number. And understanding where that number could come from is another very major challenge that we'll talk about. And will end up being related to yet other potential extensions of our notion of space-time, including the idea that we're just a small part of a very, very, very vast multiverse. And that we have to figure out what that means on top of everything else. So that's the plan for tomorrow. Thanks a lot.
Okay. So one of the really delightful things about this subject, which I hope you've been getting a sense for in the past number of lectures, is that some of our very, very biggest questions are about incredibly basic things. They're really simple to state. That's a hallmark of very, very good questions in our part of physics. If they're really simple to state, of course, they're not often simple to understand and come up with a solution for. But they often involve incredibly basic properties about our universe. And today, we're going to address one of perhaps the most basic properties of the universe, which is that it's big. Okay? Our universe is big. We are big. The planet's bigger. Galaxies are bigger. Atoms are small. The nucleus of the atom is smaller. The fundamental laws operate on very short distances. So it's an interesting question why there's nonetheless a macroscopic universe. Now, you might think this is not, so this is coming back to the picture of the scales that we've seen a number of times. We're going to try to understand why it is that even though it seems there's something fundamental going on down at length scales of order 10 to the minus 33 centimeters, the Planck length, or some other incredibly short distance scale, that nonetheless we have lots of huge scales relative to that. We have this weak length scale, and we have this gargantuan scale, which is the size of the universe. By the way, there's only about, I can't do the addition in my head, but not so many orders of magnitude between those scales. It's remarkable that so much, all we know about the world actually fits between there and there. Nonetheless, it's going to turn out that it's a really major puzzle why these scales are so far separated from each other. Now, you might think that we understand why something like an elephant is big, or we're big. It's just made out of lots and lots of atoms. So it's not so confusing after all. But if you trace that question back and further back and ask why are there a lot of atoms, why, you end up hitting a number of brick walls. Okay? So we're actually going to start from the brick walls and just explain why it is that it's almost impossible to imagine that there is a macroscopic universe, given what we know about the laws of physics. And that fact suggests a number of radical modification of what physics should look like in order to explain that extremely basic fact about the world. This all goes back, as everything in this series of lectures has done, to quantum mechanics and relativity, the uncertainty principle, antiparticles, and the whole picture that the vacuum is an exciting place. So we've seen this a number of times. If I take my magnifying glass and look at a little region of space and time to see if it's empty, I pop out an electron and a positron pair if I do the magnification powerfully enough. And so everywhere in space, we have this picture of particles and antiparticles popping out, in and out all the time. So the vacuum, far from being an empty, boring place, in this picture where we combine quantum mechanics and relativity, is a very exciting place, is a rich place, and I should say that even though we keep drawing these qualitative pictures of particles popping in and out and so on, there's a hard machinery behind all of this. We can actually figure out what all these things mean precisely. It's exactly this picture of the particles popping in and out of the vacuum that allows us to make these 12 decimal place accurate predictions for specific questions, for example, about the magnetic properties of the electron. Okay, so it isn't all pictures. We're going to be talking about a lot of pictures, but it isn't all pictures. And so there's a piece of this story, there's a piece of these fluctuations coming in and out that it's not only qualitatively correct, it's amazingly quantitatively correct. Okay? So we understand it very, very well. However, there's a big problem riding underneath it. The vacuum isn't just exciting, it's way too exciting. Okay? One aspect of this problem, which we'll begin with, is the fact that even the vacuum has energy. Now, again, this is another basic consequence of quantum mechanics that we remarked on when we were talking about it. If we imagined having a ball hanging from a string, a pendulum, then in classical physics, its minimal energy would be zero. It could be sitting there and sitting at the bottom and standing still. So it would have zero energy, zero potential, zero kinetic energy, zero energy. But in a quantum mechanical world, it's constantly fluctuating. And it actually has a minimum amount of energy of order Planck's constant times the frequency with which that the pendulum would swing. Okay? So that tells you that, that these quantum fluctuations have energy in them. Let's try to make an estimate for how much energy there is, therefore, in the vacuum. All right, so let's make the estimate by looking at, now, since the vacuum looks the same here and there and there and there, whatever kind of energy we're talking about should be the same everywhere. So it's an energy per unit volume. Okay? So we can ask about the energy of the vacuum per unit volume here, or the energy of the vacuum per unit volume there, and we should get some number for that, right? So that's really what we're asking about. Not the total energy, but the energy per unit volume of space. All right, let's do an estimate. So imagine I make my volume some nice big volume. There's some quantum mechanical fluctuation by the uncertainty principle, again, that lives in that volume. Okay, so there's some energy there. Now let's make a more refined measurement. Let's make the volume smaller. Well, the quantum fluctuation in that smaller volume are bigger, right? They have they're associated with much shorter scales, much shorter times, much higher frequencies, and by this basic rule that the amount of energy gets higher as the frequency gets higher, just the energy in those fluctuations is bigger. Okay, so let's make the box even smaller. It gets even bigger. So we have a big problem that as we make the box smaller and smaller, the energy of the fluctuations is getting bigger, the box is getting smaller, so the energy per unit volume is just blowing up like mad. Okay? In fact, naively, the energy per unit volume would be infinity. I would make the box arbitrarily tiny, and the energy per unit volume would be infinity. Now, of course, I can't make the box arbitrarily small. We spent all of yesterday talking about how space-time is doomed. We can't talk about arbitrarily short distances, blah, 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 right? So that means that surely it doesn't make any sense to talk about this box when it gets smaller than the Planck length, okay? So definitely whatever this estimate we're doing is wrong when the box gets close to the Planck length, but it sounds like it should be pretty good somewhere in that neighborhood, okay? So let's just, to get an idea, this quantity, in previous lectures I called rho, the vacuum energy density. I'm giving it a new name for this lecture, which is the name people normally give it. It's called lambda. That's a capital lambda. And its name is the cosmological constant. Okay? So I'll interchangeably say vacuum energy, cosmological constant, big lambda. It's all referring to the same thing, which is the energy density of the vacuum. Okay? So we're now trying to make a good estimate for the energy density of the vacuum. Good theoretical physicists can estimate anything under the sun to a factor of 10. Okay? So we are good theoretical physicists, or in the neighborhood of some. Okay? So let's do it. All right? So we just got a good estimate for it. It's an energy per volume. The energy, if the box is of order the Planck length, is, now it doesn't even matter. We don't need to use units or anything. All the words here are Planck. So it's a Planck energy, a Planck volume. The energy density is Planckian. Okay? That's actually a technically accurate statement. Okay? It's a Planckian energy density. Very good. Okay, so what would that energy density do? Remember, we said yesterday as well that if there was some positive energy density in the vacuum, that it would make the universe double in size at some uniform rate. So it would make the universe accelerate. And we can come up with an estimate for the rate of that acceleration, except we don't even have to remember the formula now, because we know it has to do with gravity. Gravity is associated with the word Planck. The energy density is Planck. So what's the doubling time for the doubling rate of the universe? It's the Planck time. Can't be anything else. Every word in this discussion is Planck, right? Great. So we get a great estimate. We get an energy density of the vacuum. It has a great prediction. The universe should be doubling size every 10 to the minus 43 seconds. Well, that seems very, very wrong. Now, I've mentioned it already yesterday, but I'll emphasize it again today because it's the biggest experimental discovery in our subject in the last 20 years. The universe is accelerating. It is accelerating. We discovered that in 1998. But the rate at which it's doubling is every 10 billion years. It's pretty far from every 10 to the minus 43 seconds. Okay? So you see, often when people talk about the accelerating universe, they say there's some mysterious dark energy that's is driving the expansion of the universe. We don't know what it is. Actually, it's not true. We've known for ages and ages that we can make the universe accelerate. You fall out of bed, you make the universe accelerate. Okay? The problem is that we make this back of the envelope estimate of how fast it should be accelerating, and it should be doubling in size every 10 to the minus 43 seconds, not every 10 to the 10 years. So why did people say that it was such a surprise that the universe is accelerating? That prediction that I just told you, that it's doubling in size every 10 to the minus 43 seconds, was so absurd, so obviously wrong, that all theorists thought that even though normally theorists are good at doing back-of-the-envelope estimates, this was a time when there was something just very big missing. And clearly, if it's off by so humongously much, there must be some very deep principle we have yet to uncover that tells us that, in fact, this vacuum energy is zero, exactly zero. Okay? You can't get it so far off. So we all expected that it would be exactly zero. That's what was so shocking about the accelerating universe. Not that it was accelerating, but that it was accelerating, but at such an incredibly tiny rate. That meant that this value of the vacuum energy wasn't going to be declared to be zero by some angels who saved theoretical physicists. Okay? It was really non-zero, and we'd have to come up with an understanding for why it had the specific value that it has. The specific value that it has, which is around 10 to the minus 3 electron volt per millimeter per millimeter cubed, that specific value is 120 orders of magnitude smaller than what we get from this back-of-the-envelope estimate. Okay? I used to say when I gave talks that that was the biggest error in the history of physics, then I realized there's no reason to smear any other science. I don't think anyone else has screwed up so bad. So I think it's the biggest error in the history of science. By error, I mean the biggest disagreement between a reasonable back-of-the-envelope estimate and the right answer. I assure you, we do not screw up this bad in physics ever, anywhere else, okay? We're used to predicting things to 12 decimal places. So that's why this is such a shocking problem, right? Not to even get within a factor of 10 or 100, to be off by 120 orders of magnitude. Now, I told you we have this spectacularly successful theory. We predict all these things. It's so awesome. So what do we do about this? What do we actually do? I mean, before predicting these detailed properties of the magnetic properties of the electron, we should surely understand why the universe isn't doubling in size every 10 to the minus 43 seconds, right? Well, this is what we actually do. What we do, we say, no, it's fine. Don't worry about it. It's fine. Well, we do worry about it, but this is what we, this is the calculation we do. We say that was indeed some quantum correction to the energy density of the vacuum. We just estimated it. We're very good. We pat ourselves on the back. Great job. We estimated that. Imagine that you do the calculation and it's in Planck units, right? So you get some specific number, 2.6493781, ... goes on forever. You work very hard, okay? So this is a quantum correction. That's this quantum mechanical origin of this vacuum energy. But we say, it just so happened that there was a classical contribution that was sitting there already. What was the size of that classical contribution, you ask? Well, it just happens to be negative 2.6493781, ... and they happen to agree to 120 decimal places and begin to disagree in the 121st decimal place. Okay? That's what we actually do. We're allowed to do it. No one will stop us from doing it. And once we do it, I want to emphasize this, once we do this, everything else works. You know, it's not like this thing feeds in everywhere else and is screwing up every other calculation. It's a set it and forget it thing, okay? You fix it at the start and then everything's fine. But it's really weird. It's very deeply weird. For obvious reasons, this is called fine-tuning. Okay? It's really like you know, taking your finger on a dial and just adjusting things to part in 120 to get something to work. The situation we're in is like walking into a room and seeing a pencil standing on its tip in the middle of a table. Okay? And it's vertical to an accuracy of 10 to the minus 120 degrees. Now, it could be. It's a consistent way the pencil could be. Okay? It's consistent with what we know about physics for the pencil to be within 10 to the minus 120 degrees of vertical. But if you saw something like that, you would probably wonder that something's up, right? You might look for a string hanging from the ceiling, right? Something that explains why it's vertical. You would find very dissatisfying the explanation that, but that's just the way it was. Just accidentally happens to be 10 to the minus 120, okay? That's the explanation we give now. It just accidentally happened to be 10 to the minus 120, okay? So, and this is our current answer to the question, why is the universe big? Since these lectures are being videoed, I'm not sure I should make this remark, but maybe I'll make it anyway. I think it's great that the intelligent designers don't know about this, okay? This is a much, much better argument for intelligent design than anything to do with evolution. I mean, those things are all true, okay? This is a situation where we ourselves don't have an incredibly compelling answer yet. I'm going to tell you about the answers we do have, okay? But, and we take the problem seriously and we think about it and we propose scientific approaches to it. But it's really a major puzzle. It's not like this is not one of those things we understand amazingly well, okay? We don't. It's something we're speculating about. I think it just goes to show the intelligent designers actually don't care about the Big Bang. They don't care about cosmology. They just don't want to be monkeys, okay? Funnily enough, okay. Now, that's the biggest problem. That's the biggest one of these fine-tuning problems. But there's another one. And for this, we have to go back to remembering something about, something I told you about where mass comes from in our understanding of the standard model of particle physics. You remember we had this picture where we said the mass occurs because the electron becomes massive because as it's propagating through space, it keeps bumping into this condensate, which isn't like the ether that fills the universe, right? And it keeps bumping into it, every 10 to the minus 17 centimeters or so. That's why the length scale 10 to the minus 17 centimeters is important. It's actually a property of nature. But that's what it does, okay? So it picks up an inertia because it bumps into it every 10 to the minus 17 centimeters or so. Now, every single thing in the universe is quantum fluctuating at tiny distances. It's the same argument over and over again. We'll all start getting bored, okay? So this condensate is fluctuating. It has huge fluctuations. It doesn't want to be uniform on the scale of 10 to the minus 17 centimeters. This is the whole problem. Quantum fluctuations are big. They get bigger and bigger at shorter and shorter distances. Nonetheless, we have a universe that seems to have correlations across much, much, much larger distances than that, okay? So really what this condensate wants to do is fluctuate like hell. And the electron wants to fluctuate like hell. So the electron would want to be enormously heavier than what we actually see it to be. It would want to be 16 orders of magnitude heavier than we see it to be. Because these fluctuations want to be, this typical distance wants to be 10 to the minus 33 centimeters, not 10 to the minus 17 centimeters. Now, that's evidently also not what the world looks like. If that is what the world looked like, you and I would all be black holes, okay? We'd be so massive, the constituents that make up the atom, everything would get so much more massive than they are now, that the strength of gravity would be just as big as everything else, and there would be no stable matter of any form. We'd all be collapsed into horrible black holes, a very, very a highly unpleasant universe. Okay? By the way, just as a brief comment, the reason why there's, in our world, we actually have such a large diversity of distance scales. There's humans, there's planets, there's, the fact that there's such a big diversity of them turns out to be a direct consequence of the weakness of gravity. Okay? So really, the weakness of gravity is not only necessary for any kind of macroscopic world to arise, but actually also generates the very rich structure of different length scales that we see. So, but our current answer then, in the theory that we actually have and have tested to why is gravity weak, is, well, that looks like it wants to do that. So once again, we have to do exactly the same thing. We fine-tune. We say that there is this parameter that would say how often it bangs into the Higgs field, and we just adjust things against each other now, not to 1 part in 10 to the 120, but to 1 part in 10 to the 30. Okay, it's still pretty bad. In order to accommodate this very basic fact. So the questions, why is the universe big? Why is gravity weak? All special cases of the general question, why in a universe with violent short-distance quantum fluctuations do we have nonetheless macroscopic order, is the question that we're going to address. So back to this picture, our understanding now of that scale invokes a 1 part in 10 to the 30 tuning. That invokes a 1 part in 10 to the 120 tuning. If we didn't do these tunings, if we imagine putting a bunch of theorists in a spaceship, closing the windows, and asking them, giving them the laws that we have, the standard model of gravity, ask them to predict what the universe would look like without letting them look outside. Of course, this isn't a very consistent experiment, because if they're in the spaceship to begin with, the universe, anyway. But just, but if you do that, they would not in a million years predict the world that we see. What they would say is, oh, there are these huge fluctuations. My guess is that the world looks like that. All the scales are stacked right on top of each other. And that's a horrendously unpleasant universe. Okay? So what controls these violent quantum fluctuations? Why is there a macroscopic universe? Well, let's talk about the second problem. The first problem is more confusing. So we'll defer it to the end. Let's talk about the second problem, this problem of the fluctuations in, well, we can phrase it actually in general terms. Let's phrase it in general terms first. So we have these huge fluctuations. We have these quantum fluctuations. They get smaller. They get, as the box gets smaller, they get bigger and bigger and bigger. Okay? This problem, I want to emphasize, does not come from some detailed part of a 6th decimal place of some esoteric calculation. We run into this problem for precisely the reason I've told you, which is almost identical to the correct technical reason for it. Okay? We run into it as a direct consequence of putting together relativity and quantum mechanics. Special relativity and quantum mechanics, vacuum quantum fluctuations just directly lead to this problem. So it's just an absolutely direct consequence of the marriage of quantum mechanics with this notion of space-time that Einstein gave us. Okay, now, let's say we are trying to understand why it is that, we don't have these big, huge fluctuations at distances shorter than 10 to the minus 17 centimeters. Well, there's a very qualitative prediction. Something new should happen as I shrink the box down to around 10 to the minus 17 centimeters. Right? Let's say nothing new happens at 10 to the minus 17 centimeters. Let's say something new does happen, but at 10 to the minus 28 centimeters. It doesn't help, because then these fluctuations are huge, 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 down to 10 to the minus 28 centimeters. Right? So it still doesn't help explain why we have this nice scale where the electron bangs into the condensate every 10 to the minus 17 centimeters or so. So this argument just tells us that something new has to happen at 10 to the minus 17 centimeters. At some level, this is a $5 billion argument, okay? Because this is one of the very strong arguments we have, that we expect some dramatic new physics to show up at the Large Hadron Collider, which we'll talk about tomorrow. That's exactly the scale we're about to probe. But something has got to give, like right around the corner. Okay? Now, what could it be? There's a historical precedent for this. Actually, there's a number of historical precedents for it, but let me give you one of them. There are other times in the history of physics where exactly this sort of question was confronted. This style of answer was given and was exactly correct. In fact, it was correct in even more profound ways and more surprising ways than people realized. For instance, at the turn of the century, classical physicists had a really serious puzzle because they looked at the point-like electron and they saw that there's some energy stored in the electric field around the electron. They calculated that energy. That energy got bigger and bigger as they went to smaller and smaller distances close to the electron. And they found that that energy could become infinite. So this was a serious puzzle for classical physicists. And they thought and they thought and they said, okay, in order to avoid this problem, something new has got to happen at some distance scale that they worked out. It turned out to be around 10 to the minus 13 centimeters. And around 10 to the minus 13 centimeters, if something new happened, well, then the energy stored in the electric field around the electron wasn't too much bigger than the mc squared of the electron. So it might be okay. Okay? But if you made it much, much smaller than that, it would be crazy. Because once again, you'd have this huge positive contribution to the mass of the electron, the energy of the electron, which you would have to cancel against some other contribution in order to understand why the electron had the mass it had. Okay? So this was a serious puzzle, and the way they tried to solve it is to give the electron a small size. They tried to make it around 10 to the minus 13 centimeters big. They tried and they tried. These theories failed in every imaginable way. Okay? They didn't work. But that's because they were missing quantum mechanics and relativity. We now know the correct answer to this problem. The correct answer is actually at even larger distances than 10 to the minus 13 centimeters. Something new did happen. The new thing was quantum mechanics, electrons and positrons, vacuum fluctuations, that whole story. These vacuum fluctuations, one thing they do is, you see, as you get the distances shorter than 10 to the minus 11 centimeters, where these vacuum fluctuations for electrons and positrons become important, you can't actually tell anymore which one of these electrons is the central one. There's just this whole big cloud, many, many electrons and one fewer positron. Okay? And so it just doesn't look point-like anymore, and this crisis, classical crisis, completely disappeared. Okay? So I'm giving you an example. Precisely the same sort of argument came up, and the solution was pretty dramatic. The solution was an extension of space-time plus quantum mechanics that doubled the world. Okay? I'm giving that analogy because we're about to, the best solution, candidate solution we have to this problem, to our problem today, has exactly the same character. Yeah, let me. Now, if this slide seems to be completely out of place, it isn't. So all of these arguments about something new needing to show up at 10 to the minus 17 centimeters were purely internal theoretical arguments, right? Quantum mechanics, relativity, this, that, violent quantum fluctuations, and we arrive at a conclusion. Something new has got to happen around 10 to the minus 17 centimeters. Okay? It turns out that from a completely different part of physics, from the opposite distance scale, from the largest possible distances, not the smallest possible distances, but from cosmology, from astrophysics and cosmology, there's other evidence that something new should be happening at 10 to the minus 17 centimeters. It's a part of the wonderful unity of this subject, okay? And that evidence has to do with something probably many of you have heard of, which is that in addition to the dark energy, which is mostly what dominates the energy of the universe today, there's also been evidence for a long time that there's dark matter. That even the mass that we see, that most of the mass in the universe is not made out of us. Okay, so we're a tiny component of all the mass and energy in the universe, or even a very tiny component of the mass. And most of the mass that's out there is in the form of dark matter. One of the early pieces of evidence for this was that people looked at galaxies. The stars around the galaxy go at some velocity around the galaxy. And you can infer, you can indirectly measure how fast they're orbiting around the center of the galaxy. Now, if what's keeping them bound to the galaxy is just standard Newtonian gravity, then you would expect that if the stars are getting further and further out, while they're further and further away, the gravitational force is getting pretty small. They've basically seen all the mass that they're going to see, so their velocity had better slow down if they're going to remain bound in this orbit. Okay, just that very basic argument. So if you would expect that if you measure the velocity of the stars as a function of distance, that it would eventually go down as you went out to larger and larger distances. Well, that's not what was measured. What's measured is that more or less the velocity of the stars go to a constant as you go further and further out. Okay? So what do? Do we chuck everything? This is evidence that Newton was wrong, gravity is wrong, everything is wrong? Or do we try to do something else? As I've mentioned a number of times, you never know ahead of time whether the right thing to do is to think that everything's going to hell and we have to change everything, or you just keep pushing with the theory that you have. But the best idea is to push the theory that you have as far as you can and see if it breaks. Okay? In fact, if this dark matter seems mysterious to you, I want to remind you that the way many of the distant planets in the solar system were discovered were exactly like this. The distant planets in the solar system were first inferred by the fact that there seemed to be funny things in the motion of planets far away that you could even back then in the 1800s have said, oh, Newton's wrong. Or you could say, no, there's another planet out there somewhere, it's tugging on it. Dark planet. Okay? And dark planet was the right answer over and over again. That's how Neptune was discovered, Uranus, Pluto. Okay? So, anyway, so that's what, so the conventional explanation is that what's explaining this is that there's actually a huge amount of other matter here. We're a tiny component of it. There's actually a huge cloud of dark matter surrounding the center of the galaxy, well, surrounding the galaxy. And that matter is explaining this, the fact that this velocity flattens out. Now, you can ask, how much of this dark matter do you need? And, well, you can come up with the energy density you need for the dark matter. But you can ask, where could it have come from? And if we imagine we go back earlier in time, in the Big Bang, everything was a hot soup. And if we imagine that eventually this dark matter has got to have extremely weak interactions with us, otherwise we would have seen it already and it would have shined light. Okay? But if we go back early enough, we can assume that the interactions eventually become strong enough that everyone's in a big hot soup with each other early in the Big Bang. So you have a lot of these particles, the dark matter particles. The universe expands, it cools, and eventually, so we know how much dark matter and all the other matter there was very early in the history of the universe, and then we can just churn standard physics to figure out how much of the dark matter is left today, and see what it would take for the right amount to be left. Well, this is a calculation you give to cosmology graduate students, and they come back and they tell you that we need to have the dark matter have interactions, the dark matter with ordinary matter, needs to have interactions like this. And in fact, we can predict what the needed range of this interaction is. The range should be around 10 to the minus 17 centimeters. That number, 10 to the minus 17 centimeters, is popping out of a completely different part of physics. And it's giving us evidence that there has to be new physics, minimally the dark matter. And where should it be coming in? The interaction length, the strength, the range should be around 10 to the minus 17 centimeters. So this is quite remarkable. We have these deep theoretical reasons to suspect something new happening at 10 to the minus 17 centimeters. And we have this direct experimental clue that there is something new happening at 10 to the minus 17 centimeters. This isn't the unique particle that could be the dark matter. This argument doesn't have to be correct. Well, this argument is correct, but the dark matter could still be something else. Okay? But it's in a sense, it's the most canonical possible picture for dark matter that we could have. And it's quite remarkable that it's telling us the same scale. This is often called the WIMP miracle, because this kind of dark matter is often called the weakly interacting massive particle. Okay? And the WIMP miracle is that the needed range is exactly what we think it should be from other arguments. Okay. All right, so I've given you this deep theoretical reason. So let's go back to the deep theoretical question. There's this problem with the fluctuations of space-time. Okay? Something new has got to happen at 10 to the minus 17 centimeters. Whatever that new thing is, it can't be something dinky. Okay? It can't be, oh, there's this one extra particle. It has to do something radical. It has to remove these violent vacuum fluctuations. Those violent vacuum fluctuations are hardwired into space-time plus quantum mechanics. So it stands to reason that if you're going to solve this problem, if you're going to give a good solution to this problem, you have to modify one of those two things. You have to change one of those two things in some way. Okay? It's ironic that a lot of today's lecture is going to be about modifying or extending our notion of space-time, when yesterday's lecture was all about the fact that space-time is doomed anyway. Okay? What I'm really saying is we have to modify space-time first, and then it's doomed later. Okay? But all of this stuff is happening at 10 to the minus 17 centimeters. Okay? This is still gargantuan distances compared to 10 to the minus 33 centimeters, which is what we're talking about a lot yesterday. Okay, so that's the picture we're after. We're looking for some kind of extension of space-time that actually explains why the pencil is standing on its tip. It's a little hand holding it up. Okay? It's stabilizing it. It's removing these huge vacuum quantum fluctuations. So we're looking for that little hand. And there have been many ideas. I think it's fair to say that there have been two classes of ideas in the 30-some-odd years people have been thinking about this problem. There have been two basic classes of ideas for what might solve it. And both of them, in one guise or another, involve some extension of our notion of space-time. One of those set of ideas involves invoking extra dimensions. Again, in one guise or another. Something you learned yesterday is that dimensions are not necessarily so different from ordinary physics, right? So extra dimensions aren't necessarily so different from ordinary physics. The inside of that tin can was completely equivalent to something going on the boundary of the tin can. But anyway, it invokes in one way or another extra dimensions. Extra dimensions are an interesting idea. I've enjoyed thinking about them. But they're not the deepest idea. They're not the deepest idea for what can solve this problem. For some reason, especially in popular books, in various presentations to the general public, people get more excited about the idea of extra dimensions of space. But it's really not a very deep idea, really at all. Okay? This is a much, much deeper idea. It's a much deeper and much more important idea. So I want to tell you about it. And it's called supersymmetry. Supersymmetry is also a kind of extra dimension, but a much more interesting one. Okay? Supersymmetry says that in addition to our usual 4 dimensions, there are extra dimensions, but the extra dimensions are not measured. The distances in these extra dimensions are not measured with the same numbers we use to measure the distance in the ordinary dimensions. We use ordinary numbers to measure distances in ordinary dimensions. 5 meters, 7 seconds, right? Those numbers have the property that A times B is equal to B times A. They're ordinary numbers. Okay? It turns out that in supersymmetry, we have these extra dimensions, but the distance in these extra dimensions is not measured in ordinary numbers. You can say, in some sense, they're measured by quantum numbers, quantum mechanical numbers, which satisfy the following funny multiplication rule, that A times B is equal to negative B times A. Now, if A times B is equal to negative B times A, in particular, A times A is negative A times A, so A squared is 0. Okay? That fact is going to be very important in a moment. But anyway, if we go back to our picture here, we have an electron zipping along. When the electron moves in the quantum dimension rather than the ordinary dimension, then we see it in our four-dimensional world as another particle. Okay? We see it as another kind of particle whose properties are almost identical to that of the electron. In fact, it has the same charge, but I'll tell you what small property is a little different in a second. Okay? Think about it for the moment. It's just some partner to the electron. Okay? Almost identical properties. Now, if this was an ordinary dimension, then there's many ways that the electrons could pop into that direction, right? You could make it go slowly in that direction. You could make it go fast in that direction. There's all sorts of things that you could do, but not for this quantum dimension. In this quantum dimension, you can't take more than 2 steps in the quantum dimension because A squared is 0. Okay? So you try to go 2 steps and you're already dead. You can only take 1 step in this quantum direction. So either the particles move in our direction or they move in our direction with 1 step in the quantum dimension, and that's it. So that means that for every particle we have in nature, there has to be a partner to it, which is the analog of that when it's taking 1 step in the quantum dimension. These partners are called superpartners. Okay? So if I have the electron, then this particle is called the superpartner of the electron. Okay? So notice how eerily similar this is to the antimatter story. We have an extension of our notion of space-time, this time incorporating these quantum dimensions. It once again doubles the world. In addition to ordinary particles, we have ordinary particles and their superpartners. So let me introduce the superpartners. Okay? So here's the electron. Remember, the electron, as we've said a couple of times, is like a bit of a spinning top. It spins around at some rate. The selectron would have exactly the same properties, but just simply wouldn't spin. Okay, so that's the property, that's the thing that distinguishes. Same charge, everything else. So it's selectron because it's the superpartner of the electron. It's also silly, okay? But once again, these things were invented in the 70s. So the names were invented in the 70s, so you can't blame my generation for it, okay? Okay, the superpartner of the quark is the squark. The superpartner of the photon is the photino. I don't know why it's not the sphotino, other than I guess it's hard to say, okay? So, but anyway, all these guys exist. And remember, I told you, these quantum dimensions do not violate the rules of relativity in quantum mechanics. They're, if you like, they're a very, very special kind of theory that combines relativity and quantum mechanics. It's so special that, in fact, it can be interpreted as having these extra quantum dimensions. So it's just a good old-fashioned theory, but with a very interesting symmetry. Okay? So to describe the menu of what's going on, I still have to give you these little stick figures, and something that tells you that this theory is, I've explained the super part, but not the symmetry part. There's supposed to be a complete equivalence between what's going on in the quantum dimensions and the ordinary dimensions. If this supersymmetry was a perfect, was perfectly realized in our nature, there would be just complete equivalence between what's going on in the quantum dimensions and the ordinary dimensions. And you would notice that from the fact that these interaction strengths of the electron and the photon, there would be that stick figure. There's also another stick figure of an electron, a selectron, and the photino. And those interaction strengths are just identical. Okay? So that would be, that's how you would see that there is perfect symmetry between the ordinary dimensions and the quantum dimensions. Now, of course, we haven't seen these guys. We haven't seen any of these selectrons. We haven't seen any of these photinos. Okay? We haven't seen all these particles with these identical properties to us other than their spins being a little bit different. But as I mentioned before, already we've seen a number of times the similarity between the weak interactions in electromagnetism, between the strong interactions in electromagnetism. They're there. They're there. They're there at short distances. They're just being obscured because because of various accidents at long distances. These accidents at long distances we sometimes call symmetry breaking. But all it means is that if you go to short enough distances, you'll see what's really going on. Okay? So in this case, that means that supersymmetry has got to show up if we go to short enough distances. Now, where from our general arguments must it show up? It must show up near 10 to the minus 17 centimeters. Otherwise, it's not going to help with anything. Okay? But how does this actually help the problem? How does it remove the violent quantum fluctuations? Well, this is how it does it. Let's take our big box, and we shrink it in size until it gets down to the neighborhood of 10 to the minus 17 centimeters. In that neighborhood, you all of a sudden see that it's possible to go into these quantum dimensions as well. So you're trying to fluctuate a lot in this direction, but then you see that these quantum dimensions around too. Now, the laws at this scale now tell you that there should be a perfect symmetry between what's going on in the quantum dimensions and what's going on in the other dimensions. But you can't have wild fluctuations in the quantum dimensions. You can't even take more than 2 steps in it. Never mind wiggle back and forth like mad. Okay? So the fact that these are these funny quantum dimensions tell you can't have big fluctuations in that direction. How can that possibly be consistent with what look like big fluctuations in our direction? The only possible consistent story is that those big fluctuations are actually absent. And they're removed by the presence of this supersymmetry. Okay? That actually really technically happens. So the fluctuations, they're there. They get bigger and bigger as you hit 10 to the minus 17 centimeters, but they don't get bigger after that. Okay? As you go to shorter and shorter distances, there are simply none of these gigantic quantum fluctuations survive at distances much shorter than 10 to the minus 17 centimeters. We thought on general grounds we needed an extension of space-time to solve this problem. Here's an extension of space-time. Here's how it solves the problem. Okay? Now, just so you have an idea, if we collide 2 of our ordinary particles together with enough energy, we can give them enough. We can give enough energy so that we can pop some particles off into the quantum dimensions. So there are some quarks inside this proton. We'll talk about it tomorrow. This will hopefully happen at the LHC. But we can collide 2 protons with enough energy so that 2 of the quarks in there can pop off into the quantum dimensions, and it looks like we've produced 2 pairs of squarks. Okay? Now, these particles aren't infinitely long-lived. In fact, they have a typical lifetime of around 10 to the minus 27 seconds. That's how long it takes light to travel the distance 10 to the minus 17 centimeters. And okay, so this squark is going to decay to a quark and let's say a photino. That's one of the allowed stick figures. This could do something more complicated, go through a more complicated chain and end up with something that has this photino again. Okay? So we'll talk about these things a lot more tomorrow. For now, all I want to do is mention that no matter what you do, when you make these things, you always end up with this photino sitting down here at the bottom. That photino cannot, in turn, according to the stick figure rules that I drew, can't decay into anything else. So the photino is just stable. That's interesting. So it's a massive particle with a range around 10 to the minus 17 centimeters. It's neutral. It's stable. It will be made early in the Big Bang. It would survive out today. That's a perfect candidate for the dark matter of the universe. So this super partner of the photon is a very nice candidate for what the dark matter might be. You see, from this theoretical point of view, it's not the particularly fundamental deep thing. Okay? It just happens that it's there. And we've seen that sort of physics thing happen in physics a lot, where there is some deeper structure, and it does various things as ancillary small consequences. An ancillary small consequence of this picture is that there's dark matter. Okay? But if it's true, it would be quite a remarkable picture, because dark matter would actually be light. But it's light when the light moves in the quantum dimensions. Okay? So the motion of light in the quantum dimensions would be the photinos that make up the dark matter of the universe. Okay. Now, There is one more remarkable hint that this idea of supersymmetry showing up around 10 to the minus 17 centimeters is correct. Remember I told you one of the great accomplishments of this standard model of particle physics was that it allowed us for the first time to even entertain the possibility that the strong force, the weak force, and the electromagnetic force were somehow, well, they were being described in the same mathematical language for the first time. They looked basically the same, and the only things, there are some detailed differences between them. For example, the interaction strengths were a little bit different. Electromagnetism was 1/137. The strong interactions, its dimensionless strength was 1/10. And there are a few other detailed differences between them, but it allowed us to entertain really seriously for the first time that they were part of a more unified whole. One of the necessary things that should be true if they're actually part of a more unified whole is that those interaction strengths should actually be equal to each other. And the other thing that we learned is that the interaction strengths aren't a constant. They gradually change as you go to shorter and shorter distances. Now, we can take what we know in the standard model and figure out what those interaction strengths would look like as we went to shorter and shorter distances. I'm plotting it. I'm plotting this 1/1 distance just so shorter distances is going to the right. And I'm plotting 1 over the strength of the interaction because it turns out that lets me draw straight lines. But if I do this, I find that the strong force, so 1 over its strength is 1 over the strength of a strong force is around 10. 1 over the strength of E and M is around 100. So I'm plotting something that looks like this. I find that the strong force gets weaker as we go to shorter distances. So 1 over its strength gets bigger. The weak force does this line, and E and M does that line. It's E and M in quotes because it's not really quite E and M, but it's some mixture of E and M and the weak force. But anyway, it doesn't matter right now. But anyway, there's a picture you can draw, and you find 3 lines kind of roughly converging to each other and coming tantalizingly close to actually meeting. But they don't actually meet. Okay? So this is what would happen if we extrapolated what we knew in the standard theory, nothing else, to shorter distances. But now we know that we should expect something new at 10 to the minus 17 centimeters. We should expect that we have supersymmetry. So you can ask what happens if you include the supersymmetric particles in that calculation. And this is what happens. Those 3 lines converge to a point perfectly, to within % accuracy. This, by far, did not have to happen. Okay? 2 lines will meet in a point. But it's not at all guaranteed that 3 lines meet in a point. Okay? So again, this is something that we didn't put in by hand. We didn't put in dark matter in by hand. We get dark matter out. We don't demand that something wonderful happens with the relative strength of the interactions as we go to short distances, but we find that something wonderful does happen. If we include supersymmetry, at distances around 10 to the minus 30 centimeters, all these interactions become equal. Quantitatively equal. So that really allows us to entertain the possibility that these forces are all unified. They're coming from a bigger force with exactly the same interaction strength. And that's being hidden at long distances, where long is long compared to 10 to the minus 30 centimeters. Okay? You know you're making progress in physics where a simple calculation quickly gets you something that looks right. Einstein thought for 30 years about how to get a unified theory. He never saw anything like this. Okay? This is the strongest hint we've ever had that the idea of unification of the modern forces is actually correct and is on the right track. And notice that the place where this is unifying is not so far from where gravity becomes important. So gravity is right around the corner. It really seems like there might be some theory out there that would unify these forces and unify it also with gravity. Of course, if this is an even longer lecture series, we talk about how string theory might do that. But that's not what we're going to do now. So now I'm going to switch gears. After all these marvelous possible successes, so once again, everything there, even those last 2 things that I said, which were very strong positive hints that we're on the right track, etc., none of that is confirmed by experiment yet. Okay? We haven't detected dark matter directly. We have not seen these super partners. We hope to see them at the LHC, as we'll talk about tomorrow. These are all circumstantial hints that we're on the right track, but we don't know that it's true. Okay? However, there are at least very positive hints that we're up to something good with trying to solve that problem. But let's go back and talk about the even bigger problem. Okay? What happens with that vacuum energy density? And here, it turns out that the analogous arguments that tell us we should expect something new to happen at 10 to the minus 17 centimeters for the second problem, for this problem would have led us to expect something new to happen at around, involving gravity now, something new to happen around a millimeter. Nope. Okay. There doesn't seem to be anything obviously strange going on with the laws of physics around a millimeter. So the same sort of argumentation that I remind you worked 100 years ago with the problem with the infinite self-energy of the electron, which leads us to think about supersymmetry and all these other wonderful ideas with the circumstantial evidence that we're on the right track now. The same line of argumentation just runs into a brick wall with this problem. It just flat out does not work. Okay? And no one has a good mechanistic explanation today. No one has a good explanation for why the vacuum energy is small, why the cosmological constant is small. No one has found the hand that might hold it up. Okay? So what I'm going to tell you now in the last 10 minutes is another kind of argument that people have talked about, which might explain why it's small. There's many ways to start this discussion, but this is one of them. I mentioned last time that one of the features of string theory that was discovered in the 1990s was that there was actually a single underlying theory, one theory. That was just a really remarkable theoretical fact. Which had another remarkable consequence, that it had lots and lots of solutions. Okay? We could take that theory and find many, many different solutions where it's a 10 or 11-dimensional theory, but there are many, many different ways of rolling up the internal dimensions to come up with a theory that was 4-dimensional at long distances. By the way, there was something that smelled pretty good about that basic philosophy, because that standard model that I showed you looked a little bit complicated, right? It has a bunch of moving parts. There's gluons, there's W's, photons. It had 19 parameters. It's beautiful and successful, but it had many, many moving parts. If you want to imagine how that might arise from something even simpler, well, this gives you a way how. The underlying theory can be completely unique, but depending on which solution, which particular way you rolled up the extra dimensions, you would come up with different possibilities for what the world looked like at long distances. So it's a good way of getting more complex things out of a very simple underlying structure. Okay? And what was discovered in the 90s is that it was so simple, the theory was completely unique, many, many different solutions, lots of different classical limits, and roughly speaking, it had zillions of solutions. Okay? Now, before 1995, zillions was millions. Okay? After 1995, and especially in the early 2000s, it became clear that zillions is zillions. Okay? Zillions is 10 to the thousands. 10 to the thousands. Actually, in some sense, infinite. But let's just say 10 to the 1,000 because it doesn't make any difference anyway. Okay? The number of atoms in the universe is 10 to the 88. Okay? So 10 to the 1,000 is nothing to be sniffed at. Okay? It's a very, 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 very big number. So the set of all these solutions of string theory were called the string landscape. And the second this word is uttered, controversy begins. Okay? So, but I want to tell you roughly how it could work. So first I want to give you a rough idea. How do you get all these zillions of solutions? Where does it come from? It's actually it's a very basic property of exponentials. Okay? Let me give you a little a toy analogy, which is essentially exactly how it works in string theory too. Imagine you have a smallish number, not 10 to the 1,000, but just around 1,000, little wells, okay, little double wells. They're not identical. They're all a little different from each other. Okay? They're all a little bit different from each other. And what you can do is put a ball in either the top or the bottom component of each well. Okay? So imagine there's some energy potential energies, say, associated with the ball in one well and ball in the other well. Okay? So, because you have roughly 1,000 of these, you have roughly 2 to the power of 1,000 different configurations that you could have. For each one, you can choose whether it's in the top or the bottom. So there's 2 choices for the first, 2 choices for the second, 2 choices for the third. By the time you go out to 1,000, there's 2 to the 1,000 different ways that you could arrange them. Okay? They're not all identical, so they won't all, if you added up all the energies for every one of the particles, you wouldn't get the same set of numbers. You'd all get slightly different set of numbers, so you get some distribution. Right? You get roughly 2 to the 1,000 numbers. The biggest they can get is if they're all in the top ones. The smallest they can get is if they're all in the bottom ones. You have to fit 2 to the 1,000 numbers between those 2 extremes, which aren't very extreme. So you're going to get an incredibly dense set of possible different energies that you might arrive at. The typical splitting between these energies would be roughly 1/2 to the 1,000. Okay? And so that means that just statistically, for no deep reason, just statistically, there is going to be some thing here whose typical energy is 1/2 to the 1,000 compared to what you would think it is naturally. Okay? Just a complete statistical accident. I didn't have to put in a number that was big as 10 to the 1,000. I just had to put in the number of about 1,000, which is a much more reasonable number, and let the power of exponentials take over. Okay? So it's very easy to get an exponentially large number of different possibilities out of pretty simple building blocks, relatively simple building blocks. In string theory, each one of these double wells corresponds to some slightly different way that you could have rolled up the extra dimensions, so you get to a 4-dimensional world. And detailed different ways. Do you turn on a magnetic field in this direction? Do you do something like that? Okay? So they're all just slightly different, discrete, detailed things that you can do, but you see, it adds up quickly. Okay? And so that's how you can get these 10 to the 1,000 huge numbers of solutions. Now, there is a very important consequence of this, which has to do with the fact that, now let's imagine that it's the real situation. So this cartoon is representing one of those configurations that we might get in the actual theory. And let's say that we're talking about one of those choices, one of those 2 to the 1,000 choices. And let's say it happens to have a positive vacuum energy, okay, positive lambda. Big positive lambda. There's no reason for it to be small, right? Big positive lambda. What would the universe look like? Well, it would be expanding, be accelerating, right? Accelerating like mad. Now, in a classical world, that would be all you would ever get. It would sit there accelerating like mad, and that would be that. But remember, in quantum mechanics, anything that can happen does. Okay? And there is some chance to have one of these tunneling events that we talked about. Okay? So there's some chance, let's say, for the configuration that was over there to tunnel across that barrier and end up over there. That would be something now that has lower energy than the one that we started with, right? Now, what would that look like? I have this universe around it, exploding around it, okay? When you tunnel, you can't everywhere in space at exactly the same time make this transition. This transition is occurring because of quantum fluctuations, right? So somewhere in this region, the fluctuation happened, and luckily, you're able to go over the barrier, okay? But now, once you're over the barrier on the other side, there's now kinetic energy, okay? So it's not that, so there's a little bubble that's made. It isn't like it's happening everywhere in space. You make a little bubble, but now that bubble wants to grow. That bubble wants to grow because there's less energy on the inside than on the other side. So the bubble wants to grow. It grows, and it grows at the speed of light. Okay? So it grows amazingly fast. So if you start in this high state, you'd go to the low state, poof. It's expanding out really, really fast. If we ignored for the moment that the underlying universe is accelerating, then what would happen is that here the bubble would be made, there the bubble would be made, there the bubble would be made. All these bubbles would smash into each other. It would completely destroy the original space, and everything would end up in the new vacuum, okay? In this new lower vacuum. And then it would happen again, it might happen again, and you would just start from one place, and in a few steps you'd end up in the lowest of all possible energy configurations, okay? But the situation changes dramatically because the universe is accelerating. What happens is you make this bubble, and it's expanding out of the speed of light. But remember, the acceleration is happening even faster than that. So by the time you make this other bubble in this place, and it's expanding at the speed of light, the space between them is growing so quickly that these bubbles just never ram into each other. And so this inflation keeps going on forever, just never ends. Space just keeps getting made more and more and more of it. You make this bubble, you make that bubble. Inside one of these bubbles, there will be some vacuum energy. So you make another bubble inside that. Inside that one, there will be one. You make another bubble inside that. And the whole picture goes on forever. It's a dramatic difference by turning on gravity and getting this phenomenon of inflation to take place. So this picture, for obvious reasons, it's called eternal inflation. Okay? So you make a bubble, a little later you made a bubble inside that one, a bubble there, a bubble there, a bubble there, but they never ram into each other. Okay? It's not quite true. They ram into each other occasionally, which is very interesting, but not in a way that changes the story right now. Inflation goes on forever. By the way, every now and then you jump to an energy density that's negative. Negative energy density doesn't inflate. It turns out in this picture, when you hit a negative energy density, the universe instantly hits a big crunch. So there are also some very nasty places in this picture where if you end up in there, you just crunch instantly. But now you see you get an extremely interesting global picture of the universe. No matter where you start, you're going to go down, you'll go up, you'll go down, you'll go up, down, it goes on forever. Every one of these 2 to the 1,000 possibilities is realized somewhere in the space-time. In fact, not only is it realized once, every one of them is realized an infinite number of times. Okay? So that's just fascinating. There's 2 to the 1,000 different possible worlds, or let's call it 10 to the 1,000 possible worlds, and they're all realized somewhere in this gigantic space, in one of these bubbles somewhere. Okay? So I can draw the picture also like this. Instead of drawing the bubbles, well, it's hard to draw accurate pictures. But imagine that you have a universe and it bubbles off another one as a bubble inside it, bubbles off another one, another one, another one, and it's this infinite fractal. It's an infinite fractal. And I stress these are really worlds, even though it's one unique underlying theory, it's a unique underlying theory, it has many solutions. And these solutions will all look at long distances like one of those menus that we talked about. They'll have their own stick figures, they'll have their own electrons and photons and quarks and gluons and other things like that. But they'll be different. They'll be different in detail. It's quite remarkable. People used to think that a holy grail of physics would be a unified theory of everything that would unify the strong force, weak force, electromagnetism, and gravity together in one super thing. Okay? Often, the sort of wishes we have before we understand things better turn out to be not even as grand as they could have been. Okay? What this theory is doing is unifying our world with 10 to the 1,000 other worlds that would naively look radically different. We're all the same thing. All these worlds are solutions of the same underlying theory. Okay? So it's an even deeper notion of unification than I think any of us could have imagined. Okay? So there's just one fabric, and it leads to all these different possibilities at very large distances. Okay, but this still doesn't seem to be any help to explain why we found this very, very minuscule energy of the vacuum. Except for the following final observation. Let's go to the middle of one of these regions. Let's say, I don't know, we go there, and there the energy is big. The energy of the vacuum is really big. In that universe, things are exploding every 10 to the minus 43 seconds. It's doubling in size every minus 43 seconds. Okay, that universe is just empty. Okay, everything is getting ripped to shreds constantly. Now, let's say a very much smaller fraction of those universes, roughly 1 over a million of those universes, will have a vacuum energy that's 1,000,000 times smaller than Planckian. Okay, in those universes, it's doubling in size every 10 to the minus 40 seconds. That's also empty. 10 to the minus 40 seconds is plenty fast. So you can try to make things smaller. You're looking at a smaller and smaller and smaller fraction of all these possible worlds where it's just not empty. Okay? Simply not empty. It has any chance of having anything in it. And you find that if it was going to look anything like our world, even roughly, that the value of the vacuum energy cannot be more than really a few times what we've observed it to be now. In other words, if we go backwards, if we take our universe and ask, how much bigger could we have made the vacuum energy and just not have our universe be empty? Something very dramatic, like empty, full empty, okay? You can make the vacuum energy maybe 10 times bigger, 5 times bigger than its value that we observe. If you make it much bigger than that, our universe is empty. Okay? So that's very striking. Actually, the value that we observe is very close to a dangerous value, beyond which it would just be empty. From this global picture, it's like most of the universe is empty. It's empty, 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 in incredibly tiny fraction of it, but a tiny fraction of infinity is a lot. Okay? A very tiny fraction of it, there are places where it's not empty. Okay? Now, is it so surprising that we might find ourselves in such a place? We live on a rock called the Earth, right? We don't live in interstellar space. The volume the Earth takes up out of the volume of the whole universe is around 1 part in 10 to the 60. That's not a deep, pressing problem of theoretical physics. Okay? There's a good reason we don't live in interstellar space. It's because, how could we? We have to live where there's some structure. Okay? So in this picture, most of the universe is lethal and empty, except a tiny few places, like there, where accidentally, because there's so many possible worlds, accidentally, the size of the vacuum energy is small enough that we can consistently live there. This kind of reasoning is often called the anthropic principle. Okay? And it's a really terrible name for it, because it makes you think that it's putting human beings at the center of everything. I hope you see from the way I've described it that it's exactly the opposite. This is a much more depressing view of the universe than even the ones that we've had so far. We are 10 to the 1,000 times less relevant than we thought we were before, at least. Okay? It's a very hostile, deadly universe out there. Okay? And we're lucky to be in a little corner of it where accidentally we can exist, if this picture is correct. Okay? By the way, it's even more bleak than that. If this is the way things are, then that means there's zillions and zillions of different possible states. That means that since we have such a tiny, tiny positive value, that anything close to us is very likely to have a big negative value. And that means the next thing that's going to happen to us is that we're going to tunnel into a big crunch. Okay? So that's the very likely future of our own universe, is that everything is going to end up in a big crunch, and a very catastrophic end. All right. So that's really the question that I want. That's unfortunately the best explanation we have so far for the smallness of the value of the vacuum energy. I say unfortunately because it's demoting our importance in the grand scheme of things a huge amount, and it's simultaneously making it harder for us to come up, starting from very first principles, with a unique prediction for what the world should look like. You know, that's one of the things that physicists hope to do, is to come up with first principles with a unique prediction why the mass of the electron is so-and-so, why is the strength of the weak interaction so-and-so. These 19 numbers, we hoped there would be some unique underlying theory and would predict those numbers uniquely. In this picture of the world, there is a unique underlying theory, but there's so many different possible low-energy worlds that those numbers just don't come out uniquely. It's not the fault of the theory. The theory is unique. Okay? But the solutions that are complicated enough to look like us, they have 4 dimensions, and so on, there's just many, many of them. And that actually has a positive benefit. There are so many of them that it becomes possible somewhere in this multiverse for structure to exist and for us to be here. So that's the question. Are we a tiny part of a vast multiverse? And I think it's clear that if, and it's a very, very big if it's true, then it's the modern Copernican revolution. In fact, it puts Copernicus to shame. Okay? So we're not the center of the solar system or the galaxy, blah, blah, but you know, we're 1 part in 10 to the 1,000 of some vast multiverse that just does not give a damn about our existence in the least. Okay? So if that's true, okay, but there's actually, people spend a lot of time having polemic philosophical discussions about this. But in fact, what's wonderful about this is it's a problem that's a real physics problem, because there's a major conceptual issue associated with it. We can make this analogy another analogy people like to use is to say the Earth goes around the sun at a nice distance from the sun. A little closer in, we'd boil and die. A little farther out, we'd freeze and die. Okay? So that's not because there was some benevolent creator that put us just at the right distance. It's because there's lots and lots of solar systems, probably, lots and lots of planets. Mostly it's too hot, mostly it's too cold. Sometimes, like Goldilocks, it's just right. Okay? And it's not surprising. Again, we're not surprised by that because we can build telescopes and see that there are other solar systems, see that these other environments are actually out there. If you can have a gigantic diversity of environments, then it becomes possible to have this sort of explanation for why things seem so perfectly adjusted right around you. But it's important to be able to see those other environments. Okay? And there's a conceptual physics problem here. No philosophy. Okay? There's a conceptual physics problem. Can we see these other universes in any way? Can we build the analog of a telescope to see them? That's the only way we could be convinced that they're there. If there's even some in-principle experiment we could do to see them. And it seems like we can't, very naively, because we're stuck in this accelerating universe. I told you yesterday, we're stuck in this accelerating universe. What we see out there is everything we're ever going to see. And all of this wonderful multiverse is out here, somewhere where light from those regions will never, ever, ever make it to us. Okay? So now this is a really interesting physics problem. Because on the one hand, if you just follow the equations, it tells you those reasons exist. It tells you to trust this global picture where there's this big multiverse, everything that we talked about. On the other hand, we appear not to be able to observe any of them directly. Okay? So does it make sense? Is it consistent? Is it just mathematically consistent? Does it make physics sense? This is an open problem. I think this is one of the hardest and most interesting open problems in this part of theoretical physics, is to see if it's possible to make progress on this purely internal theoretical puzzle. Someone might come tomorrow and write a paper with a perfect interpretation of the whole thing that's obviously correct, and we'd all be thrilled. Okay? I mean, I think we'll know the solution when someone hands it to us. But I want to stress it's not just a philosophical issue of whether we like it or don't like it. There are some very hard and deep physics problems that are exposed by this picture, which once again tell us that the biggest conceptual puzzles involve the use of the words quantum mechanics and cosmology in the same sentence. And once again, this issue of emergent time needs to be understood a lot better. So, there are these two problems of understanding why the universe is big, why gravity is weak. I told you that we have a very, very nice candidate set of ideas for why gravity is weak. Finding the hand that holds it up. That idea involves an extension of our notion of space-time to supersymmetry. Okay? There's circumstantial evidence that it's on the right track, and that's something that will be checked experimentally in this decade. Okay? So we'll really know something about that experimentally soon. So on that front, there's very big help from experiments on the way. There's also the problem of why the universe is big. For that problem, we don't have any, at the moment, we have no analogous explanation. We have no pencil that holds up the hand. And this picture of the multiverse that I told you is, at the moment, the best attempt we have at a scientific explanation for why this is true. There's always the other explanation that someone loves us, okay? But if you don't want the explanation that someone loves us and has adjusted the parameters just to allow for our existence, then that's a sort of explanation that also fits. I mean, I want to stress that it's not some capricious explanation that, and maybe you could come up with other ones. One of the reasons people take it seriously is that it seems to be an inevitable consequence of many of the best ideas we have for resolving the other puzzles. Okay? You follow your nose and you combine this idea of that there could be lots and lots of solutions. That just seems to be easy. It seems to happen in this theory. You combine that with the fact that when there's positive energy, the universe inflates, and just those two ingredients alone immediately give you this multiverse picture. And there's nothing you can do about it. Whether or not there is ultimately some anthropic principle associated with why we're here, that picture that there's this gigantic multiverse with most of the regions being lethal just seems to be a consequence of the best theories we have in physics right now. Okay? So perhaps it's true. Perhaps it's roughly true. Perhaps it's being, part of it's true and it's not being interpreted correctly. In the early days of quantum mechanics, it took people 30 years to sort it out, starting from good starts in roughly the right direction. So we don't know, but it's the best we can do right now. Even there's some help coming from experiments, because experiments this decade, as we'll discuss tomorrow, are also going to measure something about the acceleration rate of our universe. And while we can't conceive of an experiment yet that will directly confirm this picture, it could easily be that certain experimental results will just rule it out instantly. Okay? So there are things that can instantly falsify it. And we'll talk about some of them tomorrow, too. So after these 2 lectures of speculation, tomorrow is going to be completely devoted to our experimental friends who, very wisely pay no attention to us and go back down to their grungy labs and, and screw around with knobs and dials and actually bang things into each other, see what comes out, which is what's going to dominate a lot of the rest of the activity in this field in the next 10 years. So that's what tomorrow will be about. Thanks a lot. I failed again. I had promised you all that today I was not going to go 1 minute over 1 hour, okay? So I'm very sorry.
FaceTime is doomed, in particular the time. If you want to take a few questions, so if you have some questions, let's ask some. We can have another 5 minutes of discussion. Yes.
Right. So really the statement is that the real answer is no, I can't. But that's because the question isn't a very well posed question. What I can tell you is this. What I can tell you is that according to general relativity, energy, mass, curves space. Okay? It actually curves space-time, which is very important, not just space. Often people draw these sort of rubber sheet. There's some rubber sheet analogy for what the curving space-time looks like. That's a nice analogy for just curving space, but it's really curving space-time. And in cosmology, the time part's very important. If you're curving something, it means that 2 lines can't keep going and keeping exactly the same distance from each other forever, right? If something is flat, you have 2 parallel lines, they'll keep a constant distance between them together. But it might be curved and they would meet each other, or they'll get further and further apart from each other, okay? And the fact that they get further and further apart from each other is a reflection of the underlying curvature, okay? So, if you take 2 lines on the surface of a sphere and you send them up, then down at the equator, they're far apart, but they'll converge at the North Pole, and they'll hit each other. So the fact that they get closer to each other and hit each other is because the surface of surface of that sphere, or the surface of the Earth, is curved. Okay? Now, what happens is that in general relativity, energy and mass curve space-time, and so exactly the same thing happens not in the analogy, the motion in space on the surface of the sphere, but the motion in time as the universe gets bigger and bigger. In fact, the universe getting bigger and bigger is really the way we interpret the fact that these 2 lines are now getting further and further apart from each other. They're getting further and further apart from each other as a reflection of the underlying, the curvature of the space-time. Okay? So that's just what the theory says. The theory says that there's curvature of space-time, and it forces the actual space to be getting bigger. Okay? So when I say there's space being invented all the time, I mean through no known mechanism, right? It just keeps getting bigger. A very important lesson we've learned for hundreds of years is that we shouldn't get too caught up in what people sometimes call the word problem in physics. Okay? That when you have a theory, it's actually the theory that tells you the questions that make sense to ask. It's not you ahead of time, right? It's the theory or nature that tells you what the questions that are sensible to ask are. And so it just says that space grows. You can ask why, how, but it's not a right. Exactly, that's right. Well, I'm saying that so the word static involves time, but if you like, there is a space-time. There is a space-time. That's right. There is a space-time geometry. There is a space-time geometry, and things are just moving, and that's moving. So I'm doing it too, okay? Things are lines in that, there are trajectories in that space-time geometry, and the trajectories have the property that in a direction that you, for other reasons, will call time, because it's a direction in which you can causally separate events. In the direction you happen to call time, you find that the lines in that geometry diverge from each other, okay? So that's, right.
We have one more question.
So the question was that yesterday I said that this picture we have for what gravity in anti-de Sitter space looks like, that it's just completely described by a normal theory that lives on the boundary. I explained yesterday how that picture allows us to resolve the information paradox, and resolve it by saying that there is no information paradox. The information comes back out. Conservative quantum mechanics wins. Okay, and the question is, was it very important for it to be anti-de Sitter space in that argument? And what happens instead to de Sitter space, which is what the accelerating universe, uniformly accelerating universe, is technically called. So I think the correct statement is that if you want to talk about making just a normal small black hole, okay, black hole in this room, black hole the size of my head, okay. If you want to make a black hole in the size of my head, and you aim laser beams, you make the black hole, you wait for it to evaporate, you see things that go out. The question of whether information is or isn't lost in that process is very, very unlikely to depend on whether, on the 10 billion year light year length scale, the universe happens to be negatively curved or positively curved. If on the 10 billion years time scale, it happens to be anti-de Sitter space or a de Sitter space. Okay? Maybe that's wrong. Maybe it depends in some maybe what's going on in this room depends in some crazily subtle way on what's going on 10 billion light years from here. But if that's the case, it'll have many more interesting consequences than the black hole information problem, okay? We'll have to come to grips with it with many, many other things. It's staggeringly unlikely to be true. But so if we just assume that it can't have any effect on what's going on in here, then for the purposes of this thought experiment, for the purpose of the thought experiment of making a black hole and watching it evaporate, it's perfectly good enough to imagine a slightly different universe that is not ours, but where we lived in anti-de Sitter space instead, curved on the 10 billion year time scale. Okay? So in that universe, it's simply essentially proven that there's no information loss. Now, that doesn't mean that we're done, because there's many, many other questions that we want to have the answer to, other than just that one. And in fact, the fact that our universe is not this static tin can, but that on the 10 billion year time scale right now is actually accelerating, is completely removes the tools that we have developed to give some sort of precise definition of what's going on, a precise understanding of what is going on. And that's what I talked about yesterday. I mean, but there's lots and lots of things we're going to have to understand before we can come up with that. Well, again, if the black hole is much smaller than 10 billion light years, then it's very unlikely that it matters. Maybe if you're talking about a black hole that's almost as big as the de Sitter space, then it'll matter a lot, of course. Okay, but that's again, at least in our universe, that's a black hole that's so big that we have once again other trouble. If it's lying around. Okay.
Okay, so we have one more lecture tomorrow.
So we've had a lot of discussion about the theoretical part of fundamental physics. And today is almost completely going to be devoted to the experimental part. And something that you should know is that this decade is actually really an interesting one. There was a previous golden era of experimental results in fundamental physics that started late 1950s, early 1960s, stretched out about a decade or so, and played a very important role in the construction of that standard theory of particle physics that I told you about, and a golden era of cosmology that came after that, starting the very late 1980s, early 1990s, that played a very crucial role in the development of that standard cosmological picture. But for roughly a generation, certainly going back to the particle physics side, we have not been in a situation where we've been probing exactly the length scales where we expected something new to happen. Now, we've had very high energy accelerators in the interim, between the late 1970s and now. They've done absolutely spectacular physics. They've taught us a lot about how well our theory is working, but they haven't given us a clue for how things are going to break. And really, truth be told, there was, of course, always some chance that something would show up. People went to explore shorter distances in the past just for the heck of it, and they found lots of things. Okay? But there wasn't a completely rock-solid theoretical argument that something should be seen at energies roughly comparable to the energies that are being probed by accelerators now. But there has always been, as I've emphasized a number of times, some rock-solid arguments for something to show up by the energy scales we're about to probe. So that's why this is a particularly interesting decade from the point of view of the short distance part of our subject. It's really, for the first time in 30 years, we're going to be getting a window, a peek into physics at a length scale where we really expect something new and important to happen. And together with that, there's a whole slew of other experiments in astrophysics and cosmology that are all coming together at the same time. So we really haven't seen a decade with so much promise. We'll see how it turns out. But we haven't seen a decade with so much promise in quite some time. And so I want to tell you about it. So I'll tell you about three things, three kinds of experiments. The Large Hadron Collider, which is nearest and dearest to my heart. Experiments that are going to look for the dark matter of the universe. This is actually a very exciting subject, even right now. Many of us are waiting with bated breath for results from experiments that are looking for dark matter right now and might be releasing their data at the end of October or the end of November. So it's like happening now. The Large Hadron Collider is also now turned on and is running, but it's going to take probably a little while longer for us to get the interesting data out of it. I'll briefly talk about some of the experiments probing cosmology. And very unfortunately, I won't have time to talk about some of my favorite set of experiments, which are much smaller scale experiments, sometimes tabletop, sometimes much lower energy accelerators, that do what I call, that go out on what I call fishing expeditions, looking for interesting, weird things that might be showing up that could be telling us also something important about fundamental physics. It's very sad that I won't have time to tell you about that. But some of these things might actually end up turning up extremely exciting evidence for new physics that we'll have to follow up on as well. All right, so let me start by telling you about the LHC. So that's an aerial view of the region right outside Geneva. There's Lake Geneva. There's the Swiss-French Alps in the background. Near the border of Switzerland and France. And of course, you don't see this red ring on the surface of the Earth. That red ring signifies the place where if you go deep underground beneath where the red ring is, there's a tunnel, and in that tunnel there's a beam, and the excitement happens in the beam. This ring is around 27 kilometers in circumference. Okay? That's Mont Blanc. Okay. That's what it looks like in the tunnel. Okay? So that's deep underground where that red ring was. And you see 27 kilometers is a long way, so you can barely see the curvature. Okay? And now inside this tube, We, and in this talk, since I'm a theorist, we refers to the royal we, so it's the experimentalists. Okay, but I'll say we over and over again, even though I've never, if they let me near it, I would probably destroy the whole thing. Okay, but we accelerate to extremely high energies protons. Okay, one set of protons are sent whizzing around the ring in one direction. One set of protons are sent whizzing around the ring in the other direction. They're both inside that beam. They're made to accelerate faster and faster and faster and faster. Every time they go around, they're given a kick, a bigger kick, a bigger kick, a bigger kick, until they're going at roughly 0.999999 times the speed of light. That's 7 nines. Okay. That corresponds to the protons having an energy that's roughly 7,000 times their MC squared energy. Okay. And then at a couple of places around the ring, at a few places around the ring, these protons are made to collide with each other head-on. And in the debris of those collisions cause us to probe the structure of physics near 10 to the minus 17 centimeters. Okay? And we study what comes out. So around these collision points, we have gigantic detectors that detect the debris of what comes out. Oh, before I tell you that, let me tell you some more about the experiment. Sorry. So this experiment has a superlative associated in every possible adjective you might use to describe it. It's the largest experiment in human history. There's roughly 9,000 people who work on it from all around the world. Okay? America has committed roughly 1,300 people to this effort. The particular sub-experiments that I'm telling you about have 3,000 people working on them each. Okay? And it's taken roughly 20, 25 years from conception to the design and actually running of the accelerator. These accelerators are often called the modern-day version of cathedrals, which take very, very long time to build, often longer than the lifespan of people for cathedrals and the lifespan of careers for people, okay, now. So it's a very big scale, large scale effort, which we undertake because we think it's really important. Okay? So this is a slightly more schematic version of what happens when we collide particles at the LHC. So I told you we accelerate the protons, and here's the other protons. They're going at 0.999999 times the speed of light. We make that proton smash into that proton, and something happens. Now, mostly what happens is the following. The proton, if I take my famous magnifying glass and look at it, I see that it's, as I've described before, it's a bag that's made out of quarks and gluons. So inside the proton, we have a bunch of quarks and gluons. These quarks and gluons are point-like, as far as we can tell. The proton is big. The proton is this big, messy bag of quarks and gluons. Okay. So you take one big, messy bag of quarks and gluons, another big, messy bag of quarks and gluons, and you smash them into each other at enormous, enormous velocities. So what do you think happens most of the time? Most of the time, they just go splat, okay? And they just break up, and you get a whole stream and debris of particles going in this direction, and a whole stream and debris of particles going in the opposite direction. They're going so fast that the stream and debris more or less goes in the direction that they were coming in, okay? So they're going really fast this way, they go splat, and they just go splat like that, okay? That's not what we're interested in. So what happens the vast majority of the time is not what we're interested in, at least for this talk. Some people are interested in that, and there are some interesting physics associated with it, but it's not what we're interested in. We are interested in doing these things at very high energies because we want to probe very short distances. Again, it's the uncertainty principle over and over again. We've said it a number of times, but if the world was classical, we wouldn't need high energies to probe short distances. We'd build the little fantastic Voyage spaceship, and we'd make it smaller and smaller and smaller. And we'd zip around slowly, seeing what's going on, taking in the sights, okay? The problem is that as we make the spaceship smaller and smaller, the uncertainty principle starts breaking it apart, okay? We have to put more and more energies to probe smaller and smaller distances. So that's just the uncertainty principle. So what we're actually interested in is the head-on collision of these point-like constituents with each other. Okay? That happens much more rarely. That happens much, much more rarely, but it happens sometimes. And we know that it's a head-on collision because the debris of what comes out doesn't just go back to back from the direction of the beam. It's like two billiard balls hitting each other head-on, or just a little bit off, but really fast. They can come off at big angles relative to the beam. So that's what you look for. You look for stuff coming out at fairly large angles relative to the direction they were coming in at. Now, something new happens in here, okay? But the something new happens, and the something new happens is typically the formation of new particles. But unfortunately, the new particles don't typically come out with a name tag saying I'm a new particle, okay? They very rapidly decay and disintegrate in a time scale of order 10 to the minus 27 seconds. That's how long it takes light to travel the distance 10 to the minus 17 centimeters, okay? So in a time scale of order 10 to the minus 27 seconds, they disintegrate, eventually into the particles we know and love that are pretty stable. So for example, that includes electrons and positrons, which are exactly stable. It also includes muons. The muons are not exactly stable, but they go out so fast that, the time dilation effect that we've talked about many times easily allows them to survive a long time, and they're essentially stable as far as any observation around the LHC is concerned. We can make quarks. And the quarks will come out. We can't see them individually, but they get surrounded with another bag of other quarks and gluons and get spat out as something we call jets. But all of this stuff we can see. Okay? And we surround this collision region with gigantic detectors so that we can study everything that comes out. So we study the visible things that come out in order to get and try to use it to back reconstruct what actually happened. Okay? And then use that to tell us something about whatever the new thing was that was going on. So here's a schematic picture of one of the detectors that surrounds one of these interaction points. So the beam comes in this way in one direction, that way in another direction. The collision takes place in there. And surrounding it is this big, huge onion-like structure of detectors upon detectors upon detectors. Okay? These things are gigantic. This Atlas detector is 24 meters tall, 45 meters long. And you can ask, why is it so big? There's a number of reasons for why it's so big, but there's one very basic one. It's really cool. It's a little ironic that this machine that's letting us study the shortest distances we've ever studied is the biggest thing that we've ever made. 27 kilometers around, these enormous detectors. It's the uncertainty principle again and again. We had to make these things so big so we can accelerate them so fast so we can smash them into each other at such high energy. They come screaming out at high energies, and minimally, you should stop the particles if you want to study what they're doing. The particles coming out, you just have to stop them. But they're coming out so incredibly fast that you just have to put big blocks of material to stop them. And that has to be this big in order to stop them. Okay? So even the gigantic size of the detectors is a direct consequence of the very high energies because we're trying to study short distances. And this is a picture, again, of what it looks like. So a typical collision would have a particle coming in here, the proton coming in there. Something happens, and this spray of particles goes out and is detected all over the place in this onion-like structure. This is a picture of the actual Atlas detector. That's somebody, okay? Don't know who, right? But you see, it's no joke. It's really big. Okay? A cool thing about this detector is it's really big. It's got all this steel, et cetera, et cetera. If you stuck it in the middle of the Atlantic Ocean, it would float. It's got a lot of air, too. Okay? This is the other detector that there's two detectors that are studying the sorts of physics that we care about. The second detector is called the CMS detector. CMS stands for compact muon solenoid. The compact referring to the fact that it's kind of small compared to the other one. Okay. Now, I've emphasized the very, very big feature of these detectors, but really, I mean, I could spend an entire series of lectures telling you about how these detectors work, okay? But there's something going on in every one of these layers. Not one bit of space is wasted. Everything has a purpose and is designed to measure some feature of the particles coming out. Is it an electron? Was it a jet? Is it a photon? Is it a proton? What the heck is it that's coming out? And all the way down to really, really tiny distances around the interaction region. In the really tiny distances around the interaction region, there's lots and lots of strips of silicon. It's exactly like the inside of one of your digital cameras, except a very fancy version of it, okay? So this is what it looks like very, very close in to the beam, as the interaction region is covered with all these beautiful layers of silicon. Just to give you an idea of how far underground it is, this is the cavern in which the CMS detector sits, okay, before it was in there. Okay? So again, those are people, and this detector was lowered through that hole very, very slowly, okay? Now, amongst other things, again, I should resist the temptation to just tell you trivia, but it's just so cool. When these detectors are so heavy, when they sit, they would actually sag under their own weight, okay? So when they're engineered to be a little bit oblate. So when they sit, they sag and they become perfectly symmetrical. And that's because you have to arrange it so that you know the position of the beam to millimeter accuracy, okay, in order to be able to do the physics that we're interested in. All right, back to my pictures. So I want to tell you a little bit about how we will look for some of the physics that I told you about theoretically at the LHC. So remember, some of the puzzles that we mentioned yesterday, such as this question of why gravity is so weak compared to all the other forces, these fine-tuning problems that I mentioned, really demand that the new physics show up right at the distance that we're about to probe. I want to stress that this is not because we want to invent something to make our lives exciting, okay? The LHC is not simply exciting because it happens to be the frontier of where we are today. It is the frontier of where we are today. It is the shortest distances that we've seen so far. But that's not the only reason why it's interesting. It's interesting because it's going to a length scale where we've known for 70 years something is going on. As I've said a number of times, something is happening at 10 to the minus 17 centimeters. Something was happening there 2 billion years ago. Something will be happening there 300 million years from now. What's interesting is that we happen to be living in the epoch where we're about to explore that scale experimentally. Okay? And if there's a resolution along the lines I mentioned yesterday for these puzzles for why gravity is weak, and as I mentioned, there are a number of proposals. Some of them involve the ideas of extra dimensions. They're interesting. They have very specific signatures at the LHC. Those signatures might involve the production of black holes that will most certainly not in any conceivable universe eat up the Earth, okay? So please don't worry about that. When I was talking to a New York Times reporter about this, I had an hour-long conversation with him where I told him all the reasons why there was no problem. And at the very, very end, he said, yes, but are you really, really sure? And I got frustrated. And I said, look, because of the laws of quantum mechanics, anything can happen. So there is some chance that the LHC might make dragons that might eat us up. But I lose about as much sleep over black holes as I do about dragons. Okay? One of my smart aleck graduate students sent me an email after seeing this quote in the Times saying, but don't dragons violate energy conservation? I pointed out that there was plenty of mass in the detectors to make a dragon and to stop being such a smart aleck. Okay. Anyway, so I'm not going to talk about extra dimensions. There's a whole, I mean, it's an interesting possibility. It might happen. But I'm going to focus on supersymmetry because we have both more circumstantial hints that it's correct, and I think it would be a deeper, and more exciting discovery if it was there. Anyway, so how would we do it? We collide these protons together. Sometimes there is enough energy, and hopefully these guys have got to be, these quantum dimensions have to show up around 10 to the minus 17 centimeters. These very high energies at the LHC are designed to probe 10 to the minus 17 centimeters. So Sometimes the two quarks inside the proton will smash into each other and pop off the quarks into the quantum dimensions, making the squarks. We draw this picture yesterday. The squarks then come out and typically decay very, very rapidly into ordinary particles, quarks, other quarks, electrons, positrons, as well as things that escape the detector. These were the photinos that we talked about, the superpartners of the photon, which are neutral, very weakly interacting, and really just escape the detector without hardly leaving a trace. These were the things that could well constitute the dark matter of the universe, as we mentioned yesterday. So you can look for this. You can look to see if you've produced new particles and if there's missing energy. The way you look for missing energy is it looks like there's some missing energy in your event. Okay? It can look something like that. This is actually a cleaned up picture. In a real picture, there would be a lot more junk going on here corresponding to other normal processes, not just this spectacular process. It's slightly cleaned up. But anyway, it's a picture. The protons came in. You produce a whole bunch of particles that go out, which we see. Okay, you identify them in different ways. The things that went out that way, things that make it really, really far out could be muons. There's other things that you could see. So there's some way of identifying all these guys. But you can sort of see by eye here that there's something missing. Like there's a lot of stuff going out in this direction. There's something seems to not be conserving momentum, right? There's some overall momentum flow in that direction. And that stands to reason that there's something canceling that, moving off in the other direction. So that's how you would see that there is missing energy and have some evidence that the stuff was there and is being missed. So that's how supersymmetry could look at the LHC. Okay? And there's an entire experimental program that's devoted to figuring out exactly how we'll measure all the properties of the superpartners, from very, very detailed, more and less detailed measurements of exactly what comes out, exactly the pattern in which the particles come out. You can try to go back and reconstruct quite precisely what it was that you made, how it decayed, what sequence of decays it underwent, and try to get a more detailed handle on the actual, the masses of all the particles, how they all talk to each other, and so on. Something that I said was virtually guaranteed to be seen at the LHC was the Higgs. Remember, the Higgs is this condensate that's supposed to fill the universe, and typical particles move along, hitting this condensate every 10 to the minus 17 centimeters or so. And if we're probing physics at 10 to the minus 17 centimeters, we'll put ripples in this condensate, and the ripples in that condensate should look like new particles. Okay? Well, one of the dominant ways that this would happen in the LHC is if a couple of the gluons inside the protons, as they're smashing into each other, produce out of the vacuum, or take advantage of the fluctuation of a top quark in the vacuum. And the top quark was one of the particles that has a very big coupling to the Higgs. So that gives a particularly efficient way of making the Higgs also out of the vacuum. So we can have gluons and gluons fusing and producing a Higgs particle. Now, what the Higgs particle, exactly what it wants to do, exactly what happens to it after it's produced, exactly how it decays, depends on its mass in some detail. I'm giving you an example of what it would do in a particularly nice range of its masses from a theoretical point of view. But it also illustrates one of the challenges of doing physics at the LHC. The Higgs, at least in the range of masses that I'm considering, what it really wants to do, if you make it, what it really wants to do is decay almost all the time to another kind of quark. It's a kind of a partner of the top quark called imaginatively the bottom quark. Okay? So the Higgs really wants to decay to a pair of bottom quarks all the time, almost all the time. So you go through all this bother, you make the Higgs, you produce the Higgs, it's sitting there, and it just decays to bottom quarks almost all the time. Unfortunately, completely standard other processes, just the collision of a couple of these gluons together, all by itself, also makes bottom quarks all the time. And the rate for doing that is vastly, vastly bigger than the rate for producing the Higgs. So you've worked really hard, you've produced the Higgs, it's decaying, those bottom quarks are telling you everything you need to know about the Higgs being there, but they're buried on top of a gigantic extra amount of bottom quarks coming from other processes that are just hiding it. Okay? So at this point, you don't just give up. You notice and you realize that very rarely, like 1 in 1,000 times, roughly 1 in 1,000 times, the Higgs decays in other ways, which are more visible. For example, around 1 in 1,000 times, the Higgs decays to a pair of photons. Okay? That is much harder to fake with standard physics, and so you can look for that. Okay? So that's an example of what such a Higgs event would look like at the LHC. So the Higgs is produced somewhere in there, and there's a whole bunch of other particles coming out, but here are the 2 photons. Okay? Here are the 2 photons that are detected somewhere in this onion. Now, I told you that standard physics has a harder time making photons. It still makes plenty of photons. So here's just a plot of number of events. I'll tell you what that means in a second, but this is what's going to end up coming from the Higgs. And you see, standard physics is giving you plenty, lots and lots and lots of photons, even more than you get from the Higgs. So you have to take advantage of yet another fact, which is that when you have this photon, and it decays, when you have this Higgs and it decays to 2 photons, each one of the photons has exactly 1/2 the energy of the Higgs. Right? Now, of course, the Higgs could be coming out really fast, but we can still figure out what the energies of those photons were. And we can figure out if it was coming from the Higgs or not. If it was coming from the Higgs, if I take the 2 photons and I figure out the frame in which they would be coming from, where they would go back to back carrying equal momentum, then if I add their energies in that frame, it should always be the same value, namely the mass of the Higgs. Whereas from standard processes, it would come out all over the place. Okay? So the events you get from the Higgs would be all piled up in one spot and in the neighborhood of what the mass of the Higgs actually is. So you make a plot like that, and you find that there's a bump sticking out there. Okay? So standard physics is just sort of randomly giving you photons and fewer of them as you're going to higher and higher energies. But the Higgs has a particular mass, and it would show up as a feature or a bump in a plot like this. So that's how you begin to infer things about the fact that it's there and some of its properties. So this is actually a completely ubiquitous way of looking for this physics. We're always interested in looking at, I mean, this is extremely schematic. Any of my experimental colleagues in the audience will just kill me for making their life look so simple, okay? But this is roughly what you do. You look for some kind of configuration of the particles coming out. So we typically call that the final state. You look at the final, you look at a final state, and you figure out how many of those things you would have gotten if all you had was completely known standard physics. Okay? That's something that we can in principle calculate because we understand the theory that we have very well. So we take the theory we have, the standard model, we understand it very well, we turn the crank, and we figure out how much of those processes we would expect to see. But just like in the example we saw, if there is some new physics beyond what we've seen, then it would be coming in at some characteristic energy, the characteristic energy that we haven't been to yet, that we're about to explore, okay? But at some characteristic higher energy scale, and you would expect to see it as a bump on some plot like this, okay? And one of the things that helps you distinguish it from just standard processes is the fact that it does have a characteristic energy scale, whereas the other stuff doesn't. Okay? Again, this is a cartoon, and in real life, it's harder than this, but it's an okay cartoon. Okay? Now, let me give you an idea of, so it's obviously a needle in the haystack problem. Okay? Let me give you an idea of the size of the haystack and of the needle. Okay? So when we collide the protons at the LHC, the rate at which we have events taking place is about, there's about 1 billion collisions per second. Okay? 1 billion collisions per second. The rate is actually so high that, that you can't even record the data that would come out from every one of the collisions. That would be vastly more than we could possibly store. Okay? So you already make a decision at the level of every event that took place, whether you're going to keep it or not. The decision is made roughly whether enough things are coming out at high enough energies at large enough angles relative to the beam that we deem that they have a chance to be interesting enough. Okay? So you cut out roughly 1/10 of everything before you even get going. Okay? And you store all of that data. The amount of data is around 15 petabytes a year. If you were to store it in CDs, it would be a stack of CDs 30 miles high. Okay? And it's farmed out to computer farms all around the world, and that's only 1/10 of everything that's actually going on. Okay? Okay, so that's the kind of size of data sets we're talking about. So the rates are about 1 billion collisions a second. Now, let's talk about some standard physics, like the production of top quarks. Okay? Top quarks were what the previous experiment at the previous highest energy accelerator in the world, which is right outside Chicago. It's called Fermilab. It was colliding protons at where each proton had an energy roughly equal to its mc² energy. So the energy at Fermilab is 7 times smaller than the energy at the LHC. The LHC is about a factor of 7 leap relative to Fermilab. And Fermilab was essentially built and conceived. It had one main purpose, which was to produce this top quark. It was one of the particles that was predicted in the standard theory that people hadn't seen. So after 7 years, 8 years of work, they managed to produce some few numbers of top quarks, and it was very exciting. It was the discovery of the top quark. Great. This is in 1995. People were thrilled with 20 top quarks. Okay? At the LHC, we're going to make 10 top quarks every second. This illustrates a very important point. Something that happens when you go to higher energies. I mean, this factor of 7 might not impress you very much. We're just a factor of 7 above Fermilab. How can this factor of 7 make such a huge difference? It's not a factor of like 3,000. It's a factor of 7. Well, it turns out that the rate for producing new particles happens to scale like a pretty high power of the energy that you collide them with. It happens to scale like the energy to the 6th, roughly. So that factor of 7 is really buying you an enormous amount. Okay? And is buying you these factors, hundreds of thousands, a million, which makes the difference between waiting 7 years till you make a handful of particles versus making them all the time. Okay? That's why it's when this machine turns on at maximum energy that you expect the biggest jump in our reach. Okay? And that's why we do it. Right? So you expect big things to happen relatively early on. Okay. So we expect to make 10 top quarks every second. What about supersymmetry, the other things that we're excited about? Well, we expect to make roughly a squark a minute. Okay? So that's a nice human scale. If you make a squark a minute, we can accumulate a lot of squarks. But you see, you've got to beat down all of these things in order to be able to see it. Okay? All right. Now, I want to take just a little moment to say something about this known physics. Okay? So things that can contribute to known physics are, for example, if I collide 2 gluons in the proton, it can spit out 4 gluons coming out. And it can do this at some very, very high rate that can happen hundreds of thousands of times a second. And it can mask what would happen, like, let's say, if you produce squarks or if you produce other particles. Okay? So for a long time, and this, which you would think is the sort of grungy physics we understand already very, very well, but you still need to learn how to calculate it. Okay? How to calculate it just so we can make some, we can understand it accurately enough. Okay? I just want to tell you a very, very short story which also illustrates the really wonderful unity of our subject. Because it turns out in the course of these supposedly grungy calculations about understanding what's going on with good old-fashioned physics might be, in and of itself, a little hint for a new way of thinking about space-time. Okay? And I don't want to spend too much time on this, but let me just tell you a little story. It turns out that this problem, remember I told you draw these stick figures. Feynman told us how to draw these stick figures. It's all standard. We're done. We've understood it for 60 years. It turns out that as you start drawing those stick figures for a process of the sort that I told you about, it starts getting hard very rapidly. Okay? So for the process that I told you about, there'd be 220 of these stick figures, tens of thousands of terms. You wouldn't even do that to a graduate student. Well, tens of thousands is maybe okay. Hundreds of thousands, you would pause. But people learned how to do these calculations by various tricks. You don't need to understand anything actually on this slide in detail. All you need to understand is that those tens of thousands of terms collapse into this one simple expression. One line. So there were some crazy cancellations that took place in the course of the calculation, and then it collapsed mysteriously to a single term. That sort of miracle turns out to happen more and more and more when you do more and more and more complicated calculations like this. And it actually strongly suggests that the way Feynman taught us how to do these calculations, which, after all, as I stress many times, makes locality in space and time manifest, makes quantum mechanics and locality in space and time manifest, is making that manifest at the expense of obscuring some much, much deeper structure. Even sitting here in physics that's been under our noses for 60 years. Okay? Under our noses for 60 years is some marvelous new mathematical structure that's governing good old-fashioned standard physics. You don't need to understand any of these words, but the ideas that I told you from string theory, other ideas, older ideas that I've had no time to tell you about, going back to Roger Penrose, things known as twistor theory, and strange branches of old classical beautiful branches of mathematics that never had to do with physics in any deep way before, now seem to be sitting at the heart of this new mathematical structure that in the past number of years is starting to be uncovered, associated with good old-fashioned standard physics, the grungy part. Okay? There's something amazing going on even in the grungy part, which seems to say that there's some way of doing the scattering without ever talking about space-time. So there might be a hint for what gets us to replace space-time in a new way, even sitting here in the standard physics calculations. This is something that happens in physics over and over again. There is no, everything is just, everything talks to everything else. You can make these artificial separations and say, that's the boring part, this is the new part. The physics doesn't care, right? There's an incredible unity to the subject, and any time you start doing something interesting, you find that it ends up bumping into other things that are actually important. Anyway, that was just an aside. But so now let me finish the discussion of the LHC by discussing what we might know by 2020. Okay, so after 10 years of running at the LHC, what might happen? Well, of course, we don't know. So all of this is speculation. But I want to go through a variety of the implications of a variety of possibilities for what might happen. The first possibility that everyone asks about is, what if we see nothing? Literally nothing. Okay? And it's actually literally impossible for us to see literally nothing. This is something I unfortunately don't have enough time to explain properly, but I've alluded to before. It's the fact that if we just take the particles that we've seen so far, even no Higgs, just take the particles we've seen so far and do quantum mechanical calculations in the theory with the particles that we've seen so far, that little sub-theory predicts its own demise by 10 to the minus 17 centimeters, full stop. If you take that theory and you calculate things with it, if you calculate the probability for some specific processes, you find the total probability for some process starts becoming bigger than 1. It makes no sense. There's no such thing as probabilities getting bigger than 1. And that's the way the sub-theory has to tell you, I am sick, please repair me. Okay? I need help. The Higgs or something like it solves that problem, okay? Amongst other things. So we simply must see something. Now, it's possible there is something going on and we're missing it experimentally. I'm not saying that it'll necessarily be easy, But as an actual physical fact, it's almost impossible to believe that there's nothing there. If there is nothing there, then quantum mechanics is wrong. And there's no way that quantum mechanics is going to be wrong yet. Okay, another possibility is that by 2020, and actually, again, if this is what's going on, it's really likely that this will start happening earlier, significantly earlier than 2020. I should mention that right now, the LHC is running at 1/2 of its ultimate design energy. Okay? That 1/2, remember I told you that these rates scale like the energy to the 6th, so that 1/2 to the 6th is a bit of a pain. Okay? So it's running right now. It's possible that we'll see some hints for something new going on already in this current round of data, but it's not really guaranteed. It's going to run till the end of 2011, and then it's going to shut down for a while they take it up to its final energy. Okay? Once it gets to its final energy, then really, if there's things going on there, they should be produced like gangbusters. Okay? Fermilab right now has been looking for supersymmetry, has been looking for all these things, and after the result of many, many, many years of effort, it tells us that if there are gluinos there in nature, those superpartners of the gluon, they have to be heavier than, let's say, 300 times the mc squared of the proton. Okay? Let's say they're really there at 350 times the mc squared of the gluon, of the proton. If they're there at 350 times the mc squared of the proton, then the LHC will produce them once every second. Okay? That's, again, this big jump that you get when you go to high energies. So you expect exciting things to happen relatively soon. But anyway, if we see something like that, either supersymmetry or some of these other ideas that involve the hand that holds up the pencil, okay, that give a nice mechanistic explanation for the absence of fine-tunings in nature, I think that would be euphoria for our field, because we've been waiting for lots of new data like that for about a generation. And if it's particularly supersymmetry, it would be the first extension of our notion of space-time since Einstein. It would tell us very vividly that there was no fine-tuning required after all for answering the very basic question, why is gravity weak? It would leave us still scratching our heads about the size of the cosmological constant. Okay? We still wouldn't have a good explanation for the smallness of the cosmological constant. But we don't always solve all problems in physics at the same time. Something else that might easily happen by 2020 is that we'll produce zillions of dark matter particles. And we'll see that they're there. There'll be all this missing energy. And the LHC could be a factory for making dark matter. Okay, we wouldn't really be able to collect it too efficiently, but it's quite conceivable. There will be millions of dark matter particles just made in the laboratory, excited out of the vacuum at the LHC. We'll talk about dark matter more in a second. Now, here's what many theorists consider a nightmare scenario. I don't think it's so much of a nightmare scenario, but it's widely considered to be the nightmare scenario for our subject. What if we do eventually find the Higgs? I'll mention a small ironic point. If there's supersymmetry or any of this other exciting physics going on, that could be discovered early. It could be discovered well before the Higgs is. Because for the reasons I explained to you, the Higgs is actually a little harder to see. So the Higgs, if it's there, we're talking maybe 2015. Okay? But anyway, we're talking about 2020. So what if by 2020 we have evidence for the Higgs and nothing else? Okay. That's very, very deeply confusing. Because these arguments we had that we had to see some new physics at 10 to the minus 17 centimeters to hold up the pencil to explain why gravity is weak without invoking any fine-tuning, that there is something wrong with that argument. I should say this has never happened to us in such a sharp way before. Okay? Actually, it kind of happened to us for the vacuum energy problem. I mentioned to you that if you believe that new physics has got to come in at the relevant length scale to stabilize the pencil, then for the vacuum energy, the new physics would have had to show up at a millimeter, and it didn't. Okay? So if we go to 10 to the minus 17 centimeters, and we don't see anything that stabilizes the Higgs, then you start thinking that perhaps the Higgs is fine-tuned. Is it possible? What does it mean? Okay? In any case, it would be mysterious. It would make the fine-tuning for the weakness of gravity start looking a lot more like the fine-tuning for the smallness of the cosmological constant. And I can't emphasize what an incredibly bifurcatory moment in the history of our subject this represents. The settling of this question, one way or the other, has incredibly profound implications for the direction of physics in the future. It's the bifurcation between order and chaos. Okay? Do we see something like, do we see that there really is a mechanism that stabilizes the mechanism that explains why gravity is weak? There isn't any fine-tuning. There's supersymmetry that's accompanied with these beautiful ideas that the forces are all unified at very high energies, these new symmetries, new sorts of dynamics, extensions of space-time on the one hand, or this other picture, the picture that we're a tiny little nothing speck in a vast lethal multiverse, and most of the multiverse is deadly in the few places where the parameters are adjusted so that, for example, the energy of the vacuum is small enough we can be there. Okay? Could it be that there's an explanation like this for the weakness of gravity? Well, remember I told you, if gravity was stronger, we'd be black holes. It's actually conceivable that the weakness of gravity, it's conceivable that the weakness of gravity has a similar explanation. Okay? In fact, if you made gravity even a few times stronger, you would drastically change, when you look at it in detail, you would really drastically change the nature of chemistry. The fact that we have interesting stable atoms turns out to very, very sensitively depend on the precise value of this weak length scale. And if you change it a little bit, you would completely change what chemistry looks like. So it does seem like even the value of the weak length is at an interesting, somewhat special value. It's conceivable. There's much, much less evidence for this. I think the case for this is a lot less strong than the case for the vacuum energy. But if we see the Higgs and nothing else, then we might start taking this possibility a little more seriously. And I don't have time to talk about it, but there are other theories more closely related to supersymmetry and more closely preserving this picture of unification, which would be lost if we just saw the Higgs and nothing else, for which this conclusion that there is some fine-tuning could be made even sharper. Okay? I don't have time to describe them, but it is possible that by 2020, we will be contemplating this possibility more seriously if we don't see this whole panoply superstructure of mechanisms coming in, extending space-time and explaining the question, why is gravity weak? So it's really a dramatic moment. One way or the other, the field will go, and physics will go, fundamental physics will go in radically different directions. All right. So now I want to end by telling you about the other class of experiments that will be happening. So let's talk about dark matter. Now remember, one of the reasons dark matter was interesting is that we had this argument that there was a very good reason to expect dark matter to show up at around the scales we're about to go. It doesn't have to. There could be other kinds of dark matter particle. But if you ask the sort of simplest possible way that cosmology could synthesize and make in the early universe particles that had the right density to constitute the dark matter of the universe, you would find the answer particles whose mass is hundreds of times the mass of the proton. The range of the interactions are around 10 to the minus 17 centimeters. That's just remarkable. It didn't have to happen that this argument from the opposite end of physics supported this picture that we had to see new things at 10 to the minus 17 centimeters. Okay? I should say that if this is what the dark matter is, then there's roughly one of it per every liter of space here. Okay? So right there, there's one dark matter particle. There's a dark matter particle. There's a dark matter particle. Actually, they're whizzing through here at around 1/1000th the speed of light. Okay? But there's very few of them. They're pretty dilute, but not that dilute. Okay? There's lots of them in this room. Okay? So how do you look for dark matter? Well, every way of looking for dark matter really involves the observation that it does interact with ordinary matter in some way. I mean, the range of this interaction is very short. It's 10 to the minus 17 centimeters. It's incredibly weak, but it does interact with ordinary matter in some way. So we can make it at the LHC, as we just discussed. So the LHC might be a dark matter factory. Okay? You can do something else. The dark matter should be out there in the neighborhood, in the galaxy somewhere. In fact, under its gravitational influence, it would want to clump a little bit more towards the center of our galaxy. There's this big dark matter cloud, 100 times bigger than our galaxy. Okay? We're sitting in the middle of it, but the dark matter would even be clumping a little bit more towards the center. And every now and then, a pair of those dark matter particles could annihilate with each other. Exactly the same sorts of reactions here that make dark matter talk to ordinary matter could make the dark matter particles annihilate. And they have these big masses, hundreds of times the mass of the proton. So the particles that come out will be whizzing out at incredibly high speeds. Okay? And so you can look for anomalous high energy particles coming from our vicinity in the galaxy. Particularly interesting is looking for antimatter coming at very high energies from the center of the galaxy, because you'd be making particles and antiparticles, and it's not so easy to make high energy antimatter from ordinary processes. So that's called indirect detection. And finally, you can look for it directly. So there's one of them for every liter of space. So how would you look for them? Well, you take very, very cold vat of stuff. Okay? Many different kinds of stuff. But you take cold vats of preferably quite heavy nuclei. You put them very, very deep underground to shield them from all sorts of cosmic rays and other things that could be hitting the apparatus, and you just wait. You just wait for one of these dark matter particles to come along, hit one of these nuclei. When they hit them, the nucleus will recoil, and as it recoils, it'll give off some energy. And so what you have is this incredibly cold, dark place where every now and then the nuclei, for no reason, start moving. And you use that to infer that a dark matter particle came along and hit it. Okay? So that's called direct detection. And what's been going on in the past couple of years is lots and lots of activity in these two subjects, in these two areas, as the LHC has been ramping up. And we really expect certainly direct detection is really going places, especially in the next 2, 3, 5 years. Okay? Let me tell you a little bit about that. So I'm going to describe, just in a little bit of detail, one of the experiments that's looking for that's doing direct detection of dark matter. This experiment is known as Xenon 100, and it's because the vat of stuff in this case is xenon. Okay? So you have I won't describe it in too much detail, but you have this big vat of liquid xenon. There's some gas up here, some gaseous xenon up here. But you have this vat of liquid xenon. It's deep underground in Gran Sasso in Italy. And, and you wait for a dark matter particle to come in, hit one of these xenon nuclei. When it hits one of these xenon nuclei, one of the things it does is it shakes up the atom, which gives off a lot of light. And it also strips off some of the electrons. And those electrons, after you apply some electric field through the xenon, drift to the top. And when they get to the top, you measure them another way. Okay? So you get actually two signals from one of these dark matter particles coming in. First, a flash of light. And then after some time, another flash of light associated with the electrons. So using these two pieces of information, you can figure out that a collision happened and where it happened. Okay? And this is actually important because this experiment is designed to be big enough that other possible sources of things that could cause these nuclei to recoil become small. The major source of this so-called background, the thing that would fake the signal that you're looking for, is, believe it or not, just the radioactivity in the detectors that surround it. Okay? Just a trace amounts of radioactivity there will occasionally spit a particle into the vat of xenon, and that particle will hit the nucleus and make it shake and give off some light and so on. Okay? So one thing you do is you make it big enough so that there is a region in the center which is likely to be shielded from these, accidental external radioactivity. Okay? There's other detailed things that you can do. It doesn't matter this doesn't matter in detail, but it turns out that the way that the dark matter excites the light and excites the electrons is exactly the other way around as the way the radioactivity would. The radioactivity would turn out to give you less light and many more electrons, whereas the dark matter would give you much more light and many less electrons. So that gives you a way of discriminating what was radioactivity from what was dark matter. Okay? It matters a lot for the success of the experiment. So you have these two kinds of signal, the light signal and the electron signal, and when one is much bigger than the other or vice versa, you can deduce if it was dark matter or ordinary stuff. And again, the details don't matter here, but you see, so this is a measure for the ratio of the size of those two signals, the electron signal and the photon signal. And you do see that there's this big, this is the actual data that they released just a little earlier this year. And you see there's this big spread of things up here which correspond precisely to that radioactivity you're trying to get rid of. But indeed, it starts going down precipitously as you go in this direction, where you would start expecting it to look more like dark matter. And the signals for dark matter would be expected to be seen in this band, inside this blue band. And you see there's a little bit of leakage into this blue band. But you then look at these events in detail and actually figure out that so far they're not really seeing any evidence for dark matter. But this picture was based on a very small amount of data that they studied. They've been collecting a lot more data than that since then, just this year. And they plan to analyze it, open their box, look at their data. They haven't decided exactly when, but maybe at the end of October, maybe the end of November, maybe January, but sometime in that neighborhood. And they've collected enough data that if there's dark matter out there with roughly the properties we'd expect, we're talking about 50 events in there. Okay? So it's something that would really hit you over the head. Again, when you do experiments that go into uncharted territory for the first time, you expect big bang for your buck early. Okay? It makes sense. That's why you do it. All right. Something else so that's direct detection. Something else that you can look for, as I mentioned, is indirect detection. And here I'll just take a short, amusing story because it triggered a fair amount of excitement in the field 2 years ago. Remember, I told you that if there is dark matter out there in the neighborhood of the center of the galaxy, you would expect that every now and then it annihilates, and it could annihilate into very high energy particles and antiparticles. And so you would expect to see very high energy antimatter in space. Well, there was a satellite, an Italian satellite known as the Pamela satellite, okay, which was up there looking for high energy antimatter, high energy positrons. And antiprotons, but positrons in particular. And they reported at a conference in August 2008 the following picture, where they were drawing, you can't even see this here, but it was the ratio of the number of positrons to the number of electrons, which went down, just as predicted from standard astrophysics theory, and then started dramatically going back up again. Now, the reason I'm showing this picture is because they announced this result at a conference. People got very, very excited because this is exactly what you would have expected if there's dark matter out there. You expect to all of a sudden start seeing an extra new source of antimatter. And this was at around the place where you might have expected to see it. So people started getting very excited. I got an email from people who were at the conference. I immediately went to the conference website to try to see if I could pull this talk and get the slide. They had pulled the slide. The one slide that had the data in it, they had just pulled from the presentation. They weren't making it public. So people were very frustrated, and they knew that this experiment was going to release their data again, give the same talk 2 weeks later at another conference. Well, guess what? At the other conference, everyone was ready with their cameras. And when the slide came up, people took a picture. And this is a picture taken by my buddy on his cell phone and emailed to me. Okay. Anyway, later, indeed, it came out. This is the official plot, and indeed, the ratio went down, then it went back up again. So this actually triggered a fair amount of excitement in the field a couple of years ago, and right now the status is really unclear. Is it dark matter? Is it not dark matter? Our astrophysics, us particle physicists, got very excited, started building theories of dark matter that might explain this and might explain other things. Our astrophysics colleagues got excited and invented theories of pulsars that would explain these things. Okay? So we don't know if it's dark matter. We don't know if it's astrophysics. It definitely was unexpected. And it tells us that, but there is a bit of a cautionary tale here that anything from indirect detection of dark matter is likely going to take many, many pieces of evidence till you start taking it seriously. It's not going to be as valuable as just the direct detection, something bangs into your vat of xenon in the lab. It's ultimately better to do experiments in the lab here than rely on making observations on what's going on many, many light years away in the galaxy. Okay. There are other things that could happen, by the way, in the next few years that would be more incontrovertible. It turns out that when you look at the way dark matter is distributed around the galaxy, it's not distributed completely uniformly. And there are places where it's a little bit more clumpy. Okay? There are places, in fact, off the plane of the galaxy where it's a little bit more clumpy. Now, if it's a little bit more clumpy over there, you would expect there to be more chance that they could annihilate over there. And so you would expect to see these signals that we're talking about, very, very high energy photons, very, very high energy, particularly very, very high energy photons, to be coming now not from the center of the galaxy, but from well off the plane of the center of the galaxy. There's nothing out there. There's no stars out there. There's no pulsars out there. There's no funny stuff out there. So if you start seeing strange light coming in a clumpy way from off the plane of the galaxy, then that's another very good signal that maybe you're seeing annihilating dark matter. And these are a few pictures for what it might look like in a variety of scenarios. And you really could see that, that things off the plane of the galaxy would start lighting up and would not only give you evidence for dark matter, which would be exciting enough in itself, but would start actually probing exactly what it looks like, how much of it there is where. Okay? All right. So what might we know by 2020? Well, as I said, this subject is really, on the experimental front, evolving very rapidly now on all these different fronts. The most exciting one continues to be the direct detection of dark matter. And here is a plot. Again, you don't have to pay attention to the details. Very roughly speaking, roughly speaking, the vertical axis is a measure of the strength of the interaction of the dark matter with ordinary particles, something we call a cross-section. And the horizontal axis is the mass of the dark matter particle. So basically, this entire range from the mass is something that's theoretically reasonable. These various curves show what a variety of experiments have done, putting limits on what these cross-sections can be. I won't go through a story that some of these experiments actually claim to have seen something. You know, as exciting experimental science should be, it's in a chaotic and a quickly developing state right now. But just so you get an idea, people have sensitivity. For example, with the Xenon 100 experiment, we have sensitivity down to these cross-sections of order 10 to the minus, at the moment, let's call it 10 to the minus 44 centimeters squared. That means that the range of the interaction that's being probed is around 10 to the minus 22 centimeters. Okay? Now, it turns out that just from a theoretical point of view, if you ask the theorists, what are the sort of reasonable places that you would expect to have, what are the reasonable values for the cross-sections you would expect? Well, one set of values would live up here that have been long excluded, but another set of values really live right in the neighborhood of where we're about to probe. Okay? So this is something that's going to improve very quickly, and the experiments are exactly in a region where we expect to start seeing something. I should make one final comment. If there are WIMPs out there, they will be seen by 2020, almost period. If they're there in this mass range, they'll be seen by 2020, or they won't be seen for a heck of a long time after that. The current round of experiments is going to have sensitivity to cross-sections, not the current round, but the planned next generation, certainly by 2020, will have sensitivity to cross-sections that will go down another 2 orders of magnitude from that. Okay? So we'll go down another factor of 100 from there. In that neighborhood, around 100 times lower, around 10 to the minus 47 centimeters squared, you start running into a new background, something new that can fake the signal that you're looking for. And those are neutrinos. I haven't mentioned much about neutrinos in these lectures. They're some of the particles we expect in the standard model. And they're copiously produced in supernova explosions. Okay? So supernova explosions far away give us some stream of neutrinos that are running through the Earth right now. Okay? These neutrinos are incredibly, incredibly feebly interacting. That's why I've hardly mentioned them in these lectures. Okay? But they would interact with these nuclei strong enough to kick the nuclei by an amount that would be exactly what these events would look like, down here at 10 to the minus 47 centimeters squared. If we don't see the WIMPs by then the WIMPs will start being swamped by neutrinos. And the experiment will start getting very, very hard. Okay? Very, very hard. Not impossible, but very, very hard. On the other hand, as I mentioned, there's no very good theoretical reason to expect it so low. There's very good theoretical reasons to expect it right around here. And so if there are WIMPs there of the sort that theorists have known and loved and talked about for 30 years, they will show up by 2020. And they'll show up in someone's detector. Okay? And once they show up in someone's detector, you can be more confident that maybe you're seeing some signal from far away as well, because you can correlate what you're seeing far away from the properties that you have inferred from the detector. Okay? All right, so that's the story of dark matter. Let me end with just a few brief remarks about cosmology. So the story of this decade, coming decade in cosmology, is developments on 2 fronts. One of the interesting things about cosmology is what happened very, very early in the history of the universe. And particularly, as we've discussed, this wonderful theory of inflation that we have lots and lots of, not just circumstantial, but pretty reasonably hard evidence for, and that evidence will get more and more solid as this decade progresses. This theory of inflation gave us an understanding for where the tiny, tiny fluctuations in energy density early on in the history of the universe came from. And these tiny, tiny fluctuations, which in the sky today look like tiny, tiny differences in temperature of the cosmic microwave background in different directions of space, came from these underlying quantum fluctuations during inflation that were stretched out by this rapid accelerated expansion of the universe. And turned into ultimately the structure that gave us today, right? So that's an amazing thing. And the experiment that throughout the last decade did more than anything to solidify this picture and help us believe it was this wonderful WMAP satellite, the Wilkinson Microwave Anisotropy Probe. And it just takes a picture of the cosmic microwave background in a number of frequency bands. This is what it actually looks like before you process it too much. So you see there are these regions, different colors here are just slight temperature variations. You're just looking out of the sky. They're just slight temperature variations. The overall size is around 10 to the minus 5, a part in 100,000. The blue regions, as you see from here, are colder. The red regions are hotter. What do you think this is in the middle? That's our galaxy. Okay. So you don't often see the picture look like that. You often see the picture look like that, which is what happens after you subtract the galaxy, which you think you understand. Okay? But anyway, that's what it looks like. This is really a snapshot of what the universe looked like around 100,000 years after the Big Bang. And there are regions which were about within a part in 100,000, a little bit hotter, a little bit colder. And as I mentioned before, this a little bit hotter and a little bit colder got magnified by gravity. So ultimately, we got big galaxies, small galaxies, solar systems, planets, you and me. Okay? So the ultimate origin of all the structure in the universe is sitting here in this picture. Okay? And studying this picture in detail in great detail tells us a lot about the early inflationary epoch, which could have given rise to it. Okay? So WMAP did a huge amount. And now there's a next generation of experiment that's going to improve our measurement of exactly this picture by another order of magnitude or more. Okay? And that's that's known as the Planck satellite, which has been launched by the European Space Agency. Okay? It was launched a little while ago and has just started this year releasing its first pictures. So where it is this is fun. The Planck satellite is actually nowhere near the Earth. It's 1.5 million kilometers from the Earth, and it's sitting at an interesting point determined by the Earth an interesting point of the determined by the gravitational pull of the Earth and the Sun, which happens to be relatively stable. Okay, so it can sit there for a long time. These special points in the neighborhood of the orbit of the Earth and the Sun are known as Lagrange points. They were discovered by Mr. Lagrange in the 1700s, I guess. And there's 5 of them. 3 of them are, well, there's 2 of them that are completely stable. In other words, if you're in that neighborhood and you give a little kick, you just always stick around that region. And the other ones aren't stable. They're sort of semi-stable. In some directions they're stable, in the other directions they are not stable. This thing is in the neighborhood of one of the semi-stable ones. You might wonder why you don't put things in the neighborhood of the very stable ones. It's because things in the neighborhood of the very stable ones also accumulate rocks, other crap floating around, which is also get trapped around there. It's a very bad place for a extremely expensive experiment doing very fine measurements to sit. So you actually put it in the neighborhood of one of the semi-stable ones where, okay, every now and then it goes off a little, but you have computers on Earth that tell it to go back. Okay, anyway. And it's just started releasing its first images. That's the first image of the Planck map of the sky. But anyway, so this has not subtracted the galaxy or anything like that. But ultimately, we're going to get much, much more detailed measurements of the microwave background with Planck. Okay? Those detailed measurements could tell us much more and give us a lot more confidence in the underlying inflationary structure. Okay? In particular, one of the predictions of inflation is that not only should we have these fluctuations in temperature, but we should also have little fluctuations in what you might call little fluctuations in the space-time as well, what we sometimes call gravity waves. So we should see fluctuations that we can interpret as gravity waves as well. If the energy during inflation was as high as makes sense in many of the sensible theories, certainly not all, but many of the sensible theories, you would expect to see that too. And if you see that too, that's a real smoking gun of the underlying inflationary picture. Okay? It's not guaranteed to be seen, but it could be seen. And it's one of those things that if you do see it, you get extreme confidence that the theory is right. If you don't see it, you still have to look for other things that might give you extra confidence. Okay? So now, the other extreme of cosmology is understanding more the behavior of our current accelerating phase. Okay? So that's the other interesting thing that's been going on in the past few billion years, is our universe is accelerating at a uniform rate. Now, I've been just telling you the whole time that what causes this is the vacuum energy. But I said it's the simplest explanation for what's causing it. That simple explanation, however, in that simple explanation, we have to swallow that there's this enormous fine-tuning. We don't quite understand why this vacuum energy has the size it does, and so on. Okay? Some people think that maybe there's something else that's causing the acceleration of the universe. Maybe it's not a vacuum energy. Now, whatever else might be causing it, you still have to explain why the vacuum energy wasn't at the Planck scale. Okay? So none of these other explanations actually so far give us any way out of that. Okay? So they're no better on those grounds. But you still might think, we understand this so poorly, there's clearly something so wrong with our understanding, that it would be a good idea to try to see if it's true that it looks like a vacuum energy. If it looks like a vacuum energy, then the rate of doubling of the size of the universe should be dead constant. It should show no signs of having varied earlier of having varied as we go further and further back in time. So what you can do is design experiments that in one way or another, as finely as possible, give you measures for the expansion history of the universe between now going back to the 100,000s of years after the Big Bang epoch. Okay? And by doing those measurements very finely, you can reconstruct what the actual expansion history of the universe looked like and see if there's evidence, that this vacuum energy, or that the doubling rate, the expansion rate, was actually changing. If it's not changing, it's a dead vacuum energy. If it is changing, it's something else. So again, that's very dramatic. The difference has a dramatic impact on how we think about physics. A whole variety of experiments will weigh in on this. The Planck satellite will actually weigh in on this. Okay? But there are also experiments on the ground. There's this wonderful telescope that hasn't been built. This is an artist's conception for what it would look like. It's been designed, called the Large Synoptic Survey Telescope, which would be placed down in Chile somewhere. The astronomy community in the US has decided that this is the most important project to support over the next 10 years because it can do a huge number of different kinds of experiments. But one of the things that could really help is to nail, as accurately as we can, whether the thing that's driving the acceleration of the universe corresponds to a constant vacuum energy or not. And once again, don't pay attention to the details of this plot, but this is a two-dimensional plot of various ways that the energy, that the expansion rate could actually be changing with time. The kind of origin here, where this is -1 and 0, would correspond to a dead cosmological constant, perfect cosmological constant. And you can see that a combination of a whole variety of experiments using this LSST and other data could start putting pretty strong constraints on how much you can deviate from an exact cosmological constant. Okay? So that's another set of things that we can be looking forward to in the next 10 years. So in this subject, what might we know by 2020? We may, it's not guaranteed, but we may gather very significant additional support for the idea of early inflation. So that's one of the things I'm most looking forward to. I think as far as probing the acceleration of our universe, I think it is overwhelmingly the most likely thing is that we'll just find that to much higher accuracy, the cosmological constant is the very best fit for the current, to explain the current accelerating universe. Okay? I'm quite sure that that's what's going to happen, but it would be an enormous shock if not. Okay? So we'd really have to go back to the drawing board again. We're actually still pretty much at it as far as the cosmological constant is concerned, but this would be just really massively confusing to a theorist. So this is what the sort of situations we might be in 2020. Okay, so that's it. That's the survey of the experimental situation for the coming decade. And so I've had an enormous amount of fun in this set of lectures telling you about the past, the present, and the future of this wonderful subject. I think one of the things I hope you take away from these lectures, especially from the first couple of lectures, is that, one of the things I hope you take away is that we've really come an enormously long way in our understanding of fundamental physics. The understanding we have today, encoded in the standard model of particle physics and our understanding of gravity or understanding of cosmology, is, I think, beyond the wildest imaginations of any physicist in the 1950s. Okay? The fact that we understand the history of the universe, the fact that we understand the basic constituents of matter, we understand the basic rules for how things interact. We know roughly all possible worlds that could make sense. Okay? We have reduced our understanding. We've reduced the uncertainties. We've reduced the things that we're confused about and which require deeper explanation to explaining 19 numbers. Okay? This is an incredible, incredible amount of progress. I want to emphasize again, there are not basic questions in the world around us that we don't have a good answer to anymore. Okay? It's an amazing thing. it was eons from being true 100 years ago. Even 50 years ago, there were lots of basic questions about the world. Just how does radioactivity work? No one knew exactly. Okay? Now we understand the question. Any question you have about the world around us, we have a very good answer for that. Okay? Now, on the one hand, you can think that that's sort of disappointing. The questions that we're left with are further removed from things that we see in the world around us. But on the other hand, it means that we understand the world so well now that we can ask incredibly deep questions about it. These questions about where does space-time come from? These questions about why is the world big? These are questions that at some level you might have thought you could have asked 100 years ago, 300 years ago, 2,000 years ago. But in any of those previous periods, it was simply completely the wrong time to ask that question. Okay? There would be no way to even start answering it. It's one of the wonderful things about progress in physics. The more and more we learn, the more and more deeper questions we generate. And we're allowed to ask them. They become sensible questions that we can ask and work on and start to make progress on. Okay? So the fact that we understand the world around us so amazingly well means that finally, this is the epoch. This is a time in which these questions about the ultimate nature of space and time become accessible and become things that you can go to graduate school, learn about, start working on, work on in your office, right? It's not something Aristotle could have done. It's not something Einstein could have done. It's not something Feynman could have done. But it's something that we can do now. And it's a testament to the power of this scientific process that it does this. So we've come a very long way in our understanding of fundamental physics, but I also hope that you've seen from the last number of lectures and from the exciting prospects for new data in this coming decade that you should stay tuned because the best is yet to come. Thanks a lot.
I will give people maybe 10, 15 seconds if they want to leave, and then I think Nima can take some questions.
Oh, thanks.
17 hours.
One funny typo. You did, Lido, you did invent a new field of mathematics.
What, really?
Allegory.
No, I didn't. No, I didn't. I don't think I did. Allegoric geometry.
Actually, allegaic.
Oh, you're right. Allegoric. Oh, geez. Hold on. Thanks, Paul. Yeah, that's funny. Sorry, just 1 second. I'm sure this was bothering everyone as much as it was bothering Paul. Sorry. You're a happy man. All right, great. Oh, sorry. There we go. Let me leave this up. Sorry, you don't need to see my desktop. We've come a long way. Stay tuned. There we go. Great. Yes, any questions?
Well, you mentioned that in quantum said, you know, all we have to do to understand quantum mechanics is understand what you see experimentally. Do you understand?
Sure. Yes. Well, I mean, so everything about the measurement problem is explained by decoherence. Every puzzle, every confusion, everything, if you just think about the whole big system and you always include the system and the apparatus, everything together, there's never a problem. Now, there's one thing that people sometimes talk about, which is I think the nub of the matter for a lot of people with the interpretation of quantum mechanics is the following situation, right? That you do an experiment, let's say you see whether a spin is up or down, whatever. So, so the state is the spin is up or down, and then after you do the experiment, you have a state where the spin is up, the apparatus says it's up, your brain thinks it's up, plus, it's down, the apparatus says it's down, your brain thinks it's down. So it looks like the whole state, including you, is in some strange superposition between the two possibilities. And so what people wonder is, why, therefore, after any one experiment, do I feel certain that it was either up or down, and I don't feel like I'm in this strange superposition? As far as I can tell, most of these issues come down to that feeling question, okay? Why don't I feel like I'm in this strange superposition? Well, if you ask the question correctly, if you ask the question in the language of quantum mechanics, I mean, that's what we have to do when you test a theory. You have to take the theory on its terms, ask a question in the language the theory likes. Then you find that you can invent an answer to the question, am I certain of the outcome of the experiment? And the answer is yes, okay? Despite the fact that you're in this strange, entangled state. So I'm stressing this because I really believe that people say lots of nonsense about the interpretation of quantum mechanics. And they make it seem like there's something deep and crazy going on when you do something as dumb as look at this cup of coffee, right? It just sounds implausible, right? We look at coffee all the time. It would be very strange if the future of everything about physics depends on understanding that interaction, okay? Which is not to say there isn't something deep and mysterious about quantum mechanics. There is. It's very strange that the sharp observables that you talk about necessarily invoke infinities, necessarily invoke infinitely large apparatuses with an experiment done infinitely many times. But in order to come to grips with how strange that is, it makes sense to go to a situation where that strangeness becomes important. And that strangeness becomes important when the words gravity and cosmology are involved. So that's why I say, unless the word gravity and cosmology comes up in a discussion of quantum mechanics, there just cannot be a mystery. Or all the mystery is in our head. Which is not to say that there aren't mysteries, but the mysteries start happening there, as I described. Sure, yes. In fact, there's a whole slew of indirect experiments like that. Those experiments, I mean, there's already indirect evidence for dark matter around the galaxy from gravitational lensing. Right now, they're kind of at the factor of 2 level, so it's not sort of sharp enough and also, there are people who talk about really radical alternatives that, again, gravity is modified in some way, and since the size of these effects can almost be determined by dimensional analysis, it doesn't necessarily, it's perfectly consistent with dark matter, but you might imagine someone else saying, oh, it's consistent with my theory too. Those theories don't make very much sense, but we're very much as means really not very much. But anyway, but it's really not as good as having something hit your detector deep underground, right? And I think if we don't see WIMPs, it doesn't disprove the idea of dark matter by any means. There could be other things that could be dark matter, but it would be very nice. I mean, if we do see it, we do have direct evidence for a dark matter. Then we can just close that little. There is this possibility that gravity is modified at very large distances in some funny way, and one night out of 100. I wonder whether that might not be the right answer to this problem. If we actually discover dark matter, then I just won't worry about it anymore.
Maybe you should explain what WIMP is.
Oh yes, I think I said last time, but WIMP stands for weakly interacting massive particles. Okay, I guess the astronomers took 15 years to catch up with particle physicists and giving things dumb names. But there was WIMPs and there were machos, which were massive compact halo objects. So anyway, I really hope we return to an era of sanity in naming. Yes. Yes. That's exactly what I'm saying. Yeah. That's exactly what I meant. No, it doesn't mean it doesn't exist. It means it doesn't exist fundamentally. I'll give you the perfect analogy for it, is the word position and momentum. Position and momentum don't exist. They don't fundamentally exist. Because of quantum mechanics, position or momentum exists. An and turned into an or as we went from classical to a quantum physics. So at a fundamental level, position and momentum don't exist. Of course, no one disputes that it's an incredibly good approximation to a huge class of questions. And of course, space-time is an incredibly good approximation to a huge class of questions for us. But for these questions of principle, knowing that an and turns into an or makes a very radical difference in how you think the next layer of physics should be described. Definitely not. You see, that's as I said, there was a small group of theoretical physicists who take this attitude. It's something in my previous lecture I referred to as atoms of space-time. That saying space-time is doomed is like saying this piece of wood is doomed. If I go to very short distances, it doesn't look like wood anymore. I see all the atoms and molecules that make up the wood, right? Or there's some kind of granular structure. You go to very short scales and you see that it's like a discrete lattice or something like that, okay? That's a sort of very naive idea of what would happen if space-time broke down. And just from this thought experiment with the magnifying glass, looking at short distances, you might say, oh, that's all it means. It means that I can't actually talk about much shorter distances and times, so it's like a little lattice, just a little like lattice sitting there. It's like atoms. There's a very fundamental difficulty with that idea, which has to do with relativity, which is that the size of that lattice would not look the same to every observer. And that's a real hint that what's going on is much more interesting than that. And in the cases where we understand it very well, you saw exactly how much more interesting it is. Space-time really was doomed. The inside really was gone. And there was some description instead involving this holographic idea with things living on boundaries at infinity. That's, I think, one of the deepest sort of qualitative lessons we've learned about quantum gravity in the last 50 years. And people said it and knew it 40, 50 years ago, but not till 13 years ago did we see very sharply how it could actually work. It's something I haven't had a chance to, it's an unfortunate thing about lectures like this that you can't see the sort of magic of it really working. You know, when you see these things work precisely, sharply, mathematically, the degree of confidence you get in them is exponentially larger than when you hear about it. But it's unfortunately the sort of thing that's harder to get across in this sort of lecture. Yes?
When you spoke about the multiverse in your 2 to the 1,000
yes.
energy levels
yes,
and so on,
right.
but we live in the case where that...
yeah, we live in the one that's damn close to zero. That's right.
Yeah. What are the chances there's going to be a fluctuation in the next 10 to the minus 40 seconds, and those numbers are going to change, and suddenly we're expanding again? Right. Yeah.
Yeah. This is very important. So in that picture, we had these. In that picture, I drew actually a little well with a barrier sitting there, right? And if there's any reasonable size barrier, also the tunneling rates start becoming very, very low. So just like the rate for my tunneling across the wall is 10 to the minus 10 to the 30. Okay? The typical tunneling rates from one side to the other can be very small. That means that you sit in any one of them for quite a long time. Okay? Now, the important thing, all that matters, in fact, is if you tunnel out slowly enough that this picture of eternal inflation takes over, right? So let's say the doubling time of the universe when you're sitting in your first configuration is 10 billion years, okay? Or let's say it's 100 years, okay? Then if you tunnel out in 1,000 years, then that's fine. You still have an eternally inflating universe because you tunnel out here, you start expanding at the speed of light. The universe is doubling in size every 100 years. 1,000 years later, you tunnel out again. Forget it. Those bubbles are never going to hit each other. And so the process just keeps going on and on and on and generates this infinite universe. Okay? Now, I should say, again, that we certainly don't know experimentally that that's correct. We certainly don't know experimentally that's correct. That's what happens if we just take the laws as we know them and we take the radical conservative attitude of pushing it and seeing what it predicts. Okay? And if I haven't said it before, I will say it now, that theorists have much, much more often made mistakes not taking their theories seriously enough than taking them too seriously. Okay? So really, and the mistakes are that you refuse to believe predictions that your theory wants to make, which has happened over and over again. But so if you do that, you're led to this picture. The picture is incredibly confusing. And properly interpreting it is a major conceptual challenge. But it's not a philosophical challenge. It's a physics challenge. It's and we may not quite have the mathematical tools to attack it head on yet, but we really may, in the next 10 or 20 years, develop those tools. Yes? Yes. Yes. That's right. That's right. That's right. That's right. We don't know. I wish I knew. That's really a problem. So we suspect that we have to figure out what emergent time means. We suspect that because we've already seen that space is emergent. We know there's relativity that mixes up space and time. And we also see that all of our real confusions now with quantum mechanics and gravity and these very, very deep conceptual puzzles all involve cosmology. They all involve the time dependence of the universe that we have. Okay? So it's just a suspicion. I can't prove that time is emergent, but it's a suspicion. The trend that things are going seems to suggest that we need to make sense of the idea of emergent time somehow. But it's a massive challenge to figure out what it means, because if you don't have space, that's one thing. That's maybe that's okay. Things could still evolve. There could still be time. I mean, physics is about, ultimately, we think, for 2,000 years, describing how things change in time, from one time to another. We don't know how to get rid of time. But 15 years ago, we didn't know how to get rid of space and gravity, and we know how to do that now. Okay, so progress happens by people chipping away, doing the kind of, you can't make progress asking an incredibly hard question that you have no idea how to get started. And you don't want to spend all your time playing around with things that you can do so well you're doing them with your left hand. So the bleeding edge of progress in theoretical physics is to attack problems that are just hard enough, that are hard, but are just easy enough that you can articulate them. And you can start attempting to, lasso your way around them and do some calculation that might shed some light on something and just start hoping a surprise happens. It's a chaotic process, but it's worked for a long, long time. And we suspect and we hope that emergent time, it's now the right time to start taking it seriously. It might not be. Maybe we'll have to wait another 50 years before we have the right language. Maybe we have to wait another 200 years before we have the right language. But I think we suspect that it's the next thing. It's the next set of things that we're going to have to come to grips with and understand.
Maybe last question.
You just mentioned the names of those last class of experiments.
Oh, yeah. Well, so there's many wonderful experiments. So there are experiments, for example, that look for things like some of the elementary particles, like the electron. I told you the electron has some magnetic property. It spins. Okay? It could also have a funny electric property. So we think the electron is like point-like, and it has negative charge, but there's no sort of separation of that negative charge into a little more negative charge on the north pole of the electron, a little less on the south pole. Okay? Of course, you can't really think of it as a little sphere, but if you did. Now, if that little separation existed, it would be called something. It would be called an electric dipole moment of the electron. And the electric dipole moment of the electron is something which we suspect should be there in many, many of the extensions of the standard model that we've been talking about, but which, fortunately, the standard model itself predicts a completely minuscule size for. So it's the sort of experiment that if you see anything positive, it immediately tells you there's something beyond the standard model. These are wonderful atomic physics tabletop experiments. Beautiful experiments. They're very cheap, I mean, on the scale of things. And they're ongoing. So that's one of my favorite classes of experiments. Experiments looking for the electric dipole moment of the electron. There's classes of experiments that are looking for deviations from or measuring Newtonian gravity at very, very short distances, about 1/10 of a millimeter by now. So some of these experiments were inspired by these ideas involving large extra dimensions of space that people talked about 10, 12 years ago now. Gravity at that time had been measured down to around a millimeter, actually a little more, actually more like a centimeter. And if you ask why hadn't people measured gravity to much shorter distances, you remember I said it in these lectures, and many of you have heard, we say the statement that gravity is incredibly weak, except at large distances it dominates because everything else neutralize, right? Now, even when you neutralize, even if you take two neutral atoms, a hydrogen atom and another hydrogen atom, there is a tiny residual electric force between them. It's called the van der Waals force. Okay? That van der Waals force becomes comparable to gravity around a centimeter, and then gets much stronger than gravity as you go to shorter distances. So if you're going to measure short-range gravity, you have to screen out incredibly accurately all of these other stray effects. And people didn't have particular motivation to do it, so they didn't. But after these proposals came out, this absolutely wonderful group at the University of Washington, led by Eric Adelberger and Blaine Heckel, did these experiments and pushed and measured Newtonian gravity down to distances now about 100 microns or so. Okay? Shorter than a millimeter, 200 microns, 100 microns. And they're continuing. They're continuing. They're going to go to shorter distances. Now, this 100 micron scale is interesting because this is around the neighborhood where if you believed there was some modification of gravity that would solve the cosmological constant problem, it would show up around there. I told you it should show up around a millimeter, and I glibly did this experiment with my fingers, and I said we didn't see anything, okay, at a millimeter. But it's just conceivable, I think very unlikely, but just conceivable, that there is some purely gravitational thing which is going on at those distances and is somehow shutting off gravity at very short distances, shorter than 100 microns. And anyway, these are absolutely beautiful, ingenious experiments, absolutely pushing the frontier of what we can do, sitting on a tabletop. They're going to keep going for a while. There's another class of experiments that's motivated by, partially motivated by some of these anomalies involving dark matter, but really they're quite generally, which has to do with the possibility that instead of going to much higher energies to see all these extensions of space-time that we're talking about, that actually some of this physics, like supersymmetry, could be sitting there at much lower energies, much lower energies, but just not involving our particles and forces, but some other particles and forces. And that those other particles and forces could be relatively weakly interacting with us. Not that weakly interacting, like 1,000 times less strongly interacting than the ordinary things. Not 1,000,000 times, not a gajillion times, 1,000 times more weakly interacting. That ends up being a perfectly viable possibility. It could be that you have these extremely light particles lying around that we've missed for 50 years. They're just 1,000 times less strongly interacting than the ordinary stuff, okay? And they could have supersymmetry. They could have all of this wonderful stuff sitting there, not at incredibly high energies, but sort of next door, weakly coupled to us through some little portals that we can try to go through these weak couplings. So there's another class of experiments that involve not very high energy accelerators, but low energy accelerators with very high intensities. They're starting to happen now. Actually, just earlier this summer, there's a new class of experiments of that sort that are starting. They might see something. You know, that's what I said. These are fishing expeditions. If they see something, it could radically change the future of the field. Like, let's say one of these low-energy experiments sees something. Then all of a sudden, you could start looking for supersymmetry. You could study all these properties about the extension of space-time at low-energy machines using incredibly high intensities, not with 27-kilometer-around machines. Okay? But as I said, you see here, there's a basic guarantee, right? We're probing a length scale where definitely something's going to happen. Things talk to us. We know something is going on. These things are fishing expeditions because there are interesting theories that would say that something is happening there, but there's no a priori guarantee. Okay? I mean, there's never a complete guarantee of anything, but these are just things where it could be. It would be nice to go look, but if you don't see anything, it doesn't rule anything out. Okay, it doesn't. Those are 3 examples. There are even more. But I'm a very big fan of these relatively low-cost, cool experiments looking for a whole array of new phenomena. And there's more of them. Yeah.
Okay, that's that.
Okay.